Even in this pandemic situation, we have tried to maintain this legacy and decided to go online. With an intent to expand in terms of participation and quality with each year, more number of invited talks have been included. We are extremely happy that the amount of response we have received from the student conference this year, despite of the current situation, is huge. This year, the participation coming not only from this country, but also from the various parts of the world. This is the only conference in India which is for the students and organized by the students. All of this would not have been possible without the contribution of our chapter volunteers and the guidance of our conference advisors, Dr. Gautam Samanta and Professor R.P. Singh. I welcome our Honorable Director, Dr. Anil Bharadwaj. Being a Director of Physical Research, he always has been generous and helpful in organizing the annual editions of SCOP. I welcome all the faculties of different disciplines who are invited to deliver talk and reached here from the various parts of the world. And I also welcome all the participants who have enthusiastically chosen to attend this SCOP. I hope we all would gain maximum from this conference and implement our knowledge in the way that contributes to the people and society. With that note, on the behalf of entire SCOP team, I welcome each and every one of you to the 5th edition of Student Conference on Optics and Photonics 2020. Thank you and have a wonderful day.
Thank you, Ayan. It is my pleasure now to introduce our chief guest for today, Professor Anil Bharadwaj, Director PRL. Professor Bharadwaj initiated the research in planetary sciences at SPL and contributed to the development of planetary science activities in ISRO and planning of planetary missions in India. He was the principal investigator of SAR experiment on the first Indian lunar mission, Chandrayaan-1, which has revolutionized our understanding on the interaction of solar winds with the moon through several new findings. He is also the PIE of Menka experiment on the Indian Mars orbiter mission. Professor Bharadwaj has received many honors and distinctions, including the most coveted Shanti Swarup Bhatnagar Prize in 2007 and the Infosys Prize in Physical Sciences in 2016. Professor Bharadwaj is a member of ISRO and national level committees on the planetary and space science research in India and future missions. So with this, I now request Professor Bharadwaj to address the SCOP 2020 participants and to officially open the technical sessions of the conference. Over to you, sir.
Thank you, Deepika, and very good morning to all of you. Namaskar. A very warm welcome to all the participants, invited speakers, students, my colleagues from PRL, and all those who are joining us live on this program of inauguration of the SCOP 2020, that is the Students' Conference on Optics and Photonics. This is the 5th edition of the SCOP, and it is expanding every year. As Ayan just mentioned, that it is now more than 150 students who are attending this conference. This is a conference by the students, for the students, organized totally by the students, and a very special one because it gives the scope to the students and young PDFs to participate in a big way. This year, this conference is being held in a very special circumstances because of COVID-19. So keeping the social distancing in mind, it is being held totally online. And celebrating the birth centenary year of Dr. Vikram Sarabhai, that is year 2019-2020. And as you all may be aware that Dr. Vikram Sarabhai founded PRL, that is Physical Research Laboratory, in the year 1947, and he is also the father of the Indian space program. This conference has several topics which is related to optics and photonics. Either it is ultra-fast atomic molecular spectroscopy, quantum information, quantum communication, or even satellite-based communications, laser and ultra-fast processes, or nanophotonics, or nonlinear optics, or quantum optics. As you will see, this program is very exciting, 3 days program. with not only students speaking, but there are invited speakers who are going to who will actually speak on the subjects which will be highly beneficial for all the students. As I could see that there are about 14 invited talks in this conference and more than 20 student talks. So this is going to be a wonderful 3-day meeting to benefit all the students, as well as it will also provide a platform to the students to talk to each other and get benefited. I wish this conference a grand success in spite of we all communicating online through this way, but this will also help more participation who cannot travel otherwise in normal conferences. So I take this privilege in opening this conference and declaring it open, and I wish this conference a grand success, and good luck to all the students who are organizing and who are participating. And I warmly welcome all the invited speakers to this conference. Please take care of yourself, stay safe, stay healthy, and all the very best. Thank you.
Thank you very much, sir. I now invite Mr. Madhusudan, co-chair of SCOP 2020, to present the vote of thanks.
Thank you, Deepika. On behalf of the SCOP Conference on Optics and Photonics 2020, I would like to thank each and every one of you for being present here and making this conference a dream come true. Even in the midst of the raging pandemic, where all hopes of the conference was lost or blurry, our SCOP Advisory Committee, comprising of Professor R.P. Singh and Dr. Gautam Kumar Samanta, encouraged us to go ahead and explore the webinar option. I thank them for their constant, unwavering support, and I would also want to thank PRL and especially our director for supporting and giving us a nod to go ahead with the webinar. Without the infrastructural support of the computer center of PRL, webinar would have proven to be very difficult. Among them, one agency without which the webinar would have been impossible is OSA, Optical Society of America. The Zoom Premium membership shared by OSA with the student chapter of PRL is responsible for this virtual conference. I would like to thank all the volunteers of SCOP who are involved and are responsible for various things throughout the conference. Last but not least, the invited speakers, domestic or abroad, who were more than willing to present in our seminar and be a part of the 5th year student conference. I would also like to thank the student speakers and the poster presenters and all the participants for whom this conference is tailored to. To summarize, I would like to thank you all for the support that you're offering, and we request you to continue the same enthusiasm for years to come. Thank you.
Thank you, Madhu. So with this, our inaugural session comes to an end. And on behalf of SCOP 2020 team, I once again thank you all the speakers and all of you for attending this inaugural session. Please join us for the next session, which begins at 10 a.m. And thank you again, everyone, and enjoy the conference. I now pass it over to Madhu to chair the technical session 1. Thank you very much.
So good morning, everyone, and welcome to SCOP again, the first session for the first day of this virtual conference 2020. I'm your session chair, Madhusudan P, and this session will be titled Ultrafast Spectroscopy-I. Before we get started, I want to go over a few housekeeping terms and also let you know how you can participate in today's session. The virtual conferencing platform, Zoom, which we are using to host this conference, has some great engagement widgets that you can utilize. The first one being the panelists' pre-recorded videos will be played or shared, or the screen will be shared using the screen share button at the bottom of the window. I request all presenters to stick to the clock. To ask questions, we have a Q&A widget for all the attendees at the bottom right of the screen. Simply type in your question and I will read out each question out loud for the presenter to answer verbally at the end of the talk. Finally, the chat widget The chat tool can be used by other panelists to ask their questions since Q&A is absent in their panel. Chat can also be used to interact with each other and and comment on the presentations. Keep the sessions lively. Lastly, let's maintain the decorum for the conference and keep the discussions lively. After all these instructions, let's start today's first session, Ultrafast Spectroscopy-I. Firstly, we have Dr. Atanu Bhattacharya from Indian Institute of Science, Bangalore. He did his PhD from Colorado State University under Professor Elliot R. Bernstein. He is now an assistant professor in the Inorganic and Physical Chemistry Department at IISc. Some of his recent research areas include atochemistry of non-covalent clusters, development of ultrafast X-ray pulses, and many more. Without further ado, I welcome Dr. Atanu Bhattacharya to the spotlight and speak a few words before we play his pre-recorded talk video. Over to you, Atanu Bhattacharya.
Can you hear me now?
Yes, sir, we can.
Okay. I thank all of you for making me involved, particularly Rajesh pointed out about this conference when I had met him last year. Yeah, and it's quite unfortunate that I couldn't meet other faculty members in PRL. It would have been a good opportunity for me to interact with all of you. Anyway, we are working on exploring electron dynamics in the attosecond time scale. And I joined IISc in 2013. So for last 7 years, we have been working in this field. And I'll be presenting what we have understood so far. So with this, I think the video I have shared already with all of you. So you can start the video. And if you have any question, please feel free to ask me.
Yes, sir. Thank you. So the host can start the video right now. If there is any audio, we are unable to hear it.
No sound is coming. Yeah. If you want me, I can share the screen right now and start.
Sure, sir. If that is
from my side.
Yes, sir.
Is it okay?
Yes, sir.
Okay.
Why don't the host give the permission to share the screen to Atanu Bhattacharya?
Okay, somebody has disabled this screen sharing mode, I think. I need the access from you. Can you get me the access? Because it's showing that host disabled participant screen sharing.
Yes, sir. We have disabled it. We will enable it right now. Host, we can't hear it. So why don't you give the screen share option to Atanu Bhattacharya?
Yeah, I can see. Yeah, I can see now.
Yes, sir. Thank you.
Can you see that?
Yes, sir. We can.
As possible, so that we can understand. We all can understand this subject from a physical chemistry point of view. There are 4 important questions in this talk. What is the attosecond time scale? What is the role of attosecond time scale in chemical dynamics? What are the consequences of attosecond charge migration? How do we probe it experimentally? So we'll begin with the first question. What is attosecond time scale? The the natural time scale of electron can be understood if we look at the Bohr atomic model. We all know that Bohr atomic model has to balance the centrifugal force and the electrostatic force. And once you balance that, then we get the velocity of the electron. And for 1s electron in the hydrogen atom, we'll be able to find out what is the typical time scale it takes to take one orbit coming from this point to this point. So one orbit time is actually 150 attosecond. That can be calculated very easily. So this attosecond timescale is natural timescale of electronic motion. And here I would like to mention one thing, that the natural timescale of nuclei, which is 3 order of magnitude heavier than electrons, is actually femtosecond. Many of the talks in this conference will be based on femtosecond time domain, but this talk, particularly my talk, is based on attosecond time domain. Now, when we talk about this attosecond or femtosecond or microsecond, this time resolution in chemistry, in the context of physical chemistry, immediately one subject comes to our mind, and that's actually chemical dynamics. In chemical dynamics, we study how chemical reaction will progress over time as a function of time. Sometimes we call it chemical kinetics, sometimes we call it chemical dynamics. And it has a very long history. It started with Arrhenius' proposal, Arrhenius equation. You might have heard this Arrhenius equation in your first year graduate study, in your first year BSc, probably, in general chemistry course. Arrhenius equation proposed that if in order to react, two atoms, let's say, reacting, in order to react, you need to circumvent an energy barrier, and that barrier is going to be EA. So this idea of circumventing a barrier was an interesting idea proposed by Arrhenius. Then, after the advent of this quantum mechanics by 1935, transition state theory was proposed. Based on similar idea, activation barrier should be crossed, this EA should be crossed. But one interesting point came out of transition state theory for a particular reaction is that one unstable mode of vibration is involved, which will lead the reactant to the product side. And that happened in the transition state during the reaction. So that's, we are skipping. We are primarily interested in the time resolved study. And if we look at this time resolved study, slowly we have improved the time resolution to view the chemical reaction. So the first question is that after femtosecond, what is waiting? Is it attosecond which is waiting in the chemical dynamics study? When we talk about attosecond in the context of chemical dynamics, one dilemma we have to face. The dilemma is following. If we cannot, basically most of us can't consider chemistry without nuclear motion. When we say chemistry, we always think that, okay, two molecules, two atoms are reacting and forming product, which means reacting. What does it mean? It means that two atoms or nuclei are moving. So if we cannot imagine chemistry without nuclear motion, then attosecond does not have any role in chemical dynamics. But if we, because in attosecond only electron density can move, nuclei cannot move, nuclei is heavier than electrons. But if we freeze atoms, let's say, we do not allow atoms to move for a particular time. If we freeze it and try to understand how the chemical bonding going on, chemical bonding is a terminology which you might have experienced in some of the BSc courses. It is nothing but electron sharing, two atoms sharing electrons densities and making bond, shaking hands and making a bond between these two atoms. That is exemplified here in this cartoon diagram. Two 1s orbitals of hydrogen atom maintain the d distance. They are slowly sharing electrons and forming chemical bonds. So if we want to understand the dynamics of chemical bonding, that's the regime where we need to be, this attosecond regime. So I'll distinguish two things, chemical dynamics and chemical bonding. Chemical bonding is all about electron density sharing. That has to do with the attosecond time scale. But in chemical dynamics, we do not have any the relevance of this attosecond time domain. Now, we talk about electron density reorganization in attosecond time domain. And in chemistry, in physical chemistry, there are multiple contexts where we have discussed electron migration, charge migration, electron density redistribution, all these things we discuss. But all the discussions are actually based on nuclear motion. This is one example, Marcus theory and Forster energy transfer mechanism. Both theories are very, very dominating theory in physical chemistry, which discusses the charge migration, charge transfer. But if you look at this Marcus theory, we take a donor-acceptor complex. Let's say two molecules. One will behave like donor, donating. It has ability to donate electron. Another one can accept electron. They are together. They are sitting together, let's say, donor-acceptor complex, we call it. And we can undergo a local excitation. That excitation is going on, just let's say electronic excitation in donor moiety only. Acceptor is not excited. Donor moiety is excited. But this local excited state can hop to a charge transfer state where charge migration will happen through this conical intersection or this kind of crossing point. But we have to remember this charge transfer state can be accessed only by a particular nuclear configuration which has to evolve from the FC point, Frank Condon point, where the electronic excitation was undergone initially to this conical intersection. So electron has to wait until nuclei makes a decision to make this hop. And that's why electron dynamics is slow. It depends purely on the nuclear dynamics. But in attosecond regime, electron migration does not need to be dependent on the nuclear dynamics. It can have an indirect effect, but it doesn't directly depend on the nuclear dynamics. So that's exactly what I would like to distinguish. What we are conventionally thinking of charge migration in the context of Marcus theory and Foster energy transfer and attosecond charge migration, a little different. Now, is there any evidence? No field, even this attosecond field, didn't pop up suddenly. It has a long history, and probably some of the hints one can find out from old literature. This is a literature taken from 1995 by Weinkauf group. They took this molecule. What is that molecule? You don't need to know. This molecule has two moieties. One is shown by red color, another moiety is NH3 part, this moiety. And they were able to selectively ionize the molecule in this regime only. Why they can do that? They can use this ladder climbing, this multiphoton ionization scheme going through S1 state. And this S1 particular excited state is characteristics of this electronic state of this chromophore, this part of the molecule. And that's why they know that they have removed electron from this moiety. But after removing an electron by mass spectrometry, they are seeing that this CC bond is breaking. Now imagine bond. What is bond? We'll talk about this molecular orbital very soon, but bond is nothing but two electron system, two electron orbital, let's say, molecular orbital. And if we remove one electron from that, you are actually weakening the bond. And that's exactly the hypothesis was. Once you have removed an electron from here, you have created a hole, which is missing electron that must have migrated to this bond. And that's why you are breaking this bond far away from this chromophore. So that was the indirect hint taken from 1995, which discussed this possibility of attosecond charge migration in the chemical reactivity. This is another example taken from recent literature from Calgary group. They took this molecule, they ionized this molecule with the help of an attosecond pulse, 300 attosecond pulse. Then they double ionized this molecule with this 400 femtosecond pulse. And then as a result of this double ionization, they are probing this stable product molecule. And they have checked with respect to time delay, and they are seeing one oscillation at the early time delay. This oscillation has been observed. Now, imagine this is nothing but an ionization process, and seeing an oscillatory behavior, oscillatory modulation in the ionization probability is actually, it means that there is an internal motion, internal oscillatory behavior in the molecule, which is changing or modulating the ionization probability. You can imagine like this way. I have AB molecule, let's say, which is vibrating, is stretching and compressing, and during this vibration, I'm ionizing the molecule. And it may so happen that when it is fully stretched, the ionization probability is low. when it's compressed, ionization probability is high. And that's why high, low, this ionization probability oscillation, you can see something like this. But what could affect this ionization probability? The first hypothesis could be the vibration. Let's say molecular vibration is affecting it. And if it is affected by vibration only, then what they looked at, that based on that first hypothesis, they looked at the CH stretching period, the fastest possible vibration in the molecule. CH is the fastest because hydrogen is a lighter element, so it vibrates very quickly. So they have found 8.9 femtosecond, and the oscillation period they have observed is 4.3 femtosecond, which is way faster than the fastest possible vibration in the molecule. And that's why, based on this fact only, they concluded that there must be some attosecond charge migration going on, which is modulating this ionization process. So with this idea, we started working in IISc in 2013, and the first question came to our mind. This is, what would be our model system to work with? And the model system we selected is non-covalent bonded species. Let's say two molecules, H2, NO. These two molecules can actually interact with each other, very weakly can interact with each other, and they can come closer. They can form friendship with each other. And that kind of friendship, weak friendship, is called the non-covalent bonding interaction. There are multiple names which are being used right nowadays, but they are all weakly bound clusters, weakly bound molecules. And the reason why we selected these weakly bound molecules of two different molecules is that in the cluster is that if we can selectively ionize one of them in the cluster, then we can have an opportunity to see how electrons are reorganizing in the cluster. And why it should reorganize in the cluster? Because the mean field you have changed because of the missing electron. And with this hypothesis, we started working on both experiment and the theory. We were setting up the lab, and during that time, we were emphasizing more on the simulation. So first part of my talk will be focusing more on the simulation. This is one example of our work. Here, there are two molecules, NH3 molecule and ClCN molecule. These two molecules are weakly interacting. This dotted line shown the weak interaction, shortest distance of the weak interaction. This particular interaction, they call it, in chemistry, we call it halogen bonding. We do not need to know the name, the meaning of this name right now. This is out of context right now, but they are interacting, weakly interacting. And if we look at the ionization potential for these two molecules, we see that the NH3 having lower ionization potential. NH3 is actually lower ionization potential than this molecule. So it is quite obvious that the HOMO, highest occupied molecular orbital, what is molecular orbital? See, total wave function is extremely complicated mathematical expression or mathematical system. Total wave function has nuclear contribution, total wave function has electronic contribution. Now forget about electronic nuclear configuration, but because we are not going to change the nuclei here. Nuclei is fixed, frozen nuclei. But electronic wave function is even complicated. And that's why often what we do is that we decompose that total wave function into certain easily understandable wave function. And those wave functions are called molecular orbitals. Molecular orbitals are nothing but one electron orbitals. So how do we construct the total wave function, electronic wave function? We take the antisymmetrized product of the molecular orbital to get the total wave function. And this is exactly the molecular orbital with highest energy. That's called HOMO, highest occupied molecular orbital. So because HOMO is localized here, one can say that when I'm ionizing with the lowest threshold ionization, we are removing electron from this moiety only. Once we remove an electron, we are in the cationic state. We haven't changed the nuclei. For the same nuclei, we can re-optimize the mean field. And if we re-optimize the mean field, we see that there are two orbitals which are very interesting. These two colors are actually different phases of the wave function, of this one electron wave function. Now, the different phases. So if we add these two, without knowing much of quantum mechanics, if we add these two, then you can see that this positive term is going to eliminate this negative term. This negative term is going to eliminate this positive term, but these two will add up. So if we add this two, we get this. It suggests that at the initial point of ionization, we are creating a superposition of these two molecular orbitals. And quantum mechanics, time-dependent quantum mechanics, shows that even the wave function can be time-dependent, but the density which is related to the physical observables, experimental observables, they are not time-dependent. They become only time-dependent when you create a superposition state. And that's exactly what we are creating, a superposition of two molecular orbitals. And the period of this density, the time-dependent density, will depend on the energy difference between these two molecular orbitals or these two superposition states. So that's exactly what we understood, and with this simulation, we have expressed this initial hole density as a linear combination of these all cationic states, and the expansion coefficient we have used as the overlap matrix or the overlap integral between the HOMO, highest occupied molecular orbital of neutral, and the cationic orbital. And based on the simulation, this is the results. What results we are seeing here is that we at zero time, at the time when the ionization occurred, we have hole density. This is 1 electron hole density plot. This hole density is localized in the NH3 moiety. Within 500 attosecond timescale or 600 attosecond timescale, hole density is getting delocalized. Again, it's getting localized, delocalized, and that's exactly a wave pattern we are seeing in the electron density. But remember, this electron density we have calculated based on frozen nuclei. Nuclei didn't move at all. It's just showing the electron density change. There are many other molecules we studied. They have shown similar behavior. Those are the results actually included here. But as I mentioned, that so far whatever we have discussed is based on the frozen nuclei. What is that frozen nuclei? Frozen nuclei is actually this R naught for the nuclei, for the ground electronic state. That is the equilibrium point or equilibrium nuclear geometry in the ground neutral state. And that's the point of geometry we have taken. But we have to remember that molecule does not exist at that point. Molecule actually exists in the lowest vibrational state. And the lowest vibrational wave function itself has a width. It cannot have a single geometry which can contribute to this charge migration. It is the multiple configuration and nuclear configuration which is going to contribute. So instead of taking only electronic component as a superposition of two molecular orbitals, what we did, we multiplied by the nuclear part. And nuclear wave function multiplied by electronic part is giving the total hole density. This is more like the Born-Oppenheimer kind of approximation. And within this Born-Oppenheimer approximation, what we did by doing this integration, what we see that the final density, that's the cross term, depends not only on the oscillatory part, which is cosine oscillatory, but it is decaying with the help of this Gaussian decay as a function of time, and that's exactly shown here. Once we create the hole at a particular moiety in the cluster, they will start oscillating, but the amplitude of oscillation will decay, and slowly it is delocalizing over the entire cluster. And that's exactly what we have found. Why this oscillation going on? Because of the mean change in the mean field of the electron. Because I have removed an electron from the cluster, so mean field has changed, and mean field will reorganize, it will reshuffle the electron densities, and that's causing it. So what I have shown here so far is the pure electron-electron relaxation. Another problem which came up during this study is that oxygen cluster can be very interesting model system for this kind of study. Why? It's because these oxygen clusters are very important for laser ignition chemistry. This is little bit of chemical point of view. Laser ignition chemistry is nothing but a strong field chemistry. Why? It's because nowadays we are using spark plug in our internal combustion engine. internal combustion engine has a spark plug, and we are actually burning fuel oxygen mixture with the help of spark plug. But nowadays, people are proposing that laser ignition can be a good way to do this combustion, and one can focus the laser beam to a very small focus pot, and they can burn this kind of oxygen ethylene or oxygen fuel mixture. So this is the proposal which is coming up, and if we look at the oxygen benzene cluster, they are actually formed in the molecular beam. What we are thinking that, okay, if we take oxygen fuel cluster and try to understand what might happen in the after ionization, we see that we are removing electron. We can remove electron from the fuel molecule, because all the fuel molecule like methane or any molecules, they have their lower ionization potential than oxygen, and that's why we can remove one of the electrons. But dealing with oxygen is a little bit tricky, because oxygen is paramagnetic in nature. That's why one can remove electron from this one or this one, and depending on what kind of electron we have removed, we can create a quartet state or doublet state, which are almost quasi-degenerate. Computationally, we have seen less than 10 wave number difference, so they can be considered to be degenerate theoretically. So if we look at these two states, interestingly, one state, doublet state, is showing charge migration based on the simulation. One can raise a hand and stop me and ask me, how do you know that these simulations are correct? We don't know. We are going to talk about it experimentally, but based on the simulation what we have, let's assume that they are correct. Based on this simulation, we see that in the doublet state, they can undergo charge migration, but in the quartet state, they do not, which means that it must be driven by exchange interaction. So exchange interaction driven attosecond charge migration can be explored with the help of these oxygen clusters. This is what we have found. Now, after doing all this theory, by the time when we did this theory, we were able to set up the lab, and we had the lab ready. So question is, how do we probe that? Experimentally, we can probe with the help of high harmonic generation spectroscopy, which is also called self-probing electron density or self-probing spectroscopy. Why it is self-probing, I'll discuss it very soon. In high harmonic generation, what happens, we create harmonics of 800 nanometers. Second harmonic generation, third harmonic generation, we are very much familiar with, but high harmonic generation is not something which we frequently do in all labs. The high harmonic generation can actually create 9th harmonic, 10th harmonic, or even 100th harmonics. It's an extreme nonlinearity which can be induced in a medium. So what happens, we use, because it is going to the high harmonics can create X-ray beam, soft X-ray or XUV beam. We actually do it in the gas phase, because no crystal can actually handle that kind of frequency. Below 200 nanometer, crystals will start absorbing, and that's why we have to use in the gas phase. In the gas phase, we very tightly focus the femtosecond laser beam. If we tightly focus, then tunnel ionization occurs, and we set one electron free. The moment we set one electron free, because of this tunnel ionization, this free electron will see the oscillatory field of the laser beam. And oscillatory field is changing the direction, and that's why electron will go away from the parent cation and it will come back to the parent cation. And there is a possibility, I'm not saying that the possibility is 100%, but there is a possibility that this electron is recombining with the parent cation again. And if it is going on, recombination occurs, then what happens? There will be a burst of energy. The energy will be released. What is that energy? Energy is the binding energy, IP, ionization potential, binding energy of that electron, and the kinetic energy which is gained during this flight, during this travel of this electron. Both energy will be released. And because of this release, what we see is that there are multiple harmonics we create. It's not a single harmonics we create. We can create a continuum of harmonics. And typical spectrum looks like this. This is third harmonics. Because we are using gaseous system for high harmonic generation, gaseous system is an isotropic medium. It's not like BBO crystal, which are anisotropic medium. in isotropic medium, because of the symmetry, it doesn't produce even harmonics, it produces odd harmonics. That's why third harmonics we produce, fifth harmonics we produce, seventh harmonics we produce, ninth harmonics, and so on. We keep going like this way. And we see that the first few harmonics intensity will go down very quickly. Then there is a plateau regime where intensity does not change much. And then suddenly there will be a cutoff regime where the intensity will drop down to 0. And that's the typical harmonic spectrum, what is expected from the high harmonic generation. This is the experimental setup. We'll go over the experimental setup a little bit in details. We are creating high harmonics in the semi-infinite gas cell. This semi-infinite gas cell, the length of the gas cell is longer than the confocal length of this focus. And if we look at this semi-infinite gas cell, we create this high harmonics. The harmonics beam is shown with the blue light. This blue light and the red light needs to be now separated. And the way we separate it, first we use 2 silicon wafers to steer the beam. This 2 silicon wafer can cut down 80% of the 800 nanometer beam. And then and very interestingly, when we use X-ray, this blue beam is actually an X-ray regime. This X-ray refractive index is less than 1, and near IR refractive index is greater than 1. And this difference makes a big change. It's more like viewing the world. We are viewing the world, and a bat viewing the world is entirely upside down. When X-ray, we are talking, if we think about X-ray, when X-ray going from lighter medium to the denser medium, it will undergo total internal reflection. On the other hand, near IR, when it's going through a denser medium to the lighter medium, it's actually undergoing total internal reflection. So when we use this grazing incidence angle for the X-ray beam, it's undergoing the total internal reflection for X-ray, but 800 nanometer will be absorbed. So 80% and 80% beam will be absorbed in the silicon wafer. Then remaining beam will be absorbed by this aluminum foil. We know that the X-ray beam can penetrate more in the metal, and that's why you have used aluminum filter. Very thin aluminum filter, though. It's not like the kind of filter we use in kitchen, but it is the thickness, typical thickness is going to be 500 nanometer. It's like that. Then once we separate these 2 beam, we have refocused the beam and with a toroidal mirror, and with the help of this grating is a aluminum gold coated grating. We have dispersed the beam and we can see the spectrum. And it is expected that we should see the spectrum something like this. This first quick decay, then plateau, and then cutoff. But instead of seeing that, this red color spectrum we observed in our lab, and that was the first puzzling part for us. It's not puzzling that much once we understand it. What happens, we are using aluminum filter, and aluminum filter can actually cut down the energy below 15 eV. The transmission, it doesn't have any transmission, so it will not transmit the beam. So above 20 eV we see. On the other hand, any aluminum surface we take, pure aluminum surface, because of the oxygen in the environment, it will be oxidized. The surface will be oxidized immediately. So we have not only aluminum surface, alumina coating we have on the surface, and alumina has a transmission which is slowly increasing over the frequency range, and that's why we are seeing a slow increase in intensity in the harmonic spectrum. Instead of seeing plateau in this regime, we are seeing increase, and then this decay, of course, for the cutoff regime. So what we observe here, this is taken from N2 gaseous system. We see the cutoff regime of the spectrum. So basically we are seeing in this regime only in the cutoff regime. Then once we have standardized and calibrated our spectrometer and the system, we thought that, okay, what would be the first experiment we would like to perform? The system we selected is that chloroform. This molecule is chloroform. Chloroform, you know, in your 12th standard, you have used chloroform for frogs. And so this is chloroform molecule, CCl3CH. And then this is acetonitrile molecule. These 2 molecules, for a physicist, this can be a little hard to remember these molecules. These are 2 different molecules. okay, and they are forming hydrogen bond. This weak interaction between hydrogen and nitrogen, this weak interaction is called hydrogen bond between these two molecules. And if we use the same simulation which we did previously, we see that at 0 femtosecond time scale, we are removing an electron from chloroform. Obviously, because chloroform has lower ionization potential than this acetonitrile molecule. Once we remove an electron, within 1.8 femtosecond, the charge oscillation going on, and they are delocalizing the charge. And if we look at the semi-classical theory of three-step model of high harmonic generation that is proposed by Corcom, based on that semi-classical way, one can predict what would be the flight time for the electron responsible for the cutoff regime. See, we are looking at the cutoff regime of the spectrum, and that's why we have to think about those electrons which are responsible for the cutoff regime. And electron, when emitted from the molecule, due to tunnel ionization, they will recombine first to get this energy, to keep the burst of energy. So this 1.8 femtosecond we have found for the cutoff, the electron responsible for the cutoff energy. And that was a little bit surprising for us at that time, because simulation is showing 1.8 femtosecond, and the time scale is also showing 1.8 femtosecond. And if this is true, we cannot accept all simulation to be true unless we verify with the experiment. If it is true, then we should have some signature in this change of this electron density, because electron was removed when 0 femtosecond, at the 0 femtosecond, but electron is recombining at 1.8 femtosecond when electron density has redistributed in the molecule. For a comparison, we kept this chloroform moiety same, and we have changed this acetonitrile, replace acetonitrile molecule by methanol molecule. Methanol is alcohol. We are very much familiar with ethanol, but methanol is another kind of alcohol. So this is also forming hydrogen bonding. And if we look at these two different clusters, their binding energies are the same, similar kind. And in FTIR at room temperature, we did that study. They can be observed. We can observe this hydrogen bonded species. This kind of cluster do exist at room temperature, and our experiments are actually at room temperature with the help of the semi-infinite gas cell. What we see that for this cluster, there is no charge migration going on. And that was the biggest surprise. So we have now two different clusters. One cluster theoretically showing charge migration, another cluster theoretically does not show charge migration. So we should expect some behavioral pattern or change in these two clusters. We'll talk about it very soon. This is the typical spectrum we have observed from N2, then CH3CN, and then CaCl3. This is chloroform, this is acetonitrile, and they all depend on the pressure. It depends on the pressure because this is a nonlinear frequency conversion, and any nonlinear frequency conversion depends on the phase matching. Phase matching is a condition which needs to be fulfilled in the nonlinear frequency conversion. In a simple way, phase matching is nothing but like this. I have a medium. In the medium, when fundamental beam is propagating through the medium, I create polarization, and polarization is nothing but creating a dipole, oscillatory dipole. So let's think about two oscillatory dipoles. The first one, which I have created in the beginning of the crystal, and in the end of the crystal, I have created the dipole, and both oscillatory dipole will emit light. So both oscillatory dipoles are emitting light. Question is whether these emitted light are in phase or out of phase. That controls final efficiency of the nonlinear frequency conversion. And because we are the medium is not a crystalline medium, it's a gaseous medium, or in more specifically, it is actually mixed neutral plasma medium. We are creating plasma because a lot of ions would be there, a lot of electrons would be there. At the same time, we have neutral system as well. So because of this neutral and plasma together, they are forming this medium. We have dispersion relationship, and all this dispersion relationship is going to control this phase matching condition for this high harmonic generation. We see that they have all of them having this P term. This P is actually pressure. we can change the pressure to get the phase matching condition fulfilled. And that's why pressure dependent behavior we see. And that's why you have to be very careful. What we see is that, very interesting, we see that if we take acetonitrile individually, chloroform individually, we see no spectrum at a particular pressure. But if we...
excuse me, sir.
Yeah,
so
yeah.
You have 2 more minutes.
2 more minutes. Okay, okay. So, so I'll go to this point. So we have, if we look at this acetonitrile chloroform mixture, we have an enhancement in the signal. But if we look at the acetonitrile helium or acetonitrile CCl4 or acetonitrile methanol, none of them are actually giving the enhancement. And we believe that this is because of that the change in the electron density. For this simulation, we collaborated with Dr. Gopal Dixit in IIT Bombay. What we have found from this collaboration is that this problem is very simple, one single active electron problem where we have one electron moving in the field. This is the field, the electrostatic field, which will be experienced by that electron, that single active electron. And remember, this field, molecular electrostatic potential field, is changing over time. And we have seen a entirely different electrostatic potential. Because of that change in electrostatic potential, this is the dipole acceleration term, which is going to contribute to this intensity pattern. We see that the intensity will be enhanced for the acetonitrile chloroform component, not for other components. So based on this, we can conclude many things right now, and there are future directions are based on that. Already we have realized that oxygen cluster can be a good point, starting point. We are working on that oxygen clusters. We haven't presented the results yet. And we should use different center wavelength for the HHG so that we can change the trajectories of the electrons. And in the end, we have to use photoelectron spectroscopy also. So rabbit experiment needs to be proposed here, because you see that the electron densities are changing, and that's why it can induce the delay also, depending on how quickly the electrons are moving. So going from 0 femtoseconds to 600 attosecond, if we have a change in the electron density, that may actually induce some delay in the rabbit experiment. So this is exactly what we are working on right now. So I'll stop here, and if you have any question, please go ahead.
Sir, so there are several questions in the questions and answers section. So Ashimani Nyog is asking, can we say that most of the chemical reactions is in attosecond time scale?
No, none of the see, when you say chemical reaction, nuclei has to move. And nuclei has to move, it means it has to be slow. It has to be either femtosecond or slower than femtosecond. It cannot be in attosecond time scale. But chemical bonding, where electron densities are shared initially, that can be initiated in the attosecond time scale. So one can say that attosecond is prelude to the femtosecond chemical dynamics. How electrons are reorganizing, that can give an hint how nuclei will move in the end. Because remember, nuclei does not move alone. If nuclei is moving on the potential energy surface created by the electron, so it is the electron which is the game player. But we have kind of neglected electrons in that respect so far.
Okay, so we have another question from Sunil Lahar. He's asking if experimentally we can find charge migration in attosecond using EIS, electrochemical impedance spectroscopy.
Electrochemical impedance spectroscopy, I am not familiar with. I'll write down this one, but I'm not familiar with this. Electrochemical, yeah, I'm not familiar with this.
Okay. Sir, I have a question. You said the electronic oscillations, they in the clusters, they transfer. You showed that there is a decaying dependence. So does that depend on the size of the cluster?
Larger size of the cluster we haven't tried yet, but it may affect. Definitely, it may affect the size of the cluster. and size-dependent behavior we haven't done yet. We are still working on this kind of system to make the experiment work. Yeah, but I'll remember this point in my mind. Size may definitely affect.
Yes, sir. So we have one last question from Pranav. He's asking, can we simply use longer wavelengths to get data points at 0.6 or 1.2 femtoseconds without actually going to attosecond beams?
What did you say? What did you ask? Seems to be an interesting question. Can you ask me one more time?
Yes, sir. So he's asking if we can simply use longer wavelengths to get data points at 0.6 or 1.2 femtoseconds without using attosecond beams.
Longer wavelength, you can see. So if you, the problem is that, see, you can use longer wavelength, but the problem is that the whole, so yeah, if you use few femtosecond pulses, let's say, and with the help of few femtosecond pulses, you can see a snapshot, let's say after 2 femtosecond or 3 femtosecond. So there are parts which are missing now. And all the experiments which can give currently attosecond time resolution, one of them is streaking and another one is the rabbit experiments. These experiments are giving attosecond time resolution based on some other factor. It's not a straightforward extension of the femtosecond spectroscopic techniques. So longer wavelength can help you in a different way. Longer wavelength can help you in the HHG, high harmonic generation spectroscopy, because if you increase the wavelength, then the electron, which will be spending more time in the flight, it will not recombine very quickly, and that means that you are allowing the cation to relax a little more. So depending on what kind of wavelength you are going to use, you can actually see a different electronic environment. That's the way I understand.
Okay, sir. Thank you for that. So I would like to thank Dr. Atanu Bhattacharya for presenting the talk in our seminar. So now we can go to the next seminar. Now we have Dr. Rajeev and Kini from the Indian Institute of Science Education and Research, Thiruvananthapuram. He did his PhD at University of Nottingham. He is now an assistant professor at IISER Thiruvananthapuram. His current research areas include light matter interaction in the quantum regime, ultrafast optical studies of emergent material systems, terahertz spectroscopy, and much more. Without any delay, I welcome Dr. Rajeev and Kini to the spotlight and ask him to share his screen for the talk on application of terahertz spectroscopy in fundamental science and industry. Over to you, sir.
Okay, thanks for the introduction. Am I audible?
Yes, sir, you are.
Okay, very good morning, and thank you for the invitation and giving me an opportunity to present some of the work here in this conference. Okay, so I'm going to talk about some of the work that we do here using terahertz spectroscopy. So I will try to show you 2 examples from our recent work. One is actually on a condensed matter system. It's a charge density wave compound, and using terahertz spectroscopy, we have looked at the charge density wave phase-on modes in this layered compound. So that is from the perspective of basic science or fundamental science. Okay, and then I'll also give you one more example from the other extreme, which is using this terahertz spectroscopy for industrial applications. So I will look at something like a non-destructive testing of thermal barrier coatings. Okay, so I'll go through this one by one. Before I start, I should actually acknowledge the guys who have actually done this work. So this charge density wave work was done by my PhD student Shaumitra, and the samples we got it from IISER Pune, and those were grown by Rabindranath Bab. in Surjit Singh's group. Okay, and the second part of the talk, in which I look at the non-destructive evaluation of thermal barrier coatings. This work was done by 3 of my students. One is Ria, she's a project assistant with me, and Vivek Vijan, who was a BSMS student and who is going for a PhD now in France, and Vaishak, he was a PhD student who is a postdoc now. Okay, so to begin with, I'll start with what this terahertz radiation is. So, you know, most of you are familiar with the electromagnetic spectrum, and you know, the terahertz radiation or terahertz waves fit right in between the microwaves and IR radiation. So these microwaves and the ones below, that is the radio waves, can all be accessed using the regular electronics, while the IR and the, you know, visible UV spectrum can be you know, obtained using photonic technologies. So for quite some time, there used to be something called terahertz gap, because this terahertz radiation couldn't be generated efficiently, but not so anymore. There are now different ways to generate terahertz radiation. So why do we even need these terahertz radiation, or what do we do with them? Actually, these have the energy scales because they are in the millimeter waves, and the energy scales of these are in milli-electron volts. Those actually go hand in hand with many of the excitations in condensed matter system, like the one I'm going to explain today. So you can have phonon modes and superconducting gaps and so on, which have energy scales of the same as this electromagnetic radiation in the terahertz regime. And also from atomic and molecular spectroscopy point of view, the rotational transitions in gases and so on also fall in the same terahertz regime. And these also play a role in non-contact nanoscopic conductivity. What do I mean by that is, in general, when you want to measure the conductivity of a material, you have to make you know, electrical contacts, send a current through it, and so on. But you can use terahertz electromagnetic waves and measure the photoconductivity without making any contact. So that's like a non-contact probe, and especially this is important if you want to study you know, small nanomaterials and nano layers. Then it is difficult to make contacts, and you can use this for that. Okay, so similarly, these electromagnetic radiations are actually transparent to several different materials. For example, as I show here, you have several different samples. One is actually paper. There is a piece of plastic, which is HDPE, and metal, and so on, scattered around. But and if you actually look at this from using a terahertz imaging system, you can identify these depending on the you know, the transmission of terahertz wave radiation through this. So this gives you opportunity to use this for different applications. Like you know, one could look at from quality control point of view. One could look at the you know, for example, water content in different materials, or you know, defects in you know, defects in food products and so on. Again, non-destructive testing using imaging or conductivity mapping, and this also plays a role in the security systems, where you can actually the terahertz in the terahertz regime, different explosive materials have signatures, and you can use terahertz spectroscopy to detect and identify different explosives. So this means that this terahertz spectroscopy has applications in pharmaceutics, food manufacturing, defense, and automobiles, and so on. Okay. So here it's an example from a paper where they have actually used terahertz spectroscopy to look at the drying process of paper, and in the one on the right hand side, they have actually done a study or trying to identify diabetic foot syndrome using terahertz, and what they propose is actually one can in a deterministic manner predict the possibility of having diabetic foot syndrome using terahertz imaging. Okay. Similarly, here is an example of a conductivity mapping of a large area CVD grown graphene, and as I said before, you don't need it to make any contacts, and using raster scanning of this terahertz beam, one can make the conductivity mapping and also make an idea about the the quality of this thin layers. Okay. As I said before, these terahertz waves have signatures, or these explosive materials have signatures in the terahertz region, and you can use terahertz spectroscopy to identify and also detect the presence of different materials. So there are cameras available which use terahertz electromagnetic waves for screening the patient, screening the travelers in the airport. And TerraSense, a company which manufactures these kind of terahertz imaging system, here is an example of that. And they have actually used their imaging system to detect, for example, a gun concealed inside a cardboard box. Okay, so this terahertz science has a very good connection with the semiconductors, because you can use semiconductors to generate terahertz, and you can use terahertz to actually probe or study semiconductors. So they kind of go hand in hand. And as I mentioned before, there used to be a gap in the spectrum where it was difficult to get terahertz radiation, but with the advent of femtosecond lasers, one could easily generate. So David Austin demonstrated the generation of terahertz radiation using what is called a photoconductive antenna, or Austin switches. The idea is very simple. So you have actually an antenna kind of structure which is excited, antenna-like structure on a semiconductor which is excited using a femtosecond laser pulse, and by applying a bias, these photo-generated carriers are accelerated, and that gives rise to terahertz radiation. So it's not necessary that you need to have an antenna structure. You can also generate terahertz radiation from a bare semiconductor surface, and so you have a ultrafast laser pulse which is impinging on a semiconductor surface, and due to two different processes, one is optical rectification, other is actually transient currents at the surface, which can give rise to terahertz radiation in semiconductors. Okay, so here in the case of photoconductive antenna, just a schematic of what I just said before. So you have a piece of semiconductor with an antenna structure on it, and a femtosecond laser pulse is impinging in the area between the two electrodes, and the electrode, this is biased so that the photo-generated carriers accelerate in this due to this electric field, and the accelerating charges, or the photo-generated carriers give rise to a terahertz radiation. So you can use the same kind of photoconductive antenna in the reverse geometry to detect terahertz radiation. So if you have the terahertz radiation incident on the same antenna, this will provide the bias for these carriers, and they will accelerate, and they give rise to a current in the antenna. So this photoconductive antenna works as a detector as well as an emitter. Okay. So the photo-generated carriers and along with the electrical bias leads to carrier acceleration, and that works as terahertz emitter. And the photo-generated carriers with the terahertz electromagnetic wave providing the bias gives rise to a photocurrent, which then can be used as a detector. Okay. So this is a very simple schematic of the experimental setup. So you have a Tie-Sapphire laser, which gives around 100 femtosecond laser pulses, which are split into two, and one is used to excite a photoconductive antenna, which gives rise to terahertz radiation, and the second pulse, which is split from the laser, is used to excite a photoconductive antenna, which is used as a detector. And if you are doing spectroscopy, probably either in the reflection geometry or the transmission geometry, it passes through your sample and it gets detected. And the time delay between the probe pulse and the pump pulse, which is the terahertz emitter, is adjusted using a delay stage. Okay, this is a very schematic setup. Okay, so what you this is just a typical terahertz pulse that you detect. So this is the terahertz electric field that you generally detect, and if you use Fourier transform of this, you get information in the frequency domain. So you make measurements in the time domain by changing the delay time between the pump and the probe. Okay. So one of the advantage here is that actually you make measurements, direct measurement of the electric field profile, which means you have information about the intensity or amplitude as well as the phase. So using this, you can actually gives you access to the complex properties of the material that you are probing, whether it is a refractive index or dielectric function or optical conductivity. Okay, so that is the advantage with this time domain spectroscopy. Okay, and you can actually directly determine the optical conductivity from the transmission or the reflectivity, and you get the complex refractive index or dielectric constant or the conductivity from the transmittance or the reflectance. Okay, so you can actually get information about the, like I said, because the energy scales that are involved here are few milli-electron volt, and so you get information about this material that you are studying and about their transport, quasi-particles, phonons, and so on. Okay, so with that brief introduction, I will go on to one specific example of a material that we actually use terahertz spectroscopy to study. Okay, so this is called this is a strontium copper oxide, and this is actually a layered material because it has this strontium 14, copper 24, oxygen 41. It is called telephone number compound. It's 142441. That's the number. Okay, this is actually a layered material which has two types of layers. One is the copper oxide chain layers, okay, which you can see here. These are the chain layer. So there is one layer of chains, and then the next one would be a ladder layer, which looks like this. Okay, so this alternates between chain and chain ladder with the layer of strontium between this. So it's like a layered material with two types of layers. One is the chain and one is the ladder. Again, these two layers are structurally incommensurate. What do I mean by that? The structure, the lattice constant of this is not equal. So the lattice constant wise, the lattice constant of the chain is smaller than the lattice constant of the ladder. So they are in the ratio 10:7. Okay, and they again there is an excess holes in this system as a it's not intrinsically hole dope, and most of the holes reside in the chain. Now, since there is this structural incommensurability, the chains which are slightly more flexible compared to the ladder, they buckle and form a wavy pattern. Okay, and because of that, now since the structure is also buckling, the electron density or the hole density is also modulated with the same pattern, and this is what gives rise to this charge density wave in this material. So you have the charges which are the excess charges that I talked in the last slide, they are arranged in a periodic manner. So this gives rise to charge density wave. Okay, and so when this material is cooled, so this gives rise to gaps in the phonon spectrum. Okay, and when it is cooled below a certain temperature, which is actually the charge density wave temperature, so normally it is an insulator, and below this temperature it becomes a charge density wave insulator. So it undergoes an insulator to insulator transition at the charge density wave transition temperature. Okay, now so that you can see here, this is the DC conductivity of this material, and the slope, this is actually on the log scale with the reciprocal temperature here. So the slope changes at this CTW transition temperature, and the slope at the lower temperature denotes the gap of this charge density wave mode. Okay, now as I said, so you can see the signature of this charge density wave in the DC conductivity, and the gap, the charge activation energy, which is equal to the charge density wave gap, is about 130 MeV or so. Okay, so this is well studied. The charge density wave formation is well studied, but from the spectroscopic point of view, there is still not an agreement between what is the frequency or what is the signature of this charge density wave mode. Okay, so not only the charge density wave mode, there is also another. The charge density wave, as I said, it is actually arrangement of the charges in a ordered fashion. Now you have 2 degrees of freedom associated with this charge density wave. You can have the modulation of the amplitude of this wave, or you can also have a modulation of the phase. So these two gives rise to what is called amplitude on mode or the phase on mode. Okay, so the amplitude on mode is more like the optical mode, and the phase on mode is more like the acoustic mode. So when you have an acoustic mode, the energy is 0 when you have when K is 0. Okay, so essentially, if that is the case, if you have a phase on mode like that, then since the energy is 0, you cannot couple light to this. Okay, however, in this case, because of the structural incommensurate nature, this phase on mode is not 0 at the energy is not 0, but it is lifted up by a small amount of energy. Okay, and there is one more interesting feature that you can see in this. As I said, you have actually chain layers and ladders in here, and they actually have they are oppositely charged. The chains have negative charge and the ladders have positive charge. Okay, and you can have relative motion between this. So you can have a IR mode wherein they slide past each other. Okay, and this gives rise to what is known as phonon modes, and they have energies in the range of 250 to 300 gigahertz. Okay, so these have been observed in Raman and optical conductivity. And what we see is a signature of this as an excess contribution to the specific heat in the a specific heat measurements. I'll come to that in a minute. So when you do specific heat measurements, you see a bump here, and it occurs around 10 Kelvin. And in energy scale, 10 Kelvin is close to 0.25 terahertz or 250 gigahertz. Okay, so let's come to the experiment. So as I said, you can generate a terahertz pulse by using a semiconductor. So usually what you use is low temperature grown gallium arsenide, because it has a very small or very short carrier lifetime in that. So what we have used is actually not a gallium arsenide, but a gallium arsenide with a little bit of bismuth in it. It's a low temperature grown gallium arsenide bismuth to generate this terahertz pulses. I will come to this again in a minute. And we have used a standard photoconductive antenna as a detector. Okay, these samples were mounted on a cold finger of a closed cycle refrigerator so that we can cool down the sample. And to avoid absorption of terahertz radiation by water vapor, this whole setup was purged with nitrogen gas. Okay, so as I said, compared to low temperature gallium arsenide, we have used a bismuth incorporated low temperature gallium arsenide, because some of our earlier studies have shown that you can get a better emission when you add a little bit of bismuth in this. Okay. Moreover, what we found is even though the intensity that you get from using a bare semiconductor is very low compared to using a photoconductive antenna, the spectroscopic features, the bare semiconductor emitter gives better features when you do spectroscopy. So for example, here I'm just showing you the terahertz transmitted amplitude measurement done using a photoconductive antenna and a bare semiconductor, which is again gallium antimony doped with bismuth. Okay, as you can see, this is transmission through a BBO crystal, and this is supposed to have three, four modes in this frequency region, and you can see them much clearer with this bare semiconductor. As I said, the intensities are much lower, maybe around 100 times lower, but still the the features, spectroscopic features, are much clearly seen when you use this semiconductor emitter rather than a photoconductive antenna. So here is the same data, but converted to the absorption length. So you can see that with the gallium arsenide bismuth emitter, you can see it much more clearer. Okay. Now, so we have used this gallium arsenide bismuth as an emitter. So this is the transmitted terahertz wave after passing through the strontium copper oxide or the telephone number compound. Okay, and just for comparison, this is what you get if you use a interdigitated photoconductive antenna. So especially we are interested in this fast oscillation that you see here, and those are much more clearer when you use this simple semiconductor emitter. Okay, and what do we see here? Let me explain that in a little bit more detail. So what you see is after passing through this, so this is essentially a leakage of this terahertz, but you see this oscillations which have an oscillation period of about 1 picosecond, and additionally you also see an oscillation which is a very slow oscillation, okay, which has a period of about 4 picoseconds. So there are two features. One is this 4 picosecond oscillation and a 2 picosecond oscillation, and this fast oscillation, which is 1 picosecond oscillation, occurs about below the charge density wave transition temperature. Okay, now the same data is transformed into the Fourier domain. So you can see the spectral features now. You see a very sharp cutoff region at low temperature, and again, there is a cutoff at a lower frequency here. So there is a 0.25 terahertz cutoff and a 1 terahertz cutoff. So once this sample does not transmit this gives rise to a peak in the transmission. So this is the peak. So there is a peak at near 1 terahertz, which is giving rise to this fast oscillation. And there is another peak is formed, which is around 0.25 or slightly lower. That is giving rise to this slow oscillations. Okay. Now, what are these, or where do these features come from? So I will talk about this. So like you have a 0.25 and a 1 terahertz cutoff. So the low frequency, which is the 0.25 terahertz terahertz mode, is well known. It is actually, as I said before, these two layers can slide past each other and give rise to these sliding modes or sliding phonon modes. And the frequency 0.25 terahertz, as I said, that corresponds to about 10 Kelvin in temperature. And we see a bump at 10 Kelvin in the specific heat measurements, and hence those are assigned to the sliding density modes, okay, sliding phonon modes. Now, the second feature, which is actually the fast oscillation, where do they come from? If you measure, so I forgot to mention, these measurements were done with the electric field of the terahertz parallel to the C-axis of this crystal. But if you do the same measurement with the electric field parallel to the A-axis of the crystal, then you don't see any of these oscillatory features in it. So which means that these oscillations, or whatever is causing this oscillation, is also anisotropic, or something is happening only in certain directions. Okay. And secondly, if you do a temperature dependent, so here the oscillations have shown as a a color plot at different temperatures. Okay. So this is the time axis. So you have oscillations, and that is one. So these oscillations disappear if you warm up above a certain temperature, which is actually the charge density wave temperature. Again, if you look very closely, if you go very close to the transition temperature, what you see is the oscillations also undergo a phase change of pi near the charge density wave transition. Secondly, again, the same oscillations I can convert to frequency domain, which is shown here. Okay, and you have this sharp cutoff, which is 1 terahertz, and they disappear above a certain temperature, which is your charge density wave transition temperature. So, and also if you dope it with cobalt or aluminum, all these oscillations and all these features disappears. And from all this, what we understand is these oscillations have something to do with the charge density wave. Okay, because it is known that if you dope with cobalt and aluminum, the charge density wave is destroyed in these systems. Okay, as I said in the beginning, you also get access to the conductivity of the material in this optical conductivity of this material using terahertz. So you can take this transmission data and convert it into the real and imaginary part of the conductivity. Here I am showing the imaginary real part of the conductivity. Okay, and what you see is just below 1 terahertz, about 0.98 terahertz, you see a mode. Okay, which was represented as this giving rise to these fast oscillations. And this again, the same feature, this mode disappears above the charge density wave transition, and we assign this to the charge density wave phase zone mode. Okay, so essentially what I wanted to show is, using terahertz spectroscopy, we could actually study such a complicated system and get information about collective excitations in this condensed matter system. Okay, so that was the first part of my talk. And as I said, we could actually see the sliding density, the sliding phonon modes, as well as spectroscopic signature of this charge density wave phase-on mode in this system. Okay, and the next part, as I said, I will switch gears and go completely into something which is application oriented. So here we use terahertz spectroscopy for non-destructive testing or non-destructive evaluation of what is called thermal barrier coating. So thermal barrier coatings. So for example, if you take a turbine engine or aircraft engine, it goes through a lot of thermal cycling, and to protect these metal or alloy parts, they are coated with what is called thermal barrier coating, or these are ceramic coatings. And as I said, terahertz penetrates through many different materials, including paper, and it's also transparent, almost transparent to this thermal barrier coatings, which are ceramic materials. So one could use this terahertz spectroscopy to actually see whether these thermal barrier coatings are good to go, or how much degraded they are. And at this point, I should say that, here there is a picture of this turbine blade with a lot of air holes. Okay, and the only way even today to actually inspect whether these are the thermal barrier coatings are intact or not is still a visual inspection. Okay, and a technique to actually non-destructively evaluate them is highly desirable. So what you can do is, as I said, you generate these terahertz pulses, and if you actually make them incident on this thermal barrier coating, from the top surface there will be some reflection. Okay, this is what is giving rise to this first one, and they will actually pass through the thermal barrier coating and get reflected from the next layer or the metallic layer between the interface between the TBC and the metallic layer. Here I have put it at bond coat. Actually, bond coat is something which helps to bind this thermal barrier coatings to the alloy parts. So you will have a reflection from the next interface. This will give rise to the second pulse, and again, there will be multiple reflections which will give rise to the second reflection. So it's like an echo, right? It's just like a ultrasound, but in this case we are using electromagnetic waves, and they go and get reflected at different interfaces. And if you look at the time between these two echoes, you can get an idea about the thickness of this layer. So if they have degraded, this will arrive faster, and you can make it. So what we have, so this is actually some signals from a sample. So what happens? How does this degrade? There are several different ways this TBC degrades. One of them is actually, of course, at the top, the thick layer gets corroded. Another way is actually, because it goes through a lot of heat cycling, there is a oxide layer which is formed between this thermal barrier coating and the bond coat. So that essentially reduces the thickness of this TBC layer. So it is interesting to see what is the thickness of this bond coat, or how the thickness of the oxide layer which is grown between the TBC and the bond coat. Now, these are actually signals from two different samples. One is actually a pristine sample which has not undergone thermal cycling, and the another one which has undergone a few hundreds of cycles. Now, how do you analyze this? So you can actually look at the just Fresnel's reflection equations. So you have an incident pulse at the interface with the two different refractive indices, and you can calculate the reflectance and so on. Not only that, most of the time, right, these layers have roughness of the order of hundreds of microns, or slightly less than that, maybe 20 to 30 micron roughness on the surface. And as I said in the beginning, this terahertz wave also has wavelength in the range of microns to millimeter. So now, if the surface roughness is of the order of the wavelength, you have to also consider the surface roughness, and you can incorporate that surface roughness into your consideration, and you can calculate the multiple reflections. So what we did is we created a code wherein we plug in the reference signal, and using a fitting procedure, we could recreate the signal that is actually detected, and from that we could estimate the thickness of the layers as well as the presence of thermal oxide, thermally grown oxide layers in this. Okay, so this is I will probably skip. This is actually simulation of the spectra at a different blade position, and essentially one way to look at the thickness is actually cut it and do an SEM imaging, where it gives you a very accurate, but it's a destructive testing. Okay. Another possibility is that, as you can see, that this signal is actually repeating in the time domain, right? So if you actually convert it to frequency domain, what you see is actually a oscillatory pattern in the frequency domain, and this oscillatory pattern also changes with the thickness of this layer. This is very similar to what is called phasic oscillations in the X-ray diffraction, and one can also use this information to calculate the thickness of this layers. Okay, so with that, actually, I'll kind of conclude. All these measurements that I showed you were done in a lab, something similar to this. Okay, it was done on a very huge table. Okay, each table weighing around a ton or so, and with a laser system which sits on that. Now, let us say if you have to do these kind of measurements on a turbine blade or on an engine, right? You cannot bring that engine back into the lab, or neither you can't take this lab or the table or the laser into the field. Okay, so how do you miniaturize this whole setup or the whole measurement into a wheelable cart, so that this can be taken into the field and the measurements can be done? So probably that is the future direction for this non-destructive testing using terahertz spectroscopy. Okay, so with that, I will stop, and I'm ready to take a couple of questions. Thank you.
Thank you, sir. So we have a question from Deepika Yadav. She's asking, what are typical dark currents of LT, GA, ASBI photoconductive antenna, and how do they compare to other semiconductor emitters used here? Can you please comment on the dynamic range of your detector?
So Deepika, so again, we haven't made any photoconductive antenna with this this gallium arsenide with bismuth in it. This is just a bare semiconductor.
Okay, so so we have another question from another platform on YouTube. Mohit Soni is asking, what is the usual time difference of the reflected terahertz wave and the incident wave in thermal coating degradation?
So it depends on the thickness of this TBC layer. Okay, for example, here I have shown, I guess this is about 160, 170 microns thick. And so you see about 20 or 10 picosecond difference here. So it also depends on the refractive index of the material and also the thickness of the layer.
Okay, sir. So thank you for your talk. The recording has stopped. This meeting is being recorded. I now cordially thank Dr. Rajeev Kini sir for his presentation.
Okay, thank you.
Thank you, sir. So the next talk should have been Titas Das, a student talk, but since he opted out to present, we can break now and regroup back at 12 o'clock. But the floor of this webinar will be open for discussions. Anybody who has questions in your webinar chat, you can start up your mic and your camera if needed, and you can start discussing on the webinar channel. But till 12 o'clock, there will be no official commencement of any session. At 12 o'clock, we will regroup. Thank you. Dr. Atanu Bhattacharya, are you here? Dr. Gopal Dixit, sir, are you here? So welcome back, everyone. Now we have Dr. Gopal Dixit from Indian Institute of Technology, Bombay. He did his PhD at Indian Institute of Technology, Kharagpur. His research areas include four-dimensional imaging of electronic motion, time delay in photoemission, to name a few. So let's welcome Dr. Gopal Dixit to talk about attosecond science meets condensed matter physics and give him the spotlight. Over to you, sir.
So thank you very much. Can you hear me? And can you see me?
Yes, sir, we can.
Okay, so let me share the screen. So now everything is visible, right?
Yes, sir.
Okay, so thank you very much for the invitation. And I was very keen to visit PRL and meet some of my colleagues there, old and new friends, but unfortunately due to this pandemic, this could not happen. But anyway, thank you very much for organizing this conference via web. So let's start. So I'm going to talk about attosecond sciences and its application to the condensed matter physics. And I'm from IIT Bombay, and we have an Ultrafast group in IIT Bombay. So as you have seen in the first talk today, that attosecond science basically rely on one of the important process, which is known as high harmonic generation. And I will brief you what is this all about. So let's say you have a gas jet and flowing in this, let's say this direction, and you shine an intense infrared laser field. And when this laser field interacts with this gaseous system, each gaseous atoms or molecules start emitting a radiation. And whenever you have a constructive interference among these, which is known as phase matching in a technical term, you will get some soft X-ray or XUV radiation in the detector. And whenever you have destructive interference, you do not have any signal at the detector. So what is happening when this intense laser field interacts with this let's say this gaseous molecule, and what type of a spectrum you supposed to get. So this is the typical spectrum of high harmonic generation, where you see the first few peaks, which are the integer multiple of your fundamental frequency, start dropping. So this is called a perturbative regime. And then you have a plateau regime, where you have all the intensities of all the harmonics are equivalent, and then you have a cutoff regime. And this is a signature of, let's say, the really strong field-driven high harmonic generation, because this is a regime where your standard perturbation theory, whatever you have learned in quantum mechanics, breaks. Because perturbation theory tells you that the signal at higher order is supposed to be the weaker in compared to the previous order, and this is not happening here, which is happening in the below ionization potential regime. And how to know what will be the cutoff of your typical harmonic spectrum? So there is a well-known cutoff law, which is ionization potential of your gaseous atoms or molecule plus 3.17 times UP, where UP is your perturbative energy cycled over averaged over laser cycle. And UP depends on the two quantities, intensity of the laser and energy, the frequency square of your laser. So what is happening? What is the main mechanism to drive this high harmonic generation? So this is a famous three-step model proposed by Paul Corkum. And what is happening? So this is your laser field shown in the green. And this is your atomic system shown in your Coulombic potential. When your field is zero at this point of time, your system is intact. And once you start increasing the strength of your laser field, your barrier start suppressing. And then there's a finite probability that the electron can tunnel it out. Once it tunnel it out, then it start propagating in the presence of laser field. So it will acquire energy. You know from the classical electrodynamics that a free charge in the presence of electromagnetic radiation acquire energy. And once the direction of the field changes and it reaches to the same zero, then the tunnel electron will recombine, and this recombination will result as an emission of the radiation. And this can happen at any time during the laser cycle. Okay, and this is the scenario I have presented when you have linearly polarized laser field, and immediately after, let's say, around 87, 88, and after 93, when Paul Corkum gave this model, people thought, okay, what about if we change the polarization of our driving laser field from linear to circular? Because the circular radiation is also important to study, for example, magnetic material and all kind of dichroism studies that condensed matter people are interested. But immediately it came out that once you change the polarization from linear to circular, the yield of high harmonics drops significantly and you don't see any harmonics at all. The reason is simple that that the tunnel out electron will spiral out and it will throw out, and the probability to recombine will be very, very small, almost negligible. So this was the hurdle for quite some time actually. And in very recently, around 2014, of course, the proposal immediately given by the Wilhelm Becker and colleagues in 1995, and then later refined model in 2000, but it was not easy to implement experimentally. And the idea was very simple, that instead of using one circular driver, you have to choose a combination of the two counter-rotating circularly polarized laser fields, so that the displacement induced by one laser field will be compensated by the displacement by the counter-rotating laser field. And if you plot this counter-rotating laser field into first time, it has a very nice symmetry, threefold symmetry. And here what we have, what is called as omega to omega. So if one frequency, one laser field is your frequency omega, the other should be 2 omega and vice versa. Okay. Of course, this was the proposal, but as I told you that it was only possible in 2014. So this is the first paper by Oren Cohen from Israel, where they have implemented this scheme successfully, and they have managed to generate tunable polarized high harmonic generation. And after that, immediately the other group, Yann Mares from France, and then Oren collaborated with Margaret, and they have followed up this one. And at this point of time, there was two challenging questions. The first question was, indeed, you are able to get the circularly polarized higher order harmonics, but it does not immediately guarantee you that the attosecond pulses, which are coming from high harmonic generations, are also going to be the attosecond, are also going to be the circularly polarized, because you are using left and right-handed circularly polarized light. So there could be a possibility that the polarization of your resultant attosecond pulse could be unpolarized, because both can cancel out. It can be linearly polarized, which is rotating by 120 degrees every time, or it could be anything. More about, these are the time-dependent electric fields, so your polarization of your light field changes time to time. So how you can measure it? And if you want to use the traditional way to measure the polarization of light, let me warn you that this will not work at all, because first of all, time dependency. But if you do not have any time dependency of your ultra short pulses, these are the pulses which are in the XUV regime or in soft X-ray regime. So it means that they have a very broad bandwidth, and there is no material which can cover such broad bandwidth. So all kind of your polarizer analyzer concept will immediately break down. And that was the challenge in 2015, 2016. And this was the time when we have provided the first solution to this one. And this is the paper that we have published in Nature Communication, that how you can record the polarization state of light with attosecond resolution, and this is based on extending the standard attosecond streaking method to multi-dimensional streaking method, not into one dimension, which is standard procedure. This one. At the same time, we have another paper which we have published, which is quite a popular scheme now, how to control the helicity. So if you do not want, let's say, for example, only circularly polarized light or linearly polarized light, you can have something in between elliptically polarized light. So how you can tune all kind of epsilon t value. Okay, and this we have proposed in this paper, which is under review, work done by the Irfana in my group. And now let's move, which is the main topic of my presentation, that high harmonic generation in solid. I mean, I was a little bit puzzled in the morning talk that speaker told that the solid will not survive in the presence of the laser field. This was a little funny to me, because the whole field is now flourishing up for high harmonic generation in solids. So the whole story started in 2011. Of course, it was not possible in till 2010. So the whole thing has been changed starting from 2011, and this is the result from David Rees and Lee DiMauro and the work done by Sambu Gimere. And what they have done, they have observed the high harmonic generation in bulk crystal, and in this particular case, they have used zinc oxide. And one of the interesting features they have found, which was puzzled for quite some time, that the dependency of the harmonics is linear with the electric field amplitude, not with the intensity, which I have shown in the case of gaseous system, where your cutoff is proportional to UP, and UP is proportional to intensity of the driving field. And here it is proportional to the amplitude of the driving field, not the intensity. So that was the first puzzling thing, what is happening. The second puzzling thing came even more surprised, that here you can see these are the polarization of the driving field. It starts from linear to completely circular. And you see that the harmonics are produced. They're not suppressed, unlike the gaseous system. So what is really happening in this case? So what is the driving mechanism? And that was still a debate, I would say. It's not a well-settled question. And there are several proposals along this line. So let me give possible options, what is happening. So let's say this is a very simplified picture of your solid. So you have a valence band, and then you have a conduction band, and you shine a laser. And due to this strong laser, what can happen? The electron can promote it from a valence band to the conduction band. And because your light is oscillating back and forth, so like in atomic case, your electron is freed and it is oscillating in the presence of electric field. Here, it start oscillating in conduction band. At the same time, the hole is also moving in the valence band. So there is a two type of processes. One is what is called interband transitions or interband polarization, and the other is interband current. And at any time, the electron can recombine with the hole, and this recombination can result as a radiation. So there are two possible competing mechanisms. And if your strength of electric field is strong enough, then electron at the first Brillon-John boundary can climb to the higher lying conduction band, and then it can emit even higher energy radiation. And if you want to see the typical radiation emitted by the HHG in solids, it's completely different what you have seen in atomic systems or gaseous systems. Here you can see, again, you have a typical signature of the below ionization potential, and here we call as a below band gap. And then you have a plateau. Then you have a drop of the signal, and again you have a plateau. So you have a multi-plateau regime, which is completely different what you have seen in gaseous system. And this has been actually observed. Another important questions which came in around 2016-17, that if you read any standard condensed matter textbook, be it Title or a Scrap Marvin or anything, whenever condensed matter physics or band structure comes, you always start thinking in terms of the momentum space, because then you say the K is a good quantum number and you start fulfilling what is called Bloch theorem. So unlike the gaseous system, when you have a real space mechanism in condensed matter, there is no real space analog for high harmonic generation. And quite recently, last year, we have proposed the first real space recombination in high harmonic generation in solid. So high harmonics in solid is very attractive from several points of view. First of all, the electron densities in solid is much higher than electron density in gas. So the emitted radiation is going to be very intense in compared to the gaseous system. Not only that, the electron which is traveling this, and when it recombines, it has all the information about the curvature of your band. So this method can be used to map the band structure or energy band, as well as it can also use to understand electron hole dynamics and their intrinsic time scale and phase transitions, both light driven and topological, because band structure are also sensitive to the topology of your material. And these provide an alternative of your another method, what is called angle resolved photoemission spectroscopy, what is typically done to measure the band structure of your solid. And the high harmonic generation is another very promising alternative method to image the band structure or the energy bands in the solid. Now the question I'm going to pose is as follows. Whenever you prepare a sample in your lab, it's very difficult that you can avoid different kind of defects. So defects are inevitable in real solid due to the growth process, and defect can be of any type. It can be a vacancies, it can be impurities, it can be interstellar, and these can be neutral as well as the charge, dislocation. And these defects is well known that they have important role to modify the macroscopic properties, and which have important consequences in the macroscopic properties. And you know, these kind of defects are very useful for the single photon emitter, nitrogen vacancies in diamond, which are used for qubit and quantum computation and all these things. So the question that we try to address in 2013, that time, that how different kind of defects are going to affect this high harmonics in solid, and can we do something? Is there any useful? So this was completely unknown question, and for this purpose, what we did, we have chosen, for example, let's say a 2D material, hexagonal boron nitride, and we have a pristine hexagonal boron nitride where there is no vacancy, and then we can create a vacancy by either removing a boron atom or either by removing a nitrogen atom. Or we can also remove it and substitute by a carbon atom, which is analogous in the same periodic table. And we'll see this how high harmonic signal is going to affect and what is the interesting or important things we can learn. I hope I'm audible, right?
Yes, sir, you are.
Okay. So let's see what is happening. So what we are going to do, we are going to use 15 femtosecond pulse with peak intensity around 13 terawatt per centimeter square, 1.6 nanometer, 1.6 micron wavelength, and the polarization of the light, we are in this particular case is choosing linear, which is the direction normal to the mirror plane of the HPM. So let's see the spectra. So here is the spectra for the pristine and compared with the boron vacant HPM. And if you see it here, you see a drastic difference, and especially in the below band gap regime. So let me zoom this part. And if you see this zoomed part of this small region, you see that especially the third harmonics intensity is drastically enhanced compared to the pristine one. Remember that the y-axis is the logarithmic axis. So it's not the linear, but in the log scale. So it's a several order of magnitude enhancement. So this immediately tells, okay, something is happening. So let's see what is happening and what we can do. Also, we can resolve the harmonics in spin resolve fashion. So what we have done here, we have resolved in spin down and spin up. Red corresponds to spin down, and this green color corresponds to spin up. And again, whenever we zoom it, we see that the spin down is contributing much more than the spin up. For the first harmonics, nothing. For the later on, everything pretty much similar. But in this particular regime, this is something significant is happening. Okay, so let's go to nitrogen. Again, the spectra is very, very different. And something interesting is going on again. Whenever we zoom this small portion below the band gap of hexagonal boron nitride, here again we see the third harmonic is enhanced drastically. Not up to that level, but it is enhanced. And when we do the spin resolve, this thing, whenever we compare the boron vacant with the nitrogen vacant, we do see some kind of difference in the higher one. And when we do spin up and spin down, here we see other way around. So spin down is not contributing as compared to the spin up, whereas in the previous case it was spin down, and here it is spin up is contributing. So something is going really strange. So to answer this question, so this is the summary for the boron vacancy case. Different spin channels are contributing differently, and the below band gap harmonics are drastically enhanced. So to understand what we did, actually, we started analyzing the band structure of your system. So this is what is called effective band structure. Why I would call it effective? Because to see the vacancy, you have to go to the supercell approach. Means the Brillouin zone size start reducing as you increase the size of your unit cell. And to map everything in the same, so you need to do what is called unwrapping, and that's why we call effective band structure. So this white dotted line are the band for the pristine, and the color coded are the strength of your band structure for the boron vacant HPN. And if I zoom this band gap regime, what I would see for the spin up channel, there's one defect state or the gap state, whereas for the spin down, I would see the two gap state. And you see that the dispersion relation of these gap state are a straight line. So this shows that these are kind of localized defects. They do not have any kind of mobility or any kind of interaction with the neighbor. And this is the typical energy spectrum you get in the atomic case, which are the localized system. So what you have seen that the removal of boron atom from the system makes the system spin polarized. With the total magnetic moment is plus 1 Bohr magneton, and the structure of HBN reduces to the lower symmetry. This is not important in our case, but this explains, if you think in a very simple manner, why the third harmonic is enhanced. So the third harmonic enhanced because when you shine a laser, these are the unoccupied levels. So this will also start contributing to, let's say, the interband transitions here and here. And you remember interband transitions are important for the below band gap regime. So the spin up channel is contributing 1 in compared to the spin down channel for the two paths, and the interferences of these paths are responsible for the enhancement of the third harmonics and related to the spin down channel. So this is what I have said it. Now, if you look how the defective states, it's clear that these are the 3 defective states. One corresponds to the one spin, and these 2 corresponds to another spin counterpart. And you can clearly see that these are the very well localized states for 5x5 unit cell, and all these defects are unoccupied. And that's why in technological term, these are sometimes called triple acceptor, and the local symmetry reduces from D3S to C2B. These are not important, but this tells you that at the end of the day that what is the region. So different spin channels are contributing differently, which is not the case when you have a pristine. Now let's see how these channels are important. So what we have here, computed. So this is your vector potential of your laser field, and this is your signal. Black corresponds to the pristine, and red corresponds to the boron vacant HBN. And when you see that the number of excited electrons per unit volume integrated over first billion zone, then you can see that once the laser field is over, all the electrons return back to the convex valence band in the case of pristine, which is not true for the vacant. Some of the defect states are going to be occupied even after the pulse is over. So this is completely different. And this means that these defected states, defected samples are much more robust towards the laser intensity of your driving field. Now I will turn another important role, which is important in this case, how the electron correlation is playing a role. So when you have a pristine, these are the calculations done at two levels. One is the TDDFT level, when all the electron correlations are taken into account. And this brown color is when your electron correlations are not taken. So these are the independent electrons in your solid. And you can see that these are very well captured within two models. So when it comes to the pristine, it doesn't matter. However, when it comes to the defected solid, it matters when you see that the orange, which is the correlated signal, is very enhanced for the third harmonics, whereas the independent or no electron correlations shown by the purple, it is much suppressed. So this means that the electron correlation is also very important when it comes to defected state, and it is also responsible for the enhancement of the third harmonics, which is going back to kind of local field effect and shielding of the charges and all these things. I will not go into detail of all these things because it will not important in this case, but let me turn into nitrogen vacancy. Nitrogen vacancy, the conclusion was that here the spin up channel is contributing much more to the spin down, and indeed the third harmonic is enhanced. So let's look the effective band structure here. So in this case, spin up, there is a one defective state, and spin down, there is a one defective state. Spin up defective state is found to be occupied, and that's why it makes one single donor. So there's only one channel which is contributing, and that's why we see the enhancement. I mean, the high harmonic generation in solids started the whole business in 2011, the first observation, first report, and it took, let's say, a couple of years to understand the mechanism, and people started looking this business into more detail. Indeed, people have attempted to look how the defective states are playing a role, but people have never managed to courage to do the simulation for this one. The reason is when it comes to the solid and when you want to do defect modeling, it is a nightmare because you have to have a very large supercell. So for the 5x5, we have around 100 atoms, including all the electrons. These are not effective potential kind of calculations. These are all electron calculations. And propagating this in presence of laser field and all these things are nightmare. So these are some numbers, and you can see that when we simulated for 5x5 spin polarized calculation, it was around 5.5 lakhs processor per hour. And this was a nightmare. I mean, we one single calculation, we did a hell lot of calculation to make sure all the results are correct and all these things. We also looked if you remove boron or nitrogen, and instead of creating a vacancy, you do a substitution by carbon, and the results are pretty much analogous to the nitrogen vacancy. We have also looked at the dye vacancy and all kind of things in a very intuitive way. And let me now give answer in a very nutshell. You don't need to do a lot of calculation. This is the whole idea of having a physics mindset, that let's say when you have a graphene, all the carbon atoms are fulfilling the valency. Okay. Now you know that when you dope the graphene with the boron or nitrogen, so boron has 1 electron less in compared to the carbon, and nitrogen has 1 electron extra in compared to the carbon. So both these atoms can be treated as electron dopant and electron acceptor, and that's why in one case one spin channel is playing important role, whereas in another case one spin channel is playing an important role. And the interesting thing is that when you come to the carbon doping, when it depends how you are doping, when you are removing the boron and replacing boron by carbon or replacing nitrogen by carbon, carbon can behave in this particular case, acceptor or donor, depends what site you are replacing. Okay, so this was the whole idea about all these things. But there is one important message, which is after all these things, if you have ever learned the magnetism or magnetic materials, you always learn that if you want to probe the magnetic properties, you always need a circularly polarized light. Then only you can do the dichroism kind of study and do all kind of things. What we have shown in this work is really that the linear polarized driven process are electron spin sensitive, which is a very, very important message that we have given to the community. So if you would like to read the detailed, so the whole work is done by the Mridul, very courageous work, more than 1.5 years writing the code and all kind of calculation. And the whole thing is reported in this 2020 paper in computational material from the Nature group. And the calculation were done in the Max Planck cluster in Germany. Now I have some time, so let me turn into a very interesting and very recent result, valuetronics in graphene. So let me tell you what is the valuetronics. So in solid, you have electron spin, you have electron momentum k. These are the good quantum numbers, and people are manipulating these kind of things to make different kind of devices like spintronics and all kind of things. I would not say in 2-3 years, but in long time, people always thought, why not to exploit the Wally degrees of freedom, which they give the pseudo spin kind of quantum number, and let's exploit these Wally spins, Wally quantum numbers in solid to encode the information and do maybe quantum computing and maybe for different kind of architectures in solid. Threefold in 0 degree, and they are contributing like a destructive interference. Whereas when you look the fifth one, here they are contributing more like a so here they are destructive interference, here they are constructive interference. So different regime of K and K from values are contributing differently when you are rotating the CEP to the total harmonics, and this is the way to selectively probe the value of one over the other, and this is very, very important. So what we have done it here, we have just integrated over all the electronic population at 2 different values, and we have seen that how we can switch population from one value to another value selectively, and we can have a value polarization something of the order of 20% to depends on how we have. And moreover, this value polarization is not sensitive to the polarization of your driving field. So whether your omega is counter-rotating and co-rotating or vice versa, the value polarization is very robust. And this value polarization is very, very important in quantum computing. So this is the paper because they want to code the qubits and all these things. So this is a very, very important message to the condensed matter community that indeed the single layer graphene can do a very polarized measurement, and thanks to this ultrafast or high harmonic generation in solid. And those who have a very basic knowledge of nonlinear optics, let me tell you very important message here from the physics point of view. Graphene is a centrosymmetric system, right? So it means that graphene is supposed not to show any response at the even harmonics, like second harmonics, fourth harmonics, because this is the signature of centrosymmetric signal. Here you have seen that we have a second harmonics, then we have a fourth harmonics, fifth harmonics. So what is happening? Still we have a centrosymmetry of our graphene intact. The thing is happening here that the laser field is, so here we have to treat the whole system as a combined system, and the laser field is breaking the symmetry. So this is a dynamical symmetry breaking from a very, very physics point of view. Okay, so with that, let me conclude with the future that all the electronic chips, or let's say the MOSFET in your computer, are operating at the gigahertz. Whenever you buy a laptop or desktop, you see the clock speed, and these are the 3 gigahertz and something like that, and you want to go. And there's a saturation because you cannot have more and more transistor into a chip in your integrated circuit, because you have to keep track of the of your heat induced by this one. So this is a saturation. I do not have a time much into this direction, but so what is the new field that is emerging out in last few years is called petahertz. Petahertz is 6 orders of magnitude higher than the gigahertz. And the idea is that the light performs several hundred trillion oscillations per second, which is a petahertz. So it is obvious to start looking that light oscillations can drive the electron motion. It can not only drive, it can also control. That's what we have seen. And this have a potential to improve the operational speed of your devices and computing by several orders of magnitude, and this open. And by selectively controlling the spins of your material, we can go to the spin tronics in petahertz, which is much, much more than the reading and writing the data in your hard disk. So this is the whole future, and that's what we are going. I mean, I would not say conclusion in 1 or 2 lines. This is an ongoing field, and this is our quest to look very interesting materials. Now we are going into more topological and wild semi-metal, Majorana fermions, and all kind of fancy condensed matter things. I also do a lot of basic atomic and molecular. I do not have time to talk in this one. We have a very strong research subgroup in my main group, which are doing X-ray for electron laser driven research. We have a beam time this year to perform some experiment in the first X-ray for electron in USA, LCLS. So hopefully we will get some meaningful. With that, let me advertise important things. Those who are Attosecond or Ultrafast enthusiasts to know, we are organizing a Faraday discussion on time resolved imaging of photo-induced Faraday discussion. Next year, this is going to be online meeting because of this pandemic, unfortunately. And these are the keynote speakers. All are the very well-known speakers from the field, like Misha Ivanov, who gave the quantum description of your high harmonics 3-step model and all the people. So those who are interested, they can join to this meeting. And thank you for Ankhel and his group for HBN, and Misa and his group for graphene. This is part of my research group, and most of the work is done by Mridul here. And thank you very much for your kind attention. And this is the website of my lab if you want to know much more about what kind of paper we are publishing. And that's it.
Thank you. That was a very interesting talk indeed. So I have a question, sir. So higher harmonics are usually caused by the electron coming out of according to the 3-step model, it comes out of the atom and returns back to the atom. That is when higher harmonics are formed, right? So yes. Similarly, what is you explained to us in solids, what happens is it oscillates in the conduction band.
No, there are two kinds of mechanisms. One is that because what is happening that electron is promoted from conduction band to the valence band. So this is one kind of polarization, or let's say the current. This is the interband transitions, okay? And then the other kind of transition you have is your intraband, because your electron is following different kind of curvature in conduction band, as well as hole is also moving. So the total contribution is intraband plus interband.
So why do we have harmonics then? Shouldn't it be a continuous spectrum?
No, because every time you are, this is a very, very physics point of view. So the point is, you put a sample, you observe a discrete peaks. So let's ask a question from the 3-step model also. Forget about the solid for the point of view. Why do you not have a continuous spectrum in the case of gaseous system? Because every time electron is recombining.
It takes one cycle. So
no, it doesn't take one cycle. It can. So if you plot the trajectories, there's a finite probability at each time to recombine. That's why you do a Gabor transformation to see the peak. So it's not about, yes, every half cycle there's a prominent process, but at any time you have a probability, and the whole quantum mechanics is the probabilistic in nature. So the high harmonic generation is the only process, at least to best of my knowledge, which requires the wave nature as well as the quantum, the particle nature of light. Particle nature of light is required to explain the discreteness of your spectrum, because you can have only discrete quantization, that is the particle nature, omega 2, omega 3, omega, whereas the mechanism which is based on the 3-step model is generally based on the wave nature, because this is the oscillating wave. So it is let's say the interplay of both the processes. Generally, you have learned in your textbook that you probe the process and then only it will tell you whether light is behaving wave or like a particle. But in this particular case, if you want to look the frequency response, then it is a wave nature. But if you particle nature, if you look the continuous or the mechanism, which is a wave nature. And this is generally you don't see this. I mean, you don't read this kind of underlying things in this one. The same thing is happening here also.
Okay. So, and in graphene harmonics, you said 2 and 4, or 2nd and 4th harmonics because of this central spatiosymmetry of the graphene. But broken. In the broken centrosymmetry.
Yeah,
so, but in the
symmetry of the whole system, light plus material, that is the whole system.
Right, sir. But in the graph that you showed of the HHE spectrum of graphene, there were 1 and 3 as well.
Yeah, because linearly polarized light is not capable to break the symmetry.
Okay. So why is 1, 3 being generated and 2 and 4, like 1, 2, 3 and 4, all are being generated?
In which case, sorry?
In graphene, sir.
No, 3 is not generated because all the 3 harmonics are forbidden due to a detailed selection rule in omega 2 omega driven processes.
Okay,
this
sir.
We have seen in case of the gaseous atoms like atomic and molecular cases also in early 2015-16. Yeah.
Okay. If I have time, I have a follow-up question. So, how is it different from solids and nanoparticles?
I mean, okay, so people have attempted when it comes to the nanoparticles, these are also the solids, but the problem is that they do not have a well-defined crystal axis and all these things, so the results will be quite chaotic. What people started doing, they started tempering the sample and creating, so there's a 2017 paper by Paul Corkum in Science where they have tempered one, and they have seen how the things go. The problem with the nanoparticle is that you have to have a thin film kind of thing. So the periodicness of the crystal is not needed to generate the high harmonics in solid. So people have shown, I think there's a Nature Communication paper in quartz, 2017, if I remember, from the same David Reed's group, where they have clearly shown that indeed they can generate, whereas the quartz is like amorphous. Yeah. A glass, let's say they have taken the glass piece actually.
Okay. So Dr. Atanu Bhattacharya has a doubt. I guess he can switch on the mic and speak to you directly.
Yeah, Gopal, can you hear me?
Yes.
Yeah, good to hear this talk. It was very nice talk. Just one confusion. We can talk about it later, but there is a confusion. This photo emission will be acting at the same time when the high harmonic generation will be created from solid. Does photo emission have any effect in this?
No, I mean, okay, so the in solid, the photo emission is little bit different, because when you promote the electron to the conduction band, still it sees the potential. It's not free, unlike the gaseous system.
Right. So those free electron which you are creating due to photo emission, and this electron which is undergoing this independent transition, do they have any effect or anything?
No. People have not seen any kind of effect of this one. Because they try to maintain the intensity so low by increasing the wavelength, so that they do not touch the damage threshold, so that they can keep the same sample over and over and over, and they can keep doing the measurement, unlike the gas where every time you are seeing the new sample.
Mm-hmm. Okay, thanks, Gopal.
Thank you, sir. Thank you for that talk.
Okay. Thank you very much.
Yes, sir.
Okay, so now the session is over, right?
Yes, sir. So now the session is over. We'll break for lunch and we'll come back at 2 o'clock.
Okay.
Nanoscience and Technology. We have 30 PhD students and 25 MSc students and 3 postdoctoral fellows. Total number of employees in our department 20, in which 11 are faculty members. So research programs, already mentioned our chair. And these are my colleagues in the department, and I will be presenting some of the works done by my colleague Dr. Abdul Aziz and Dr. Sajan and Dr. Uni Krishnan, as well as one of my PhD student. She is presently working as a scientist in extreme light infrastructure facility at Romania. Of course, we have a lot of collaborations with several senior fellows in the country and outside the country. We have a long collaboration with the DFR, with Professor Deepak Mathur and Hema Ramanathan from Raman Research Institute, Professor Ananda Sundeep from NTU Singapore, and Dr. Neil Rastan from Last Check. And we have advisors, Professor Karta and Professor Nasser Matthew. Our all programs are funded by various funding agencies, DST, Office of the Principal Scientific Advisor, Government of India, and DAE. So I would like to make my acknowledgement in the very beginning itself. These are the people who are working in the department, and those people's part of their work is presenting here. So let us start the topic, submicron tailoring of diffractive optical elements and other structures using femtosecond lasers. So all optics people know when light interact with the material, several processes occurs. Emission, absorption, transmission, and these are the processes which every one of us knows. So refraction processes, we have a reflection, we have a diffraction. These are some of the devices or optical elements which are available, lenses, mirrors, and gratings, etc. So why diffractive element is chosen for this talk? A diffractive optical element is a microstructure pattern used to implement an optical function such as focusing, beam diffusion, beam splitting, beam profile modulation, etc. It segments a wavefront and redirects the fragments by using interference and phase control. Patterns are easily tailored by either modulating the thickness of the material by modifying the refractive index to manipulate the optical path lengths. Modulation of the incoming light can be achieved in amplitude or in phase. Amplitude modulation occurs when certain region tuned as obstacles to the beam and a specific placement in the design delivers a desirable pattern in the image plane. Similarly, phase modulation occurs when these obstacles are made transparent to the beam by altering their phase response to light. So here is a comparison of diffractive optics and other optics. The advantages of diffractive optics, we have multifocal device for focal spots for decreasing intensity. In other optics, we have unifocal device for a given wavelength. But the diffractive optics focusing efficiency is low. It is decided by the OPL in the optical element and the superposition of waves at the output. In refractive optics, 100% focusing efficiency. And in diffractive optics, you can see how the focusing of red and blue light happens. It is reversed in the refractive optics. And good pointing stability is guaranteed by diffractive optics. Pointing stability decided by the parameters of the optical element. Gives fuzzy, poor contrast images, give clear and good contrast images. Here, one of the important advantages, high damage threshold by absorption. Here, low damage threshold by absorption. Diffractive optic is compatible with all wavelengths. wavelength transmission limited to specific spectral range in refractive optics. Sharp fall-off for intensity distribution, which is favorable for micro machining, but in other optics, smooth gradient fall-off for intensity distribution. For ultra-fast, high-power pulses, the beam distortion can be minimized by using diffractive optics. Thickness of diffractive optics is lower, and the design is compact. This is one of the very important advantages for micro device fabrications. So why diffractive optics? Diffractive optics is a necessity due to development of ultrafast laser-based research and development. Very little work has been reported on DOEs. In view of the several advantages mentioned earlier, DOEs, there is a requirement of novel design and optimizations. Present DOEs, zone plates, photon sieves have less focusing efficiency. There is scope of improving the designs. Popular method of fabrication in photolithography. Popular method of fabrication is photolithography. Fabrication of DOE is using femtosecond laser direct writing is still in the development stage. That is the reason we are interested to work in this area. So I think most of us are very familiar with this picture. How the laser beam interact with the material. If it is a CW laser, what are the processes which happens? The long pulse laser, what happens? If you go for ultra short pulse, you can see no micro cracks, no melt, no ripples. We can do fine micro machining by using femtosecond lasers. So in other lasers, there is a lot of issues, doubles formations, crack formation, shock wave generation, etc. So this is the experimental setup in our laboratory for micro machining works, which I'm going to discuss here. We have a femtosecond oscillator, then a microscope with 3D translucent stages. You have the you can have the idea about the femtosecond pulse here, and this system is from Femtosource Scientific Excel 200, and all other optics related equipments are written here. So again, the inner part of the femtosecond oscillator, which we have been using for our activities. So let us do a few idea about micro machining. So micro machining can be done longitudinally or transversely depending on the sample scanning direction. So most of the time, the energy which we chosen for our micro machine is of the order of 100 nanojoule energy, because our system will give only 200 nanojoule energy. So you have the transparent material, your laser is focusing and it is always at rest. The moving part is the translation stage. You can program the translation stage and make damages to your material, useful damage to the material, so that you can have various structures in your sample. So these are some of the initial work that we have done, making channels written on PK7 glass for various scanning speeds. So one of the important parameters is scanning speed. You can see how the nature of the pattern changes when we increase the scanning speed. So this is always optimized whenever you select any sample for your study. So you can make splitters. You can see an X splitter. You can have a Y splitter, 1/3 splitter. You can write a Sagnac loop. Sagnac interference. Each one of you may be knowing about Sagnac loop. Now come to Sawn plate and photon sieve. Sawn plates, each one of us knows. Whoever is studying optics in high schools, we learned about Fresnel Sawn plate. So The Fresnel theory considers concentric zones as alternating opaque and transparent regions, with the zone width decreasing with increasing radius. There are two types of zone plates. One is amplitude zone plate, the other is phase zone plate. In amplitude zone plate, the opaque zones are completely blocked from contributing any light to the designed focal point by ensuring a metal or a non-transparent material lies on that region. Whereas in phase zone plate, all zones are seen as transparent, but the alternate zones are induced with the different refractive indices. How to do that? Here we use femtosecond lasers. Hence, the result in different phase shifts. This removes the requirement of the deposition of non-transparent material for certain zones. So this is a typical zone plate. You can see bright and dark regions. In photon sieves, we do something additional. When a planar zone plate is used as a lens, the spatial resolution is equal to the width of the thinnest zone. This is well known. Thus, the resolution is limited by the size of the finest structure that can be written by femtosecond direct writing. In our case, it was found 1 micrometer. It is decided by the laser system. It has, however, been shown in literature that with an appropriate distribution of large number of pinholes in the Fresnel zones in the dark region, it is possible to focus radiation to spot size smaller than the smallest pinhole. So this zone plate is known as photon sieves. So this is the same facility. So we have the transparent material. You are delivering the laser through the microscope objective, and you have a translation stages. Now we are fabricating amplitude zone plate. What you can see is the zone plate fabricated by our system. You can see the number of zones are increasing. Here we have indium thin films as well as tungsten thin film on BK7 glass. Similarly, you can make arrays of zone plates on similar materials. So you can see a 3x3 array of 13 zone each. Each array, each zone behave like a lens. You can see the light which is emanating from the lenses. You can see the fine focusing of these lenses. Now, phase zone plate. Earlier, I was mentioning about amplitude zone plates. How amplitude zone plates made? We have a thin film on a transparent glass plate. Be careful. The surface should be extremely flat. Otherwise, you won't get all the zones properly. So flatness is very important. And thin film, So we will coat always opaque materials on the top of it, mainly metals. Earlier case we have used, Now we have another types of zone plates. They are a particular type of zone plates where you can make zone plates with a different depth. So this is the kind of zone plates which we fabricated. You can see the zone plates. So similarly, you can have a cylindrical zone plates. You have a cylindrical lens over which you are writing structures like this. So here you can see the diffracted image. Let us have a photon sieve. It is not very easy to make photon sieves. So here we have photon sieves, and can see a full photon sieve. Actually, when we are making it, it is cracked, and the crack you can see. This is because of some of the problem related to the flatness of the surface. So you can see we are getting very sharp beam profile of photon C. We can also make gratings. These are the gratings which we fabricated. You can see the transmitted pattern from gratings. Now I am switching over to some other applications. The applications are tailoring the surfaces of different materials. I wanted to tailor the surface by creating roughness on the top of it. So you can use your femtosecond laser to make structures. You can have a grating type structures. You can have meshes, and you can grow cells on the top of it. So I will show you some interesting result. So while changing the roughness of the material, you will be able to change the hydrophobicity and hydrophilicity of the structures. You know, in order to test whether it is hydrophobic or hydrophilic, there is a parameter called so this angle. You know, this is called contact angle, and you can see here we have a surface. On the top of it, you have a liquid. This angle is the contact angle. Here, the angle is more than 90 degree, and here it is 90 degree. Here is less than 90 degrees, so more than 90 degree. Based on the contact angle, you have a high wettability, low wettability, and this is the wettability in between. So here, what we did, we have a pattern in the surface. A pure quartz flat surface has 90 degree wettability. You can see contact angle. You see how the water drops lying on it. It is water drop. And when we have patterned the surface and contact angle is 16 degree, the wettability is very high. So an increasing surface roughness due to laser patterning increases the wettability of an intrinsically hydrophilic surface. So this is a very standard practice for the tailoring of surfaces by using femtosecond lasers. So here we have done an experiment by growing the cell on the surface, and the cells are fibroblast cells. You can see these are unpatterned surface, and when we pattern the surface, you can see there are the alignment of cells along the pattern region. You can see alignment of cells. So why are interested on this kind of studies? The biologists are very, very keen on this kind of studies. You know, at least the people who are working on neuronal, they wanted to make scaffold for the growth of neurons. So this kind of studies are very important for neuroscientists. So this graph shows the alignment of cells. So this one is unaligned cells, and you can see aligned cells. When we have the temporal evolution of spatial alignment of cells on 50 micron and 100 micron spaced patterns on quartz cover slip, the alignment increases. See. So this is the surface pattern when you do micro machining on the surface of these quartz plate. Now we have done a simple experiment. The studies are just progressing. Whether the femtosecond laser can do something on crystallization. Yes, actually we have a saturated solution of sodium chloride and urea, and we exposed femtosecond laser for a few minutes and few seconds, and we waited for the crystallization time. See, this is the control, and the time taken for nucleation of crystallization is 15 minutes, and 8 minutes and 18 minutes for different samples. Under laser irradiation, we got the crystallization very fast. Instead of 15 minutes, 2 minutes. Instead of 8 minutes, we have 58 seconds. And in the case of urea, 18 minutes become 10 minutes. So you can fasten the crystallization process by using femtosecond lasers. Now, I'm going to discuss a little bit about, I don't know whether any spectroscopy is involved, the supercontinuum generation. This is a very interesting area for the nonlinear people. So we have done an experiment. This is an experiment in collaboration with the Tata Institute of Fundamental Research. They have been working in the area of white light generations using femtosecond lasers. And everybody knows ultra-short optical pulses passes through a nonlinear medium such as bulk fused silica, photonic crystals, fiber, and so on. They generate supercontinuum. Whether supercontinuum is generated when light passes through water, yes, people have observed supercontinuum generation or white light generation when femtosecond laser pulses passes through water. So the laser wavelength 820 nanometer with 45 femtosecond pulse width, repetition frequency 1 kilohertz, and the energy or power 8 terawatt per centimeter square. They found supercontinuum generation. My interest is because we work on various types of biological cells. We studied the supercontinuum generation in water in presence of macromolecules. Macromolecules of our interest are proteins. So this is the white light generation or supercontinuum generation we observed in water. This one is the red one is the white light generation we observed in water. We put a protein which is very, very common, which is available and present in saliva. We know saliva is a very, very rich clinical sample. It contains more than 500 proteins. And these are the proteins which already identified. And one of the major protein in human saliva is alpha amylase. It is doing a very important job of, for the digestion of food when we eat food. So this mixes with the alpha amylase helping in the digestion of the food. So we added, this is a very simple experiment for curiosity. When we do the white light generation experiment, we put a little bit of alpha amylase. We found this white light region disappeared or reduced. Why alpha amylase? We have tested with the amino acids. We couldn't find any change. We have done the experiment thoroughly by changing the concentration of alpha amylase, 20 micromolar, 40 micromolar, etc. And we found the reduction of the white light linearly. This is a study which we have done several years back, and we could not pursue this because of various reasons. And what we observed, if you are able to detect the level of concentration of saliva in our saliva is known to be a very, very important stress marker. So we have a very fast technique to detect the level of saliva in level of alpha amylase in saliva. So we can use this simple femtosecond experiment for testing the stress of human being, but the only problem is you need a femtosecond laser. Then there is another interest, whether this is hold good for some other proteins. Yes, there is another important protein that is pancreatin. We added, while doing the similar experiment, we added pancreatin. Pancreatin is not a one molecule, it's a mixture of including alpha amylase, some other enzymes. So you can see complete disappearance of the white light from the supercontinuum. So there's a lot of interest in this type of studies. So I think my presentation is very short because I agreed to give a talk on biophotonics. In the meantime, students asked for something, ultra-fast spectroscopy. I didn't do justice here to speak about ultra-fast spectroscopy. I intentionally selected the work which we have been doing here, that is micro-machining. So I'm concluding even before time. The femtosecond oscillator-based micro-machining of optical elements are realized and its performance has been tested. I was showing, different types of optical elements, including diffractive optical elements. The diffractive optical elements on plates and photons, these are fabricated using oscillators and femtosecond amplifiers respectively. Because of making certain plates, we need to have high energy laser for, we have used the laser system in the TFR. And femtosecond laser oscillator was exploited for the surface tailoring of material surface for biological applications. You saw how the surface can be tailored and change the hydrophobicity by making a controlled roughness on the surface. In femtosecond laser was successfully demonstrated for the faster crystallization of molecules. Efforts are progressing well to crystallize certain proteins which are difficult to crystallize using conventional methods. I have shown superconductor generation in water with the femtosecond laser. We also explored, and the presence of certain proteins role in supercontinuum was studied. It has been observed that alpha amylase has the capability to suppress the supercontinuum. You may ask, what is the mechanism for the suppression of the white light? So one of the important reason for the white light generation is multiphoton ionization. During the multiphoton ionization, electrons are generated, and these are all suppressed by the alpha amylase. Alpha amylase is known as a very, very important electron scavenger. So it suppresses the white light because of suppressing the generation of electrons generated during multiphoton ionization. Thank you for hearing me as such a short presentation. And now, if you have any questions, you can please.
Thank you, Professor Santosh, for such a wonderful talk. We do have a number of questions for you. Particularly, I wanted to ask you that initially you had mentioned that you're using diffractive optics because you can use it in a wide range. So it provides you a wide wavelength tunability. Because the optics which can be created from that can extend in a broad wavelength range.
Yes.
But sir, the material that you're using is BK7. And this is a routine problem that we come across, that this material absorbs below 200 nanometers. So especially when we are doing HHG experiments, we can actually use any of the optics because they'll all absorb the XUV which is generated. So how do you circumvent this problem using diffractive optics?
Yeah, this is a very, very interesting question and difficult to answer. We are actually optimizing the conditions. By optimizing the conditions, we make this kind of structures. This is a very interesting question. Yes.
Okay, sir. On to my next question. You had mentioned that the crystalline process in the presence of laser becomes faster.
Yeah.
So is there a particular reason or mechanism?
The main reason, I didn't mention the reason because the reason is, the femtosecond laser creates nucleation centers by making micro bubbles. So these micro bubbles act as the crystallization centers.
Okay. Okay.
Yeah, this is one of the explanation. This is not a complete explanation. This is one of the explanation. There are, of course, questions whether it is correct or not.
Okay, sir. And then towards the end, you had mentioned that alpha amylase suppresses multiphoton ionization. This is particularly interesting because at least we've not come across any macroscopic process which directly addresses the multiphoton process, because they're completely dependent upon the intensity of the laser that you throw in.
Absolutely.
So we were under the impression that if the intensity is high enough, this process is definitely going to happen. So if you could just comment on that.
Can you repeat the question?
Yes. So multiphoton ionization, generally the only factor which affects it is the intensity of the laser.
Yeah.
So if the intensity is very high, the probability of multiphoton ionization is going to increase. So what is this specific property of alpha amylase that rather disturbs this entire phenomena?
See, the only justification which we are claiming is this is a very, very, very well-known antioxidant and electron scavenger, radical scavenger. It can scavenge electrons, radicals, free radicals. This is the only property which we are able to suggest. Okay. Otherwise, it is a protein. It is an enzyme which is highly, unstable protein itself. It's an enzyme actually. This is the only justification which we can give. The very, very, very interesting question and difficult question to answer. What is the special property of alpha amylase? There are other proteins also behave in the similar way, not exactly like amylase. They bring down the supercontinuum. We observed.
Okay, sir. Sir, I have another question for you from chat, which says, what is the minimum grid size that can be obtained by femtosecond laser surface machining?
Oh, in our case, we have gone down to 2 microns only. Grid size, or you are talking about the channel size?
Yes, sir. You had actually shown a presentation in which there were grids which you had made, in which you were growing some biological samples. So I think that this question is regarding the minimum grid size that you can get.
This is 1 centimeter square.
Oh, okay.
Yeah, area.
Okay. And using micro machining, the minimum that you can obtain is of the order of microns.
Yeah.
Okay.
That is absolute. Yeah.
Okay. Sir, those were all the questions that I had for you. Thank you for such a wonderful session.
Thank you.
Yeah, now we'll be moving on to our next talk, which is a student
talk. I am on time or before time?
Sir, a little before time. That's okay, sir. I think Subit is here. Sir, just before you go, there's one more question for you, which has just come up. So I'm just going to quickly ask you. The same person has asked, can we obtain nano grids?
This so far we could not achieve. That is possible. It's possible. We observe nanostructures in our pattern surfaces, but not we are able to exactly make nanostructures.
Okay, sir. Thank you, sir.
Yeah.
Okay, so with this, we move on to our next talk of this session, which is a student talk presented by Subit Kumar. Subit is a doctoral student here at PRL and is working in the Photonic Sciences Lab with Dr. Gautam Kumar Samanta. He will be talking on frequency doubling characteristics of full Poincare beam. So over to you, Subit.
Okay, thank you, Pranav. Good evening, all. Today I'll be discussing some of our recent work on frequency doubling characteristics of a special kind of beam called the full Poincare beam. So this will be the brief outline of my today's talk. So when it comes to the motivation, so full Poincare beams are a special kind of structured beam which have a spatially varying polarization in its transverse plane. And not only that, it can contain all possible polarization. Theoretically, can contain all possible polarization in within it. So when you talk about the nonlinear frequency conversion of such kind of a beam, so it's often difficult because all nonlinear processes require a polarization dependent condition called phase matching. But since this kind of beam have a spatially varying polarization, the phase matching of each of the perfect phase matching of each of these polarization is often difficult. So in normal situation, if you try to do the nonlinear conversion of this kind of beam, so at the output you will end up with a scalar beam or a beam with a spatially uniform polarization. So the question we are trying to answer in this our current work is, can I do the second harmonic generation of this kind of a beam by preserving all its polarization properties? So this full Poincare beam have a lot of applications. Some of them I mentioned here. One is you can use this beam is a good candidate for making a light beam with a flat top intensity profile. And one more thing is there, so you can use these beams for trapping Rayleigh-Range particle. And it's also experimentally shown that this beam have a good stability in turbulence-induced scintillation. So before going to polarization Poincare much details, let me talk about how we can quantify a polarization. So polarization you can quantify using 4 parameter called Stokes parameter. So each of the Stokes parameter is represented here. So for a completely polarized beam, so this okay, this S0 Stokes parameter is basically represent the total intensity of your beam. And S1 is represent your how much horizontal or vertical your beam polarization is, and S2 is represent diagonal and anti-diagonal polarization characteristics, and S3 is basically will tell you how much circular your polarization is. So for a completely polarized beam, so this 4 parameter will satisfy a equation like this. So because of this, you can make a imaginary sphere in S1, S2, S3, a space in S1, S2, S3 Cartesian coordinate, and you can represent a sphere in it. So for a completely polarized, any completely polarized beam, so each of the polarization you can represent as a point in the surface of this sphere. So this sphere is called a Poincare sphere. So when you talk about the general light beams, some of most of our real life, real life situation, we will encounter light beams with a uniform polarization throughout the beam. So those kind of beams generally called a scalar beam. But there are other special kind of beams called vector beam, in which the polarization of light will vary throughout the beam cross section. So those in those kind of beam, at each point, along with the electric field magnitude, electric field oscillation direction also important. So because of that, it's called vector beam. So if you take some particular kind of a particular set of vector beam, so and if you map each of the polarization present in that particular beam, you can see that it will span throughout the Poincare sphere of Poincare sphere. So those kind of beams are generally called full Poincare beams. So one of the interesting characteristics of full Poincare beam is polarization singularity. So two of the important polarization singularities shown by the full Poincare beam I am discussing here is L-line singularity, in which you can see in the polarization structure, you can see a line, some lines with completely linear polarization. So other kind of polarization singularities are C-point singularities. So in which in the polarization structure, you can identify some of the circular polarization, and along with so in one case, if you consider the semi-major axis of your polarization ellipse, you can see in here in the circled path, in the marked part. So that semi-major axis following a hyperbolic path along 3 lines, and the 3 lines are showing like a star. So this kind of singularity points are called star singularity. And otherwise, there was another kind of C-point singularities are also there. So in this, along with a line tipped at a circular polarization, you can see other polarization ellipse will follow a parabolic path along with that line. So these kind of singularities are called Lemon singularities. So how we can make a full Poincaré beam? So full Poincaré beam you can make by using generating the non-separable superposition of a vector beam and a Gaussian beam. So once you combine this vector beam and Gaussian beam, you will at the output you will end up with different polarization, orthogonal polarization. So you at the output you will end up with a full Poincaré beam. So in experimentally for generating that, you can use various techniques. The technique we are using used here is an interferometric technique. We used a Mach-Zehnder interferometer for generating this full Poincaré beam here. So in my experiment setup, I used a halfway plate PBS combination for controlling. My light source is a disappare laser with a 810 nanometer peak wavelength, spectral wavelength, and around 17 femtosecond pulse speed. So then I used a halfway plate PBS combination for controlling my intensity of my beam. So then this second halfway plate is used for controlling the relative intensity between the 2 arms of my Mach-Zehnder interferometer. So then the vertical arm I place of my interferometer, I used a SPP, and which will generate a VL state, which is vertex beam profile at vertical polarization. So in other arm, I used a lens combination for expanding my beam, and I generated H0 state. So at the output, at the output, these 2 beam will combine and it will make a non-separable state of VL plus H0. So at the output, I'll get a full Poincaré beam. But since I am using a femtosecond laser, the temporal overlap between these 2 states are essential. Then only I'll get a full Poincaré beam at the output. So I used a delay stage in the shorter arm of my interferometer. Then later on, using a quarter wave plate and a polarizer, I done a reduced. I recorded 4 intensity profile with a different orientation of this quarter wave plate and polarizer. I using a computational program, I done a reduced polarimetry and I extracted the different Stokes parameter, and from that I find out the polarization structure of my beam. So then later using a dual BIBO crystal and I generated the second harmonic of this full Poincaré beam. So how that was happen I will discuss in my following slide. So L3 lens is used for focusing the full Poincaré beam into the middle of my dual BIBO crystal, and L4 is used for again collimating my second harmonic beam. Then a separator is a harmonic separator is used for separating my 810 nanometer pump beam and 405 nanometer SSG beam. So then similar to pump beam, I used a quarter wave plate polarizer combination for doing the reduced Stokes parametry of my second harmonic beam, and I calculated all Stokes parameters and polarization structure of my SSG beam. So how this dual BIBO crystal scheme is working? So this dual BIBO crystal is consists of a 2 normal BIBO crystal face matched orthogonally each other. The first crystal is face matched for a vertically polarized light, and the second crystal is face matched for a horizontally polarized light. So when a vertically polarized vertex beam is coming through to this BIBO crystal, the first crystal will generate second harmonic generation, and I'll get a 405 nanometer second harmonic from that crystal. So similarly, the vertical polarization will become horizontal polarization because of I'm here doing type 1 phase matching. So at the output, I'll get a horizontally polarized vortex beam with the vertex order will double because of the conservation of orbital angular momentum during second harmonic processes. So similarly, in the case of Gaussian beam, also similar situation will happen, but the conversion will only happen in second crystal, because this only the second crystal is phase matched for horizontal polarization. So similarly, the polarization also will flip in after second harmonic generation. So altogether, for a fully Poincare beam, so at the output, I'll get an efficient generation of second harmonic, a full Poincare beam at second harmonic frequency range or a wavelength range. So this is the experimental result we got for a first order full Poincare beam. So the you can see that I'm getting a one L line and one lemon and one star structure for my pump beam of H0 V1 state, which is corresponding to a first order full Poincare beam. When it comes to the second harmonic generation of that pump beam, the lemon and stars, number of lemon, star, and L line singularities was doubled. So this is due to the reason that so during this second harmonic generation, our vertex charge will double because of the conservation of orbital angular momentum. So because of that, the phase structure of my L state, I mean L will become 2L. So because of that, we are getting this doubling of lemon, star, and L line singularities. Similarly, we done for second order full Poincare beam, and we are getting the similar kind of result. All the singularity points are singularities are doubling at the second harmonic generation, and we done the theoretical simulation of each of this situation. So our experimental result have a great agreement with our theoretical simulation. So we done this similar experiment up to third order full Poincare beam. In all cases, it's in the third order, when it comes to third order singularity, I mean third order full Poincare beam at the SSG, we are getting sixth order full Poincare beam at 405. So it's also an efficient method to generate a higher order, very high order full Poincare beam in different wavelengths. So then for checking the optimum, I mean different for characterizing this as a second harmonic generation, we done how the order of our full order of our Poincare beam will affect our SSG efficiency. So we find that the first order, I mean when it go to a higher order, so the efficiency, second harmonic efficiency is drastically reducing, I mean decreasing. So then we done the for finding out the optimum focusing condition for SSG. So we done a different focusing condition. So we find out that at 50 mm focusing condition, we are getting a maximum SSG efficiency at the output. Then we done the SSG second I mean power scaling of our second harmonic full Poincare beam as SSG. So we find that the SSG efficiency is linearly dependent upon our fundamental power, and the SSG power is quadratically dependent on our fundamental power. As it is similar to what in the case of a normal second harmonic process. And for confirming that this quadratic dependence on second harmonic power, we plotted pump power with square of pump power with the second harmonic power. So it is showing a good agreement. It is showing a good linear fit. So it is a confirmation, and we got a approximately 16.4 watt of milliwatt of power out of 836 milliwatt of pump power for first order full Poincare beam. So in the conclusion, we have experimentally realized the second harmonic generation of a full Poincare beam by keeping all its polarization properties, and the C point L line and C-point L-line singularities was doubled during second harmonic generation that we observed. It is due to the doubling of vertex charge during second harmonic generation process. And we also done all the second power scaling characteristics order dependence on second harmonic generation of this all SHG characteristics of full Poincare beam frequency doubling process. So that is all about my presentation. Thank you. And now I can attend some questions.
Thank you, Sumit, for such a nice talk. I do have 2 questions which have popped up in the webinar chat. I'll take that up for you. So first question is by Anandya. He's asking, you can directly generate the FP beam, which is the Poincare beam, after SHG2. What is the advantage of using the full Poincare beam as a pump in that case?
So that is our objective. So it is a direct conversion of a full Poincare beam, a direct frequency conversion of a full Poincare beam. So you can generate after SHG also, but for that you need that corresponding optics for that second harmonic wavelength. In case if you don't have, so this kind of scheme is very advantageous.
Okay, Sumit. So Sumit, the next question is, how do you increase the efficiency of the SHG? Can you comment on that?
Okay, you can do one thing. You can if you look on our power scaling graph, you can see that it's not yet saturated. So the only limitation here we are facing is the pump power. So our laser will only deliver maximum pump power of 836 milliwatt. So that's why my efficiency was limited. That if you have a high pump power, you can increase the SHG efficiency similar.
Okay, so there is no intrinsic cutoff or something of that sort.
No, according to our experimental observation, till now, no.
Okay. That's it, Sumit. Those were all the questions I had for you. Thank you so much. Okay, so with this, we move on to the last talk of this session. We are actually a bit ahead on our schedule, but that is rare and it's a good thing. So this next talk is an invited talk which will be presented by Dr. Sai Santosh Kumar Ravi. Dr. Sai Santosh is an associate professor of Department of Physics at IIT Hyderabad. His research interests include ultrafast time-resolved spectroscopy, ultrafast nonlinear optics, organic solar cell devices, and ceramic photonics. Today, we are all excited for his talk on ultrafast charge transfer investigations in organic photovoltaic systems. Over to you, sir.
Good afternoon. First of all, at the outset, I would like to thank the organizers for inviting me for this wonderful students conference. And I should also congratulate the organizing team, the students, to be so brave and come up with such a beautiful organization. And I've been sitting and listening to all the talks from the morning, so everything is smooth. Thank you for your efforts. Well, to begin with, today I would like to talk on ultra-fast charge transfer in organic photovoltaics. To begin, assuming that this audience is the most varied audience, I would start with the basic physics behind various organic photovoltaic devices. I would discuss a bit on how femtosecond transient absorption spectroscopy can be used to follow charge transfer process. And then I present a couple of our latest results from our lab here. I think I have a lot of time, so I will go slow. Okay, in case I'm short of my time, please inform me. Okay.
Sure, sir. We'll let you know.
Yeah, I'll be a bit slow. Yeah. Well, for a PV technology, for a photovoltaic technology, to satisfy the sustainable criteria, it should be economical, made from earth abundant resources, along with lowest environmental impact. There is a reason why this statement is made. If you look at the most common solar cell available in the market, it is that of the silicon solar cell. The silicon technology is no doubt the most mature technology, but then the way the manufacturing process, it is high temperature, high vacuum, and so a lot of expensive byproducts. Along with it, you have a lot of harmful chemical byproducts. Okay, so first thing is you have expensive manufacturing process. Second thing, the kind of chemicals you use to convert the sand, which you see around, silicon dioxide sand, into silicon is expensive. And finally, the kind of byproducts that come out of this entire manufacturing cleaning process are also much more dangerous. And so there is a study which has been progressing since last 15 years to understand or to present or to quantify the amount of green impact or the environmental carbon footprint the silicon solar cell manufacturing units are doing. It is alarming. And so researchers as well as industry have gone ahead and started looking for alternate technology. Of course, it would take a lot of years to really replace silicon. I'm not sure whether we will be able to replace silicon technology, but then there is a strong effort to make the photovoltaic technology more green in terms of looking for alternative ways to generate or harvest light to energy. Okay, so in this context, the concept of organic solar cells put the bill. Okay, why? Because organic molecule-based solar cell-based energy devices have gained a lot of interest as an attractive alternative owing to the possibility of low-cost fabrication procedure, ability to print them on flexible substrates, engineering at molecular level to tune their band gap and charge transfer characteristics and a potentially less hostile environmental behavior. So this is the main aspects about OPV, organic photovoltaics. You can, in principle, use the materials of your choice which are green or environmentally safe. These devices include technologies like organic or polymer solar cells, dye-sensitized solar cells, hybrid solar cells. Nowadays, these hybrid solar cells have become much more efficient with the introduction of perovskite solar cells. And also there has been some work on quantum-dot solar cells. Eventually, the idea here is to make solar energy conversion devices more environment friendly so that we can have a sustainable way to grow forward. Okay, now, if you look at the best research cell efficiency, this has been published by NREL, National Renewable Energy Laboratories. Every 6 months, you have a update. The trend in photovoltaics, organic photovoltaics, have begun very late. If you look at the first solar cell, it's somewhere in 1970s. Now, the organic solar cell started picking up from 1990, and the majority of the research is taken up only the last 10 years or so. Only the last 10 years or so. Okay. Now, it would be worthwhile to look at this particular yellow dot, which started sometime around 2013. Okay. So this belongs to the perovskite solar cells, and the first perovskite solar cell which came as a science paper, reported as a science paper, started with an efficiency of 12%, which is way beyond where all other technologies have begun. And now this has steadily grown towards the 25.2%, which is more or less similar to what one can get from single junction silicon solar cells. So in a way, organic solar cells are actually competing with inorganic. However, there are a lot of issues. This talk is not about organic solar cells, so I will not go into that. However, the point here I want to make it is that this technology is there for future, and it's important that one contributes towards the success of this technology. Now, something very specific about this organic photovoltaics is the excitonic nature of the material system, and therefore they're called the excitonic solar cells. Now, what is an exciton? If you look at the condensed matter physics course from our BSc or MSc, we come up across two excitons. One is the van der Waals exciton, other is the Frankel exciton. And inorganic semiconductors are known to exhibit the van der Waals exciton behavior. So the exciton binding energy is very small. It is of the order of kT, or the thermal energy which is around is sufficient to break the exciton. Therefore, a dissociation by charge field upon a simple p-n junction, the kind of built-in potential one can generate across the p-n junction in a silicon solar cell is sufficient to dissociate the binding exciton, and the charges can go to their respective electrodes. Just to define what is an exciton, it is a bound electron hole pair. Okay. Now, this is something for the inorganic semiconductors. In the case of organic semiconductors, the situation changes. In organic semiconductor, it is Frenkel exciton, and this Frenkel exciton is known to have very high exciton binding energy. Okay, the point is simple. The exciton in inorganic system is allowed to delocalize over a larger region. Okay, and so the distance between the electron and hole can be long, resulting in the Coulomb interaction to be small. Whereas the organic system typically is more disordered in nature, and when you excite this organic system, the electron hole pair are localized in the same spot as you see here. Compared to this is local, more delocalized, this is localized, because of which the distance between them is small. Resultingly, the Coulomb interaction is very strong. In fact, this Coulomb interaction is way beyond the thermal instabilities one can come across, and so it is virtually impossible to dissociate this electron hole pair by itself. And so it requires the so-called donor-acceptor type of structure if you want to employ an organic semiconductor for solar cell application. So what is the basic idea of solar cell? You have light absorbed by a material system. You have the electron hole pair form, or this exciton form, and this electron hole pair should be somehow dissociated into individual charges so that there is a current which is flowing into the circuit. Okay, this is much easier for the inorganic semiconductor system. However, this for the organic semiconductor system, it is not so trivial. And that's where the point of the donor-X interface comes into picture, and the point of electron injection or the charge injection starts coming into picture. Okay, because you need to really find a way to transfer the charge from a material system which can get excited and donate the electron into a material system which can accept the electron and transport the electron which is donated to it, okay, which it accepts. So this is the idea of this donor-acceptor interface, donor-acceptor system, and we have lot of different types of solar cells. The first one being the dye-sensitive solar cell, and the interested guy people can go back and look at the review, this 2010 review. It is a big 90-page review. You can have a look at it and try to understand the basics of this technology. Briefly, I would just explain here. A DSSC consists of three components: a dye, which has the job of harvesting the light, okay, and this dye is adsorbed onto a mesoporous titanium. Mesoporous is like a sponge, okay. You see, it's a lot of titanium oxide dioxide semiconductor system, which is more spongy and we have a lot of porous. It's very porous. Okay, so the point is that here the dye is sensitized over the titanium. The dye absorbs the light, gets excited, injects the electron into the titanium. Titanium being an inorganic system, inorganic semiconductor material, would have a faster electron transport, and this electron which is injected into the titanium gets quickly transported to the electrode which is here. Now, the dye molecule which has injected this electron is now oxidized. It doesn't have an electron, so it becomes a positive charge. Like dye becomes a dye plus cation. Now, how does we renew this dye? This dye would look for an electron from the surroundings in order to regenerate itself for the next round of absorption and injection. Because this regeneration of the cation is done by the surrounding electron-rich electrolyte. Okay, this is the iodide redox couple. It's called 3I minus I3 minus redox couple, and this liquid electrolyte has excess of electrons, which typically is used to regenerate this dye. So it happens automatically. Okay, and the point about mesoporosity is that the area of the surface area of this titanium is more with higher mesoporosity, and so when you have a monolayer of the dye absorbing onto the entire surface area, you have a lot of dye molecules, even though it is a monolayer of the dye, available for absorption. So you have a lot of absorption taking place, and this liquid electrolyte, by virtue of it being in liquid state, can easily go through these pores and regenerate the dye in the mesoporous titanium. Okay, so this is the point about the TiO2 DSSC. And the important aspect of electron injection comes into this picture here, where the dye can only inject into the titanium when the LUMO of the dye, or the lowest unoccupied molecular orbital of the dye, energy of the dye is higher than the conduction band of the titanium. Okay, so as long as the conduction band of the titanium or any other inorganic system which is accepting is lower than the LUMO level of the dye, you can invoke the Marcus transfer. I'm sure in the morning, Professor Atanu Bhattacharya has touched upon that aspect. You do have the so-called electron injection because they are next to each other and they can inject. Okay, so this is the energetics which you see here. The dye injects into the titanium. Okay, injects into the titanium. This injection can be anywhere between few hundreds of femtoseconds to few hundreds of picoseconds. This is the time scale we have. Okay, and then this guy is always competing with the natural decay of the dye, which is typical in the nanosecond time scales. So the arrows which you see here towards the dye is the recombination mechanism, and the blue arrows which you see is the actual mechanism which you want for the solar cell to work. Okay, and so the timing is clear. You have 100 femtosecond to 100 picoseconds time scale for injection, and then the regeneration of the dye from the electrolyte typically takes place in 1 microsecond, and the entire process of charge transport, injection to transport, happens within the millisecond to second time scale. So overall, each of these processes happen at various time scales, and using spectroscopy, one can really follow it up. Yeah. Next comes the concept of polymer solar cells. It's a bulk heterojunction solar cell. In other words, this is a bicontinuous network of donor-acceptor organic blend. Typically, a donor would be a semiconducting polymer. Now, there are a lot of research on semiconducting organic molecules, okay, small molecules. Similarly, acceptor typically was used to be a PCBM or fullerene-based molecules. Now there are a lot of non-fullerene acceptors. Here I'm just giving you a typical example of PTHT PCBM, acceptor and donor-acceptor blend. And this is how the blend looks like. As you see here, you have the domains of acceptor and domains of the donor mixed together, such that there is a continuous chain of donor-acceptor meeting the respective electrodes. So what is the mechanism? You have the light absorbing by the donor, which is the first part. It absorbs the light, gets excited. So there's an exciton generation which happens in the donor system. Once the exciton is generated, it doesn't know how to dissociate because the exciton binding energy is high. And so what this does is it just randomly moves around that domain, okay, and slowly diffuses to the donor-acceptor interface. At the donor-acceptor interface, you have the extra energy to overcome the branding energy, and so the dissociation takes place. Electron is injected into the acceptor, and the hole or the positive charge is in the donor, and they find their own way to go and reach the respective electrodes. So this is the idea of the donor-acceptor interface, the bulk heterojunction solar cell. Again, the injection can happen only when the LUMO of the donor is above the LUMO of the acceptor. This is the LUMO of the donor, this is the LUMO of the acceptor, and this gradient is required. Again, the timing of this injection is again typically between 100 femtoseconds to few picoseconds. Okay. Finally, the concept of hybrid solar cells. Initially, it was thought that we'll replace the dye with a polymer, okay, and then maintain the nanostructure. As you see here, I will not go why it is done because it got to do with the problems associated with the liquid director DSSC and bulk heterojunction solar cells. So this idea was thought of to be the best of the two worlds, where the organic system will inject the electron, okay, and transport the hole. Okay, this is how it is thought to be. At the interface, you have the polymer absorbing the light, forming the exciton, and injecting into the titanium. The hole which is there in the polymer would get slowly transported to the eventual electrode. So this is the idea of the hybrid solar cells. Again, there are still some problems with it, and this semiconductor polymer has been replaced with the present perovskites. Okay, perovskite is another material system which has shown excellent solar cell efficiencies. It's one of the wonder material. Okay. So what is common about all these things? If you look at it carefully, the heart of the entire organic solar cell devices lie in the donor acceptor interface. Okay. If there is no donor acceptor, you do not have donor acceptor interface. You cannot have the charge transport, charge injection. Unless there is a charge injection, the exciton would not dissociate, and therefore the crucial mechanism is the exciton's interface, and the crucial mechanism is the exciton dissociation, which is typically less than 300 femtoseconds. This is what you want, and the charge transport overcoming the recombination. So all these things, as you see here, happens at various time scales, and so the time resolved absorption spectroscopy in with supporting time resolved photoresistance spectroscopy can give a complete information about the life till the life of the birth of the charges till it reaches the interface or it dies somewhere in the track. So one can actually track the entire lifetime of the charge which is generated in an organic solar cell by using this various transient spectroscopy techniques. Right. So now I would briefly explain you what is the spectroscopy I'm talking about. Pardon me if there are students who already know this. This is more like an introduction to all the guys who are not familiar with femtosecond transient absorption spectroscopy. Okay, the idea about pump probe is this: the pump generates a non-equilibrium state in the sample. The probe measures its evolution at different times. This is the basic idea of the pump probe. Okay, so you have the sample. The pump pumps the sample. Sample gets excited because the choice of the pump is such that the sample is absorbing the pump and gets excited. The probe would interrogate the transmission of the probe, which is typically after a certain time delay, tau, indicates the actual pump-induced changes in the sample. Okay, so if the pump is given as IPU of T and probe is IPU PR minus tau, the impulse response of the medium is A of T. Okay, the pump-induced variation of the probe energy delta PR tau is equal to the product of the impulse response of the medium to the convolution of the system response with cross correlation of pump and probe pulses. Okay, this is the cross correlation of the pump and probe, and the entire delta EPR is a convolution of this system response with the cross correlation of the pump and probe. Okay, and therefore all the dynamic processes within the cross correlation of the time gets averaged out. Resultantly, or consequently, it is important that if you want to look at, it is important that the pulse duration, both pump and probe, should be as short as possible in order to follow the dynamics that happens in ultra-fast time scales, ultra-short time scales. Okay, now the science, the physics remains the same. You can use Beer-Lambert's law. The absorption is what you're going to measure. Okay, through the transmission, the absorption is sigma and d. Sigma is the absorption cross section and is the number of the population of the material which is absorbing, and d is the thickness of the material. You can use it, and the change in the absorption, change in the transmission, delta T by T, or minus delta A. A is absorption, T is the transmission, is given by this expression, where the summation is over the various population species. Okay, delta and I of tau and delta and j of tau, population of the ground state and the state I and state j, and the time, and the sigma ij is typically the probe frequency, which is so the point is that the sigma ij represents the absorption of all the photo-induced species that is possible, and therefore the pump probe signal contains a intrinsic dependence on the probe frequency, where at each frequency the signal can be result of the overlap of several transitions, each weighed with its cross section. Okay, so this is a very, very crucial point. In fact, we have written a book chapter on this direction. You can have a look at it once you go back, or you can ask me, I can send you the soft copy. Okay, now in the context of organic molecules, what I mean is this: you have a material system where a singlet S0 as a ground state, S1 as the first excited state, and if the material has a certain absorption property and the luminescence property. When we excite with the pump, with the pump maxima, pump is chosen such that it matches with the ground state absorption maxima. So when we pump it, most of the population is transferred from the S0 to S1 state. Now we come with a broadband probe of a certain time, tau. Okay, if we come with a broadband form of a certain time tau, now what happens in this case? The portion of the spectra, broadband probe spectra, which overlaps with the absorption, doesn't see any population in the ground state, and so it gets transmitted without getting absorbed. Because we are measuring delta T by T, which is the T pump on minus T pump off, or the transmission of the probe with respect when the pump is on minus the transmission of the probe when the pump is off. This transmission of the probe when the pump is off would have some absorption. Now in the presence of pump, this absorption is not there. There is nothing to absorb. So the delta T becomes positive. Resultantly, we have the pump probe signal delta T by T as a positive signal. Now, you can also have a part of the broadband probe which overlaps with the luminescence, of the molecule. And so that would result in the so-called stimulated emission. Okay. And this stimulated emission adds to the number of photons. And so the detector will see an increased number of photons. And that's why you do have a positive signal, which is called as the stimulated emission. Finally, the excited state itself would have an absorption. If the idea of the ground state absorption is that you come with a white light and you excite a material system. So all the molecules, the absorption property of the molecules, which you actually interrogate with steady state absorption spectroscopy, is how this particular ground state is absorbing. Because there is no population excited state, your ground state absorption or the steady state absorption spectroscopy cannot give you any information about the excited state. Here we are inducing a population in the excited state. We are inducing the population in the excited state. Now we are allowing the white light to actually interrogate the excited state. And so the part of the probe spectrum region which coincides with the absorption of the excited state would have a loss in the transmission, which would result in the delta T by T to be a negative signal. And this is what we call as the photo-induced absorption signal. Now this, we are talking in terms of delta T by T. If you look at the way I have explained, this would be minus of delta A. So if you're looking at an experiment where the y-axis is delta A, the breach would be, the signals will be inverted, the signs will be inverted. The positive peak would be a photo-induced absorption, and the negative bands would be ground state breach and the stimulated emission. So this is the idea of the delta A. Now, importantly, from the point of view of your organic molecules, these are the various photoexcited species that you can have. You can have the absorption. It's called GSA, or the ground state absorption. This is the absorption of excited state. So it is called photo-induced absorption, and this absorption is happening from the first excited state to a higher excited state. Okay, this is the point. You can also have the situation where there is an intersystem crossing and a singlet population may go into the triplet manifold. And so one can also look at the photo-induced absorption in the triplet absorption band. Finally, as we will be discussing now, there is a possibility of charge transfer. When there is a charge transfer happening, this molecule would lose its energy, would lose its electron, and becomes a positive charge. So then the charge band, or the absorption of the cation of the material of the molecule, starts showing up in your pump probe data. And that's how you can study the entire excited state evolution of your material, of the organic molecule system. This example I'm giving in terms of, in context of organic molecules, you can take any material system, any inorganic material system which absorbs, and you can actually look at the various photoexcited species. Okay. Now, what are the experimental requirements? First is the spectral coverage. UV to far air, the higher the spectral coverage, the more is the spectra of the photoexcited species one can actually look at it. So what we need is the generation of new frequencies. Next is extreme time resolution. Why? Because as I mentioned in the previous slide, the shorter the correlation time, cross correlation time, the shorter is the dynamics which we can actually observe. So for this, what we need is the methods of pulse compression. Then comes the high sensitivity. Why we need? Because we need to really measure good signal to noise ratio. In order to see minute changes in the absorption upon pump absorption. Okay, so I'm sorry. The idea here is that you will get very low noise, low signal strength, and one need to really find a way to improve the signal to noise ratio. So that's where the high sensitivity comes into picture. And in particular to organic solar cell system, we cannot really have high pump fluence. The reason is simple. If you want to mimic the kind of light we receive from the sun, we need to really use such low pump fluence, so that whatever we see as an excited state evolution is similar to what happens when the solar light is absorbed by the materials. And finally, there is a requirement of significant sample absorption pump wavelength, even though it is pretty trivial and everyone starts using a sample with the optical density of 0.2 to 0.5. Okay, it is not such a trivial thing to do an experiment with an optical density less than that. And so we have come up with a new technique called TRAM, okay, transient absorption by multiple reflections. Okay, this paper, it's a 2013 paper. You can have a look at it. Something very, very close to the group which PRL is doing, kind of work PRL is doing. You guys are very good you're experts in doing optical parametric amplification, superconductor generation, pulse shortening, pulse shaping techniques. So all those things really form the core of the experimental requirements for doing a very good ultrafast compound spectroscopy. Now, why we need such short pulses? This is the example which I thought I should discuss with you briefly. So, using this femtosecond pump probe with sub 10 25th time resolution, it was possible to really study the primary photo events that happen that allows us to see. Okay, so there is this so-called conical intersection dynamics of primary photoisomerization events in vision, and this photoisomerization happens in the rhodopsin molecules, which form a part of our retina. Okay, the cones, the retinal cones. Okay, so when the light is absorbed by our retina, how the retinal molecules is responding to the light has been proved using this using the pump probe spectroscopy with sub 20 femtosecond pulse. It's a Nature paper. So our group, we have contributed towards the exciton fission dynamics. In fact, polycrystalline pentacene shows a singlet fission of 80 femtosecond. This is the fastest. Just for those who don't understand this, you have a singlet going into triplet, and this formation of the triplet happens via the so-called intersystem crossing. The intersystem crossing is typically few hundreds of picoseconds to few nanoseconds. The singlet fission is a concept where the triplets form instantaneously, almost instantaneously upon absorption. So in the case of pentacene, this happens within first 80 picoseconds. Also, we have used the concept of we have followed the energy transfer dynamics using a sub 10 to 50-second pulses to follow the ultra-fast energy transfer of 50 femtosecond for this dyed-out polymer solar cells. It's again an old paper. You can have a look at it later. Now, what are the various photophysical models which work for pump probe data? Why I'm specifying this idea is that now students can take data. Okay, now how do you actually analyze the data? The way to do is to actually have an idea of what are the various photophysical processes that are possible once the material system is excited. So you have the intersystem crossing. First is the internal conversion from a higher singlet to the first singlet. Then you have the vibrational cooling, VC, from the hot singlet to the singlet manifold, from hot singlet to singlet S1 to a lower singlet S1. And then you have the intersystem crossing where the population is transferred from singlet to the triplet manifold. Then you have fluorescence, which is from the singlet to singlet de-excitation. You have phosphorescence from, have everything written. You have phosphorescence from triplet to singlet timescale, and you have the triplet absorption. So all these things are possible, and this is the Jablonski diagram for optically excited molecules. Okay. The point is how you actually use this model to fit and interpret your data. The rule of thumb is this: one should not introduce fitting parameters without need and keep the molecule model as simple as possible. Fitting in material science is an art with some connection to statistics. However, mathematics is not at the heart of it. Because of this, the danger of introducing too many parameters exists, and this jeopardizes any interpretation. As someone says, if you give me 5 points, I can fit with any polymer, any parameter, any what you call. I can use any polynomial to fit this 5 points. Now, any polymer will not give me the true reflection of the photophysical model. Okay, and so the principle here is to make sure that you understand the phenomena with one experiment, use this idea, and start using the minimum number of fitting parameters. Because the less the fitting parameter, the more would be the idea of the physical mechanism which is happening. Okay, so typically this is the this is the pump data one sees. The two-dimensional pump of data. You have this y-axis, this axis which talks about the intensity of the measurement. You have the wavelength and the time scale. It's a two-dimensional plot. Okay. Typically in this experiment, if you see that the row represents the kinetic decay at different wavelengths. Okay, and the column would represent temporal evolution of spectra. Right. If you take slices of each, you have the spectra as well as the kinetics and the spectra. Now, how do you fit? Our group has been using Glotron. It's a graphical user interface for art by Amsterdam group people. Amsterdam group to actually fit this experimental data. There are a lot of other mechanisms, other fitting softwares available. This is a free software, so we thought we will use it and try to understand how it goes. Okay, the way to do is, it's not just related to Glotron, but if you can use any photophysical modeling softwares, you can develop your own model. Okay, the point is this: you perform experiment, you get this two-dimensional spectra, okay, which you call as time result data. If it is a single wavelength, one cannot really do much analysis. You can just fit it with exponential, but that would not give an understanding of what is happening in the material system. The reason is simple. As you see here, an organic molecular system has a rich excited state dynamic, photoexcited species, and so one cannot really follow with a single or two kinetic analysis. Okay, and so we really don't use that. We try to use the so-called global analysis, where you try to fit the entire 2D map you get, okay, an entire spectral data at once. How you do it? Okay, you first do the parametric estimation, which means you do the so-called single value decomposition, so that you get the minimum number of eigenvectors, which are the basis vectors which we talk about it. And then from these basis vectors, you can use the linear combination of these basic vectors to actually develop the entire 2D matrix. Right? This is the idea of a single value decomposition. Now, how do you actually make that thing? That's where the kinetic model and known parameters comes to picture. Use the connectivity scheme, use the initial times constants, use the quantum field, anisotropy, instrument response. All these things are required to actually have a kinetic model to explain your linear combination, how you want to do the linear combination. And that's how you end up doing the so-called target analysis. And this is a iterative fit, and you keep going up and down till you come up with the least chi-square fitting. Okay, and so that's how you get the final fit and rate constant. So all these things is pretty common for every comprobe analyzing tool. Here, in our lab, we use Glotron. I would say you can also write your own program to develop your own software for analyzing this. However, you have to follow whatever I just mentioned. Just to give an example here, I explain a bilinear model related to the component process. You have a two-dimensional spectra, okay, wavelength and time, and these numbers are the intensity counts, what you have. Now, this guy can be represented as 3 row vectors and 3 column vectors, and this is the singular value decomposition where you get the basis set, and you can do global analysis in order to get the right coefficients so that they add up together to get the complete, to generate the entire 2D spectra which you see here. Okay, so I'm sure I'm confusing more with, if I will confuse you more if I give more technical information. Keep this information with you, and when you're actually using, start looking at what this means. So this is called the decay associated spectra. This is called evolution associated spectra, and each of them would mean something. Please go back and have a look at it. Right. Now I have about 20 minutes to finish my talk. I would quickly go through our latest results. The first one being the new Fuchsin molecule-based molecule solar cells and antacid-based sensitive molecules. Here we use the same story what I just explained. I just give you more detailed information of how we pick up each molecule to study. Okay, now this new Fuchsin is a very interesting molecule. It is the kind of dye you see in your Holi or a lot of places. It is this magenta dye. It is very, very common in India, and it can buy it off shelf in any supermarket. Okay, so this dye, we wanted to use it because it is very cheap to make solar cells. Okay, now the point about using any dye is to understand the extension quantum properties. And so we went about first understanding the spectroscopy aspect of this molecule. We began with the steady state absorption and steady state luminescence spectroscopy spectra. We know what it is, where it is absorbing. So this is absorbing in the 400 to 600 region. Okay, and then the emission is somewhere in the 600 to 800 region. This is the molecule, and the time dependent DFT, PD-DFT calculation shows that upon excitation, this molecule really twists. Okay, it twists in one of the angles, as you see here. This is the ground state configuration, and here when it's excited, it nicely twists with respect to one. And so this twisting is supposed to be very interesting from the ultrafast community, because this kind of twisting would lead to the so-called collision intersection dynamics. Okay, and then we went about looking at what is the HOMO-LUMO level, and we find that the LUMO is about minus 3.46, which is higher than the conduction band of TiO2, and so this molecule can be indeed used for solar cell application, so dye sensitive solar cell application, right? So first thing is we did is a detailed analysis of the palm probe. We took solution of the molecule and thin film of the molecule. Okay, then we started fitting. First thing is we realized that the solution data is decaying within the first 20 picoseconds. I hope you're able to see this. Whereas the film can survive more than 500 picoseconds. Okay, even after 400 picoseconds, it really doesn't come down. Whereas here in the solution, this is very first within 20 picoseconds, you don't see any data. Okay, and so we started looking at what is the best photophysical model. This is how we find it. We excited 500, so that would be the, as per the DFT calculations in the previous slide, this is the absorption of the singlet to S0 to S1 transition. So we have actually populated in the first Frank quantum state, which is the high singlet S1 state. So the first point is to actually relax to a ground state, lower singlet state. Okay, this is the vibrational cooling which you're talking about. Then comes the fast mechanism, because it is decaying ultra fast within the first few picoseconds. We expect that this is happening because of the twist. Okay, and this twist could lead to the so-called formation of hot ground state, meaning it has come to the S0 manifold, S0 potential well, but it is in the higher vibronic level of the S0 potential, and so which we call as S0 hot, and then it is eventually decaying it, right? So we use this model, we did the fitting, and we obtained the kind of three basis vectors we see. This is the three basis spectra, and this is the time evolution of the population spectra, population with respect to the time. And so using this, we are able to really come up with the right photophysical model to fit our data. As you see here, this is the data which is fitting the initial time scale and the final time scale, and the solid line really fits the entire experimental data completely. Okay. Then comes the point of a film, and here we find that this film doesn't decay as fast as solution, and so something else is happening. So the point is, so what is happening is the solution, the molecule in solution is free to move around. Okay, and so because it has higher degree of freedom, it is able to twist the way it likes. On the other hand, when we make a thin film, we're actually constraining the molecule, and so it cannot really twist as easily as it does it in the solution. However, there is some twist which forms, and we are not sure how much twist it comes. So we call the twisted angle as some X state. The configuration of the molecule when it is twisted to a random position as the next state. And so this evolution is having an intermediate state, which is the X state. And then from there, it either goes to the triplets or it comes to the ground state. Okay. And so we use this model to fit. So we have the 4-level model. So instead of 3, we have 4. Okay. And everything is, when you look at the way it fits, it actually takes care of all the experimental data, it fits properly. Right? And so now we know how the molecule in solution and thin film forms is behaving. Importantly, in thin film, the excited state stays a long period of time. And so when you put this thin film, this molecule on TiO2, one can expect that the excited state, the long living excited state can, in principle, be sufficient to have sufficient time to inject. Okay. So this is the idea of the next slide. So these are the numbers which we get here. For that solution, the time scale is much faster. As you see here, tau2 is much faster. So within 2 picoseconds, it is coming to the ground state or hot ground state, and then it relaxes further. On the other hand, the thin film takes a lot of time, and you do have the various time scales. And this tau4 represents the kind of intersystem crossing, and the tau3 represents the intersystem crossing time scale, which is typically about 16 to 16 picoseconds, and it can go a little here and there. Okay, so the femtosecond study of leukoxide reveals that ultrafast excited state relaxation assisted by cold intersection dynamics, whereas the study of thin film suggests a triplet assisted relaxation of the excited state. With these ideas, we go about seeing how it would behave when you put it on the titanium. As you see here, this is the solution data and this is the film data of the first 10 picoseconds. And importantly, this part where the film is luminescing, we have the so-called stimulated emission. Okay, this is the delta T by T data. And when you put it on the titania, the stimulated emission is quenched within 1 picosecond. And when you look at the kinetics, we see that the kinetics of the stimulated emission decays within the first 2 picoseconds. And so we assume that we propose that the electro-injection is less than 2 picoseconds. Okay. Then we started looking at how it could behave when you make a solar cell with it. In fact, you look at this data, you feel it is very good. The only problem is when you actually calculate the efficiency, it is very poor. It is 0.02%. So for many years, almost for 2-3 years, I could never find a collaborator to actually make a solar cell device with this till we started doing in our own lab, okay, with the help of the student. So I thank the student who was patient enough to do it, right? Even though he didn't get any help from the other groups. So what we did is we found that the iodide electrolyte is not good. Then we changed it to another electrolyte, which is sodium sulfate based electrolyte, and it is improved by 1 order, even though the efficiency is 0.22%. Finally, we moved to a much cheaper and most common electrolyte, which is ferrous based Fe3 plus Fe2 plus based electrolyte in potassium chloride solution. And then we see that the efficiency has gone to 2.8%. Even though the purist in solar cell community would not like this particular JV curve, it is the best way forward in terms of looking at how one can get a solar cell performance with normal small molecule dye, which is very cheap. Okay, to compare the sensitizer which we used with the most common best performing dye sensor solar cell, the cost of Ufuxin is 2.5 rupees per gram, whereas the cost of the equivalent dye that gives you about 6 to 7% efficiency is 3,100 grams. We have used a SSC device, costs you 300 rupees per centimeter square. And then the liquid electrolyte we used is KCl solution with Fe2 plus Fe3 plus electrolyte. And this is cheap and non-toxic compared to the standard iodide redox electrolyte, which is corrosive and expensive. Overall, we found that the electrolyte is water-based and this device is functional in aqueous medium. And eventually, we ended up getting the so-called low-cost green aqueous dye-sensor solar cell. Keep in mind, this green doesn't mean the color green, but it has less environmental carbon footprint. Okay, in fact, this work is picked up by a lot of media, and as you see here, I can just share later all these things. We do lot of general media was interested, and Hindu ran an article on this work because this dye can be used for making kumkum, the kind of things which you use for Right. Now comes the second result, which is our work on the anthracene-based or the anthracene-based moiety. This is the anthracene-based moiety, and this entire thing is called the TTF sensitizer or tetrathiafulvene sensitizers. Right. So this molecules are also already published by our collaborator group, and they are giving a efficiency of 7.15%. Okay, so we have two systems, G1 and G3 molecules, whereas where G3 is giving a higher performance than G1, and we are tasked to find out why. In this paper, they have done the nanosecond flash photolysis experiment, which is the transient absorption in the nanosecond to microsecond timescales. So the same thing which I have done. So this is, as I showed you in the earlier slides, this nanosecond to microsecond timescale relates to the recombination kinetics. So they wanted to understand how the injection is happening. That's where we started working in detail. Okay, this is the absorption and luminescence work of the material system, of the T1, G1, and G3 dyes. This is the emission. As you see here, the emission of the film is strong. It's about, let's say, 3 orders more than that when you put it on the titanium. Okay, so we have calculated this quenching, and this quenching comes out to be about 90%. Meaning about 90% of the molecule of the population which is excited in the molecules in the excited state is injected into titanium, and so one can surmise that the efficiency could be very efficient. The electron injection efficiency could be very good. Then comes the time resolved luminescence data. In fact, this is what we expect, and this is what we see. The injection would lead to a shorter timescales for the glass titanium system. Now comes the actual point, which is the absorption studies. Why we had to do for transient absorption is that the time resolved luminescence is typical in the nanoseconds. We do not have the up-conversion spectroscopy setup, so we used a TCSPC or the time correlated single photon counting system, which is of the which goes from nanosecond and onwards. And we know that injection happens in femtoseconds to picoseconds. And so we went about doing the transient absorption studies. If you look at it, this is the solution data and this is the thin film data. Importantly, when you do the pump probe on titanium, we see that there is a band which is observed in this region. If you look at 400 to 500 region, for the thin film, you do not see any band. Okay, it's just the negative band. Keep in mind, we are talking about delta A. So this negative band would refer to a ground state absorption. And so for the thin film of titanium, we see that there is a ultra-fast formation of a positive band of the photoinduced absorption. In fact, this time scale is starting from 320 seconds. And so this gave us a conclusion that we can see a charge forming as fast as 320 seconds. But then, why so fast? We have no idea, and we do not know how fast or how long the injection happens and what is the actual recombination pathways. We have no idea. And so we went about looking at the photophysical of it. This is where the global fitting comes into the picture. First thing is we fitted the data away from the thin film in the solution. And this molecule, both the molecules fitted for the 4-level system, S1 to Sn. You have the internal conversion, then the vibrational cooling, and then the relaxation from the S1 state. Okay, this is the first picture which we see. Then, if you put the dye on the titanium, you do have this injection. Now, by understanding that when you look at the time scales, you see from internal conversion and this, the injection seems to be very fast, and so we thought the injection could be also starting from the S1 state, Sn state, and which we call as the hot electron injection. Okay, and so we tried to fit this material system with the dye and titanium system with the multi-step model, where the injection is expected to we assume the injection to be from Sn state, S1 state, and also the lowest S1 state, as you see here. And we fitted the data first for the solution in thin film. Okay, solution in thin film, the same thing which I mentioned in the previous example. We followed the same thing. We see the basis vectors, evolution associated data, and this is the proof that there is a good overlap with the experimental data. Okay, these two figures show that the kinetics are fitting well, which means the spectra should also fit well. And the kind of, and this table summarizes the various timescales you see for different processes. So here, the tau 1, which is the internal conversion, happens in 570 femtoseconds. Okay, and for the G1 solution, for G3 thin film, it happens around 700 femtoseconds. So overall, the internal conversion happens within after 500 to 800 femtoseconds. This is the time scale we have for the internal conversion, which means this is the time it takes from SN to S1. And from an S1 hot to actually S1 relaxed state, it is taking about 60 femtoseconds to 90 femtoseconds, and so 90 picoseconds. And so we see that the eventual relaxation from SN to internal conversion itself is so slow. How can you have ultra-fast formation of the charge? Okay, this is the reason why we thought the injection should happen even from the SN state. Okay, this is what it is. We fitted by that point, and then we found that this injection is not single injection, but it is multi-step injection. You have the injection from SN to conduction band of Tier 2 happening at 374 femtoseconds for G1 and 314 femtoseconds for G3, and then from the other states, it is 2.54 picoseconds from G1 and 1.1 picoseconds for G3. And eventually, if you look at all these things, you find that the injection efficiency of G3 molecule is way better than the G1 molecule. And so,
Dr. Ravi,
we could conclude that, yeah, I'm done. So we could conclude that the molecules, even though they are really good in terms of injection, G3 seems to perform better than G1, right? And with this, I conclude my talk. I have explained to you the basic physics behind various organic photovoltaic devices. I have explained in detail how to use the form probe measurements to follow the charge transfer process. And I have explained the two results from our group to showcase this process of charge transfer using femtosecond transient absorption. All this work was done by my student Biswas. It's his PhD work, and he really worked hard to get all this data. And the work is done in ACR-HEM, University of Hyderabad, in collaboration with Professor Gopal. We used his laser to do the form probe measurements. Molecules G1, G3 come from Professor L. Kiribabu from IICT, Indian Institute of Chemical Technology in Hyderabad. And the DFT calculations in Benifluxing was done by Prabhakar Chetty of NIT Kurukshetra. Okay, I just briefly take a moment to explain what the kind of work we do in our lab. We follow various research areas, the major being the ultrafast time-resolved absorption, time-resolved spectroscopy. We also do ultrafast nonlinear optics. We make our own devices, all kinds of devices we make. In addition to this, we work a bit on the ceramic photonics, where we look at the electric field-induced optical activity on rare doped ferroelectric systems, mainly to explore the multifunctional application. Okay, so I thank all my funding agencies to actually do the experiments. Importantly, the organizing team of SCOP, PRL Ahmedabad, they didn't give up. Looking at the pandemic situation, they went ahead and organized it. It's a very good job, guys. Congratulations. These are my group members, and I thank you all for your attention. I'm ready to take your questions now.
Thank you so much, sir, for such a detailed and wonderful talk. Yes, we do have a few questions for you, which we've compiled from all other platforms. So, Dr. Santosh, I'll first begin with my question. You had mentioned that the sample will actually be irradiated by sun, but in lab we are doing the experiment using femtosecond lasers.
Yes.
But femtosecond lasers generally work in the domain of multiphoton ionization. So how confident are we that the physics that we are exploring is a true reflection of what is actually happening when the interaction is one-to-one, one atom, one photon interaction in the case of sunlight?
Fantastic. That's a wonderful question. And if you remember the slide I showed about the experimental requirements, in one quadrant I showed about higher sensitivity. Okay. So in order to do form probe measurements for materials or organic molecules to be used as for solar cell applications, you need to go for very low fluences. Very low fluences. In fact, the fluence would be something like 5 nanojoule. Okay, 5 nanojoule per centimeter square. It's extremely small. few nanojoules to few microjoules. In fact, if you go into 1 microjoule, you already have this kind of knowledge optical vision. Okay, so we work with very low, very low uh, fluence, and there has been work, a couple of papers published in around 2010 and 11, where they clearly mentioned the kind of fluence regime one can use using the femtosecond pulses in order to mimic the solar. Okay, so idea here is that the idea to keep in mind is always use low fluence as low as possible, and that's all. I would still say that you cannot avoid having higher energies, but the kind of thing you were talking about, multi-photon ionization, that happens at high intensity. Okay, that is what we call as the non-linear optical regime. We do not go there. Okay, the absorption is still linear here.
Okay. The other question that
the main point is to actually excite the molecule. That is the only thing you should.
Right. So I have another question. Low efficiency of solar cells. Is it because of low absorption cross-section or low retention within the cell?
I would like to answer your question in 2 points. One is, it's important that we compare the solar cell, whether it is inorganic solar cell or organic solar cell. The reason is, once the charges are formed in inorganic solar cell, typically the inorganic solar cells, inorganic semiconductors have a good order. Okay, they do have good crystallinity and good order. So the transport properties of solars or charges are very high. Right. So the point about absorption and conversion of electron, the photon to electron or the exciton, when each photon corresponds to 1 exciton, and each exciton dissociation corresponds to 1 electron or charge. This is the point. And so the conversion from a photon to the electron typically is very good for the organic material system. However, these organic material systems are known to be highly disordered. And so the low efficiencies are mainly because of the low disorder, high disorder, and the presence of lot of charge traps, which doesn't allow the charge to actually go to the electron, which we call as the mobilities. Okay, the mobilities of the charges in organic systems are very poor. And this is the reason why you have very poor efficiencies. Okay, this is how I would like to answer, because it doesn't matter how good is the absorption, it doesn't matter how good is the conversion from electron, the photon to electron at the interface. What is actually matter is that how this electron goes to the electron. Okay, this transport is what is actually a problematic for the organic solar cells.
Got it, sir. Got it. Those were all the questions I had for you, sir. Thank you so much. Thank you once again for coming and presenting over here.
I just took my time because I know I had a lot of time. Okay.
It's okay, sir. It's fine. So with this, we conclude this session. And I want to thank all our speakers for their time and their participation, despite the ongoing difficult times. We'll now take a short break, but before I go, I would like to invite Dr. Nigel to chair the next session. So over to you, Nigel.
Hello. Yeah, so we'll be starting the next session in 5 minutes. Hello. Yeah. Welcome back. Hello. We welcome everyone to the third and final session of today in the virtual SCOP 2020 conference. I'm your session chair, Nijil Lal, and this session is titled as Nonlinear and Quantum Optics. Just a few reminders before we start the session. The panelists' pre-recorded presentation will be played, or they can share their live screen using the share screen button at the bottom right of the window. And I request all the presenters to strictly adhere to the clock. The audience can use the Q&A widget to type in your questions, as many of which will be answered at the end of the session. You can use the chat widget to communicate with other attendees and to comment on the presentations. On those notes, let's start this session on nonlinear and quantum optics. As the first talk in this session, we have Ms. Shrestha Biswas, who is currently doing her master's in IIT Kanpur. She'll be delivering a talk on introducing coherence in radial degrees of freedom. We'll be playing a pre-recorded video of her talk, and Ms. Shrestha will be available for any questions after the video. So we'll start playing the talk right now. Over to Anirban.
So actually, I was prepared for a live talk. Just give me a minute. I will show my pre-recorded video. Just give me a minute.
Okay, so we can either play the pre-recorded video over here, or Shrestha, would you want to give the talk live?
I'm playing it. Just I'm opening it.
Okay, okay, you can share your screen.
Yes, yes.
Shrestha, it seems like there is a problem with the audio. Would that be all right if we play the video from here?
Okay, sure.
Yeah. So
I'm stopped sharing my screen.
Yes, sure. Thank you. So Anirban, could you play the video from here? Okay. Yeah.
Should I go for a live talk?
Yeah, if that is possible, that would be great. You can share your screen with the slides and you can give a live talk as well.
Okay. Is my screen visible?
Yes.
Okay, so here today I'm going to talk on titles Introducing Coherence in Radial Degree of Freedom. This is my MSc project that I have done with affiliation to IIT Kanpur under the supervision of Dr. Anand Kumar Shah. So the first question we are addressing here is what is coherence? So we know that, and we are basically interested in doing coherence between different points of an optical beam. That is the optical coherence. So we know the optical sources are generally random. And we try to understand different coherence functions such as degree of coherence, cross-spectral density in spatial, temporal degrees of freedom to understand the fundamental statistics of the random source, as well as these kind of coherence functions have a lot of applications in different fields. But in this study, we are concentrating on radial degree of freedom. So, what are the motivations behind this interest? The first answer is this radial space is semi-infinite. That is, it extends from 0 to infinite. And this r equals to 0 of the radial space is a spatial point. Due to that, the radial cross-spectral density, radial degree of coherence, these coherence functions is slightly different than similar coherence functions in other degrees of freedom. And hence, there is a fundamental interest to understand this symmetry. The second thing is we have the whole class of Lagrangian modes, which has these discretized P mode indices as well as these discretized L mode indices. These L mode indices have already been used extensively in the field of quantum communication. Now, our idea is to extract application from the radial P modes of the Lagrangian beam. And the third thing is we expect that with this kind of a study, we can get control over radial structure of different light beams. So to start with, let us understand what is the definition of radial cross-spectral density. So let us suppose this is the optical beam and we choose a point r1 theta 1 on that and another point r2 theta 2 on that same optical beam. Now, the electric field at point r1 theta 1 and at point r2 theta 2 ensembled average over that gives us W r1 theta 1 r2 theta 2, which is the spatial cross-spectral density in cylindrical coordinates. Now, to take advantage of the radial symmetry, if we have a radially symmetric beam, in that case, we choose another point at r2 theta 1. That is, these two points have same azimuthal location theta 1 but have different radial locations r1 and r2. So after getting this W r1 theta 1 r2 theta 1, we numerically integrate over theta coordinate or theta 1 coordinate to get W r1 r2. And this 1 by 2 pi is the normalization factor. This is kind of a partial tracing which helps us extract information of a radial symmetric beam. Now, if we have an incoming electric field with radial symmetry such that electric field at point R can be expressed as a summation over radial modes Fn R with mode index n and with weightage alpha n, then the W R1 R2 or the radial cross-spectral density or this kind of an incoming field will take this kind of a form, where lambda nm is the cross correlation of these FNR modes with mode indices n and m. Now we can show that if we have this kind of a form, then this lambda nm can be evaluated from WR1 R2 by doing inverse transformations. This is kind of a radial extension of the generalized Wiener-Hinton theorem. So to elaborate on that, let us take one radial mode, that is FNR is e to the power IPR by root r, which is the radial momentum eigenmode, where PR is the radial momentum of that mode. For that kind of a radial mode, we get WR1R2 like this, where SPR-QR is the cross correlation of different radial momentum eigenmodes with radial momentum PR and QR. For this kind of a structure, by using the orthonormality relation of these modes, which is basically a Fourier transformation relation, we can evaluate SPR-QR from WR1R2 with this mathematical formula. So basically, we are multiplying this formula over here on both sides and integrating over R1 and R2 to evaluate SPR-QR. We can take a similar example. So here our mode is Lagrangian modes with mode indices P and L. Now, if all the incoming modes are coming with same Lagrangian modes with same OAM index L, but with different radial mode indices P and Q, and such that the cross correlation between this radial modes is SPQ, then we can evaluate this SPQ using the orthonormality relation of the Lagrangian P modes with this formula. So SPQ is WR1R2, and then there is inverse transformations happening. Now, if this lambda nm is such that there is no correlation between the radial modes, that is lambda nm is beta n, then delta nm, then we can have a coherent mode representation for our cross-spectral density. So here this Fn R into Fn star R2 is our coherent mode, and beta n is the weightage of this coherent mode with mode index n. This beta n as a function of n is called the spectrum, and you can see that beta n can be evaluated with WR1R2 with similar kind of inverse transformation. So if we have an unknown incoming field coming in, and if we can understand that it has radial symmetry, then by measuring this WR1R2 and doing some mathematical trick like this with using this mathematical formula, we can understand the radial momentum content of the beam or the Lagrangian P mode content of the beam. So the entire problem boils down to measure WR1R2 of my unknown incoming field. So for that, we have devised an interferometer that we call radial interferometer. So suppose we have a source and a beam splitter where the beam splits into two, and we introduce 2 mirrors in one arm, similarly 2 other mirrors in the other arm, and one more beam splitter where the optical beam from these 2 arms are combining. And we have the CCD or EMCCD camera, that is our detector. Now here we are interested in measuring interference between points R1 theta and R2 theta, that is of same azimuthal location but different radial location. For that, we introduce 2 lenses in one of these arms. We may call it arm number 1. So if these lenses have focal length f1 and f2, then let us see what's happening. Now this incoming field is incident on the beam splitter splits into 2. Now in the first arm, due to the presence of these lenses, this gets magnified by a factor of m, where this m is the ratio of f2 and f1, and the separation of these 2 lenses is f1 plus f2. So this is a magnifier combination of lenses. Now this lenses does not only produce this magnification, this is also doing an inversion. So as this picture is showing over here, a point at point A before the lens combination goes to a point in this part after the lens combination. And a similar kind of inversion is happening in the plane normal to your screen. So there are 2 inversions, x to minus x and y to minus y due to this lens combination. This moves a point at theta to a point at theta plus pi. To take that into account, we place 2 Duff prisms in the other arm such that the beam in the other arm also get inverted from x to minus x and from y to minus y. Such that when these 2 beams are getting overlapped on the EMCCD or CCD camera, our detector, there is no angular tilt between these 2 beams. Now having this interferometer, let us understand how to extract the WR1R2 function. So we have this original field. Now at this point, the information about electric field at point R is contained, and at this point, the information about electric field R by M is contained. Now due to the arm where there is no lenses, we can get just a replica of that. So our electric field at R moves to our electric field at point R. But due to the arm with lenses, electric field at point R goes to a point at MR, and the electric field at point R by M goes to a point R. Hence, when these 2 beams are combining with each other, the electric field of the original beam at point R and at point R by M overlapping on each other at point R on the detector plane. So on the detector plane in the overlapping region, the electric field at point R, theta can be expressed as electric field due to the first arm, that is with the lenses, at point R by M, theta, and electric field due to the second arm, that is without the lenses, at point R, theta. And the beta 1 and beta 2 are the phases of this electric field that they achieve after traversing the 2 paths. And K1, K2 are due to the beam splitting ratio. Now we can have the I out, the intensity on the overlapping region of the detector plane. This involves the electric field intensity due to the first arm, intensity due to the second arm, and here comes the cross correlation term, which involves cos delta and sin delta. This delta is beta 1 minus beta 2, that is the phase difference of the optical beams in these 2 paths. Now by tweaking the parameter delta from to 0 and to pi, we get the real part of WR, R by M, theta. And by tweaking it to pi by 2 and 3 pi by 2, we get the imaginary part of the function. So we need to introduce this extra phase del. For that, we introduce a geometric phase in one of these two arms. This can be a wave plate, or we can place the mirrors of this arm on a translational state that will help us. Now, when this WR, R by M, theta is in our hand, we numerically integrate it over theta to get WR, R by M. After that, we need to repeat this experiment with 5-6 different M values and follow a reconstruction process to evaluate WR1, R2. I'm not going into the details of the reconstruction. This is a code. We need to have a code for this. So I am going to discuss an application of this radial interferometer. So we know there is a process of spontaneous parametric down conversion, SPDC, which can produce entangled photons. So if we have a nonlinear crystal and a palm beam is impinging on it, after interaction of the palm photon with the nonlinear crystal, it can produce photons which are entangled in various dimensions. We are concentrating on the photon entanglement in radial and azimuthal positions. Like these photons are entangled in the radial and azimuthal positions. Now, if this palm beam is a Gaussian beam and we follow a collinear phase matching condition, that is the wave vector of the palm beam and the wave vector of the signal and idler photon are in the same direction, then the biphoton wave function, that is the combined wave function of these two entangled photons, takes this kind of a Smith decomposition form, which involves Lagrangian modes, such that if one of these photons, let's say we call it signal photon, if this involves mode indices P and L, then the other photon, like the other photon of the entangled pair, will involve mode indices P and minus L. So if we can evaluate the lambda LP, or measure the lambda LP, the spectrum function to the Smith spectrum, then we can understand the entanglement of these SPDC photons, and we can use it for quantum communication, which will be obviously higher dimensional quantum communication. So the problem is here to evaluate lambda LP. So after a 3-page long calculation, we end up getting that this lambda LP can be evaluated from the cross-spectral density function of one of these entangled photons. The thing is, this is the lambda LP, the expression of lambda LP that we get. The main point of interest is this one, WR1, theta, R2, minus theta. The thing is, after getting the two entangled photons from the SPDC field, we need to choose one of these entangled photons, and we need to measure this WR1, theta, R2, minus theta. For that, we can use our radial interferometer that I have just introduced. So in that case, we are using two Duff prisms here for x to minus x inversion and y to minus y inversion. This will give us WR1 theta, R2 theta. So no inversion in the azimuthal direction. But as we need theta and minus theta, we remove one of these Duff prisms. And this helps us achieving WR1 theta R2 minus numerical calculation and get lambda LP, that is the 2D Smith spectrum of this SPDC entangled photons. This is the end of my talk. Here are the conclusions. So I have introduced a radial interferometer that can measure WR1, R2, but this is not using any radial slits. So there is the masking of the input field due to the slits, and the intensity of the input field is not being diminished. For that reason, this radial interferometer can be used at a high light level, or we can call it a classical light level. Or we might, sorry, just a second. Or we might use it in a low light level that we might call in the case of SPDC photons. Now, and the second thing is, if we have an incoming field and we can measure the WR1, R2 of that, we can understand the radial momentum content of the field, we can understand the Lagrangian P mode content of the field, and this can lead way to radial mode detectors. And the third thing that I have just mentioned, after measuring the WR1 theta R2 minus theta of one of these SPDC photons, we can achieve the biphoton 2D Smith spectrum of the SPDC photons. So here I would like to thank my project supervisor, Dr. Anand Kumar Jha, and my collaborator, Raghwinder Bhattacharya, for their immense support. Thank you.
Thank you, Shrestha, for the very nice talk. We'll now take a few questions from the audience. We have a question from Anindu. Could you comment on the effect of the radial index on the entanglement?
Radial index on this question is not very clear to me.
The question is, could you comment the effect of the radial index on the entanglement?
So the thing is, if we can have this biphoton wave function like this, then this is the Smith spectrum that it gets. So this is a unique Smith decomposition involving the Lagrangian P indices. So if we can have this, if we can evaluate the lambda LP, the 2D Smith spectrum, then we can understand how these photons are entangled in the L dimension as well as in the P dimension. So we can use this entangled P dimension to encrypt information. So it can be used in quantum information. That's it. I think this answers your question.
Okay, so if there are further discussions that can be taken later on. So let's thank the speaker once again. Thank you, Shrestha. So now we have the next talk is from Dr. Raghwinder Singh, who is currently a postdoctoral fellow at Delaware State University, USA. He is also an alumni of PRL, as he worked as a postdoctoral fellow here with Dr. Gautam Samanta. He'll be delivering his talk on optical atomic magnetometry with synchronous modulation of 2 resonant light fields. We'll be playing a pre-recorded video of his talk, and Dr. Raghwinder will be available for any questions. We'll start playing the talk now.
Hello, everyone. First of all, I would like to thank the organizing committee for giving me this opportunity. The title of my talk is Optical Atomic Magnetometry with Synchronous Modulation of 2 Resonant Light Fields. In this talk, first I will give the brief introduction about the optical magnetometry. Then I will talk about synchronous optical pumping of atoms, then the motivation behind this work, and then the proposed experimental setup. And then I will talk about result and discussion, and then conclusion. In atomic magnetometry, we need some kind of a atomic medium. So typically we use alkali atoms such as rubidium, cesium, and sodium. In the experiment, we take these atoms in a vapor cell where the spin of these atoms will be randomly polarized. In atomic magnetometry, it's a 3-step process where first we shine a polarized light on the atoms that will align the atomic spin in some particular direction, which we call the generation of atomic alignment or orientation in the atomic medium through the optical pumping. This generation of alignment or orientation that depends the polarization state of a input light. For example, for a linearly polarized light, we get a aligned state with the peanut shape. In the next step, we apply a magnetic field B to the atomic medium. That magnetic field causes the Larmor precession to the atoms with the Larmor frequency omega L. In the third step, you need to prove that the atomic medium either one can do by measuring the polarization rotation or direct transmission of a light through the atomic medium. Any atomic magnetometer has a 2 basic characteristics. One is sensitivity and another is a dynamic range. The sensitivity means how precisely it can measure a magnetic field. Any atomic magnetometer, how precisely it can measure the magnetic field. In the dynamic range, what's the smallest and the highest value of the magnetic field a magnetometer can measure. The different techniques have been employed to improve both of these characteristics. The synchronous optical pumping of atom with a modulated light will allow us to measure very high magnetic field precisely, for example, Earth magnetic field. and we are going to use this technique in our experiment. So I will give some brief introduction about the optical pumping of atoms. So this technique was first proposed by Bell and Bloom in 1961. So in this technique, what we do, we pulse the light intensity with certain frequency omega m. That frequency matches with the Larmor frequency of the atoms, the Larmor precession of the atoms. With that, the light will be pumping the atom at its Larmor frequency. That's what we call the synchronous optical pumping of the atom. So in Bell-Bloom technique, what the author did, that they apply it to a magnetic field which is transverse to the light propagation direction with ellipticity equal to 45. So if we consider this V, the x-axis, as the axis of quantization, then we will have a pi and sigma transition from the ground state sublevels. The pi transitions happens when the light polarization is parallel to the axis of quantization, and the sigma transitions happens when the light is perpendicular to the axis of quantization. So this sigma and pi polarized light, these light will couple the ground state sublevels and form a lambda system, and create a new state in the ground state sublevels, which we call a dark state, which results the coherent population trapping of atoms. So this coupling will, this lambda system will also result a coupling between the ground state sublevels of a same hyperfine state, and that coupling will give us a resonant condition like this. So for example, in our case, is delta m is equal to 1. So then we will have a magnetic resonance at omega m is equal to omega L. So when we demodulate this signal with a lock-in amplifier, we get two resonances. One is in phase and another is a quadrature component of a lock-in amplifier. So you know your omega m, you know your omega L, that will give you the magnetic field value. So this technique is being widely used in different area, and it can measure a very weak field. For example, the magnetic field produced by our brain, by our heart, and the very strong field also. So motivation behind this work is the remote sensing of a geomagnetic field using backscatter fluorescence from a mesospheric sodium atom. So in 2011, a Butker group from Berkeley University proposed a method in this paper that one can measure Earth magnetic field 90 kilometers above the Earth surface using sodium layer in the mesosphere region. So what exactly they propose, that if one use a modulator light with circular polarization, and when the magnetic field is perpendicular to the light propagation direction, and then if we demodulate the backscattered fluorescence signal at the Earth, then we will able to know the magnetic field at the 90 kilometer surface above 90 kilometer above the Earth surface. So that time the technology was not there to develop those lasers. So it took some time to develop those lasers, and in 2018, the same group performed the real experiment, and they were able to measure the Earth magnetic field 90 kilometers above the Earth surface. So there were different experiments were performed after and before them also, and the maximum sensitivity is in this Sky experiment is 28 nano Tesla per square root of Hertz. And one thing to note is that in all these experiments, the resonance is produced by a single modulator light using sodium D2 line. The sensitivity in the Sky experiment is 100 times or more than 100 times less than the sodium experiment performed in the lab. So therefore, there new techniques need to be explored to further improve the sensitivity. The coherent population trapping with two continuous laser field is already existing technique. So in this technique, what people do, they use a two laser light instead of using single laser light. So one laser light will be resonant from upper ground state, and another laser light will be resonant from the lower ground state to the common excited state. So in this, if we apply a longitudinal magnetic field along the light propagation direction with the circular light polarization, we will have a 3 lambda system. So in these lambda system, the lambda system is formed by the sublevels of 2 different hyperfine state. Instead of like earlier in a single beam experiment, we have a lambda system which were formed by the sublevels of a same hyperfine state. So these each resonance will give you a separate each lambda system will give you a separate resonance when the difference between these 2 laser field will match with the hyperfine splitting of the ground state sublevels. For example, in lambda system 3, this sublevel is moved up by omega L, and this lambda system is moved down by omega L. So we have a resonant condition delta is equal to 2 omega L. So these are the resonant conditions when we apply a longitudinal magnetic field. So when we measure a signal as a function of a difference detuning between these 2 fields, so we will see 3 resonances. So the first resonance is produced by 2 omega will be produced by lambda 3, and the other resonance will be produced by lambda 1, and then the center one will be produced by lambda 2. So this center resonance is being widely used in atomic clocks. So we further modify this setup and proposed a new scheme using 2 modulated CPT fields. So earlier we were using continuous laser field. Now we are using modulated CPT field. So in this particular setup, we propose that we will modulate the light with a acoustic optical modulator, and then we pass through that light through a acoustic optical modulator. So this EOM will produce a 2 laser beams, omega 1 dash and omega 2 dash. So this omega 1 dash is resonant from the upper state, and the omega 2 dash is resonant from the lower state. But these both resonances are modulated with both frequencies are modulated with the frequency omega m. So this scheme we call the synchronous CPT scheme. So in this scheme, first we apply the longitudinal magnetic field along the light propagation direction with the Larmor frequency 60 kilohertz. So as I explained earlier, we will have a 3 lambda system, and these this lambda system will give you a resonance condition omega m is equal to 2 omega L plus minus delta. So when we do the measurement, we will have a resonance at 120 kilohertz, which is the frequency difference between these 2 sublevels. And when the delta is non-zero, then you will see a splitting in the central resonance. So to match with our SCI experiment, we perform the experiment by applying a transverse magnetic field, which is perpendicular to the laser propagation direction. As I explained earlier, when the field is perpendicular to the laser propagation direction, and then we have a circularly polarized light, then we have a pi transition also from the ground state sublevels. So these pi transition will form 2 new lambda system, these type of lambda system, which will give you a resonant condition omega L plus minus delta and 3 omega L plus minus delta. And so if we do the measure, if we measure the magneto-optical resonances, then we have a 2 resonances. The omega is equal to omega L resonance because of lambda 4, and the 3 omega L resonance because of lambda 5. Now, if we want to make any atomic magnetometer, so we need two things. One is the peak amplitude of that resonance, and the second is the full width half maximum of the resonance. So to match with our SCI experiment, first we increase our applied magnetic field to the 257 milligauss, which is comparable to the Earth magnetic field, and then we measure the resonance at 50% duty cycle. The other thing is that when we do this magnetic field measurement, and then the light duty cycle is very important. The sensitivity depends on the light duty cycle also. So therefore, we measure the amplitude and full width half maxima of a resonance at different duty cycles. As you can see that the full width half maxima decreasing continuously, whereas the peak amplitude first increases and then decreases, and the maxima is seen at 35% duty cycle. And the keep the intensity in all these experiments kept constant. If we compare this result with single modulated light, you can see there's a clear big difference. For a single modulated light, 50% duty cycle will give you a lower peak amplitude. As the duty cycle decreased, the peak amplitude start increasing and get maximum at 17% duty cycle, which is a different from the synchronous optical CPT scheme. So next we measure the magnetic noise spectrum and the sensitivity of the experiment. To do that, we use this formula where the delta F is the full width half maxima and SNR is the signal to noise ratio. So first we measure the magnetic noise spectrum at 35% duty cycle, and we measure our sensitivity to be 45 picotesla per square root of hertz. The next we did the sensitivity measurement at different duty cycle. As you can see that as the duty cycle is lower, the sensitivity improves. If we compare this result with a single modulated light beam, you will see a similar trend. But there is one important thing to be noted is that in the synchronous CPT scheme, after the duty cycle 35%, the light that the sensitivity does not decrease much. Whereas in the single modulated beam, the intensity keep improving as the duty cycle is lowered. So we have improved our sensitivity at the longer duty cycle, which is very beneficial for the sky experiment, because the longer duty cycle will allow us to more fluorescence in the backscattered from the sky experiment. So in the summary of our work, we developed a new technique, synchronous CPT scheme, which can improve the sensitivity in the sky experiment. In this scheme, we use two resonant light field instead of using single light field. And this our technique has increased the sensitivity at a longer duty cycles, and we observed 45 picotesla sensitivity at the 35% of duty cycle. And we expect to conduct our remote magnetometric experiment employing this technique in the Day1 line soon. Thank you very much.
Thank you, Raghu, for a wonderful talk. We can take a few questions now. Raghu is with us here. Subedh has a question: why the polarization of light is so important here?
As I explained in the talk also, if we have a different polarization, we can create a different type of lambda system. So in the atomic system, so whenever we want to see any resonance, we need a lambda system. And the generation of any particular lambda system, whether it involves sigma or pi light, that depends on what is your polarization direction and the direction of your magnetic field. So in a sky experiment, people use a ellipticity is equal to 45, which is circular polarization, and that is allowed to pump the atoms in some particular sublevels where we see these very strong signals, which is not possible with the linearly polarized light. So everything depends on how you want form the of the lambda system, or how you want to do the optical pumping of atoms in any particular state.
Okay, so if we do not have any further questions, let's thank the speaker once again. Thank you, Raghu.
Thank you.
Now we have Dr. Radek Lapkiewicz from the Quantum Optics Lab at the University of Warsaw, Poland, with us. Bear with me, there is some issue with my video over here. Sorry for that. So we have Dr. Radek Lapkiewicz from the Quantum Optics Lab, Warsaw, Poland. He did his PhD with Anton Zeilinger, working on non-classical effects with photons. He also worked in the same group as a postdoctoral fellow, focusing on quantum imaging with undetected photons. His current interest focuses on breaking the limitation of standard imaging using quantum correlations of light. Today, he'll be delivering a talk titled "What Can Photon Pair Detections Do for Super Resolution Microscopy and Phase Imaging?" I welcome Dr. Radek to present his talk.
Okay, let me share the screen. Hello, everyone. Can you see my screen and can you hear me?
Yes, Dr. Rajeev, we can see your screen.
So first of all, I would like to thank the organizers for the opportunity to talk. It's really amazing that in these crazy times you're still able to organize this great conference. Thanks a lot. I regret that I cannot talk to you in person, but let's hope some other day we can do this. And okay, so let me start. Basically, the title of my talk is already the outline. So I would like to talk to you about how detecting photon pairs, or in general photon correlations, can be useful in super-resolution microscopy and in phase imaging. So I will start from super-resolution microscopy, which is the field of optics and bioimaging that deals with obtaining sharper images. So here you see a standard confocal image and a super-resolved image from our works. I will focus on these two papers. Okay, so first, as a reminder or as an introduction, the microscope that I will mostly consider is a scanning stage microscope. So you have a sample. The sample is positioned on a stage. In this case, for this drawing, it's just a point emitter, and you shift the point emitter across the laser beam, the blue beam over here, and you detect fluorescence, the green beam. As a function of position of the stage, you obtain fluorescence intensity, and unfortunately, what you see, it's not a point. You rather see a white spot, which is called point spread function. So an image of a point is called point spread function. The narrower the blob or the Gaussian, if you want to approximate it with a Gaussian, the higher the resolution. So this is pretty old, like this is 19th century optics. It was discovered by Ernst Abbe, German physicist. And Abbe, to discover this fact that you cannot, resolve arbitrarily close sources because of the finite width of point spread function, he used a couple of assumptions. I will read them because they're important. So he assumed linear optics, which is really natural for us if we don't work with very intense laser fields. Uniform illumination, typical for wide field microscopes or for photos you take with your camera. Far field detection, that's also a natural assumption. This is in contrast to near field scanning microscopes. You assume that your object doesn't change in time, and implicitly, because quantum mechanics wasn't there in 19th century, of course, Abbe used classical light theory. What he found was that the minimal distance at which the sources can be placed and you can still resolve them is given by this formula, lambda over 2 times numerical aperture of your imaging system. This is roughly half the wavelength of light. So for green fluorescence, you would get something like 250 nanometers. And okay, so why do we care about this 19th century physics? This image should convince you. So this is an image of a biological structure. You have some details here. We have standard imaging, limited by Abbe resolution limit. And this is what you can get if you break the diffraction or resolution limit discovered by Abbe. So you simply have access to much more information, and there's place for discoveries in many branches of science if you can see finer details. And this scale of 250 nanometers is actually a relevant spatial distance scale, because this is where subcellular structures are, their sizes. So this is a very interesting scale, and it matters if you improve the resolution by a factor 2 or 10. Okay, and it's not only my opinion that this is important. So, the Nobel Committee agrees here. The 3 gentlemen, Betsy, Kerr, and Myrna, obtained Nobel Prize in 2014 for super-resolution microscopy. Okay, so now you're hopefully excited and interested how to break Abbe's limit. So, simple logic, if you want to break the limits, I assume that he didn't do mistakes, so you have to break at least one of his assumptions. And this is a table listing the assumptions and a couple of techniques that you might find in the literature if you like. Actually, these two are the Nobel-winning methods, STAT and localization microscopy. So we see that each super-resolution method breaks at least one of the Abbe's assumption. Okay, so for instance, STAT, which is probably the most famous one, uses nonlinear sampler response and non-uniform illumination, because you use this fancy shape of the scanning beams. Now the question is, this is a quantum optics session, so can quantum optics contribute? And yes, there were many works related to the first beautiful talk of this session by Shrestha Biswas from Anand Jha group. So you know, the typical quantum optics approach is that you generate a complicated state of light, for instance with SPDC, that you shine it in your microscope onto the sample, and then you measure correlations. So you can look up these papers. There were also interesting theory works using quantum fusion information, but our approach is different. We ask the question, you know, maybe you don't have to work so hard and generate a quantum state in a nonlinear crystal or in cold atoms or complicated stuff. Maybe we can be lazy and use the quantumness of the light generated by the sample. I mean the biological sample labeled with fluorescent dyes or quantum dots. Sounds strange, but let's see, maybe we can do this. So, you know, if the photons emitted by a quantum dot or a fluorescent dye molecule, or in general we call this a emitter that's labeling the sample, if photons came in pairs, this would be really cool. Because if you consider the detection probability of one photon, you get this point spread function blob. If the emitter was always emitting two photons, the probability of detecting both of them would be given by the square of these probabilities. So for Gaussians, it would be narrower by a factor of square root 2. And then you can simulate it, and you see that you could resolve three emitters that you cannot resolve with standard single photon emitters. And this is the idea by this gentleman. You might not know him as a saxophone player, which he also is. He's more famous for getting the Nobel Prize a few years back for super-resolution microscopy. This is Stefan Hell. And he had this paper, which is not very famous because such emitters unfortunately don't exist, or they are very impractical. Okay, but we have another guy who had a very cool idea. This is Ossip Schwarz from the Weizmann Institute. And he noticed that, okay, actually, if this works for photon pairs, this should equally well work for missing photon pairs. Okay, so if you had emitters which are sources of missing photon pairs, and this will become clear in a minute what I mean, this should also work. The mathematics should be the same. Okay, and now it turns out that these emitters are not that uncommon. Actually, they are very common, and all the emitters, or almost all the emitters used in bioimaging, are sources of missing photon pairs. And the effect of missing photon pairs is called anti-bunching. And this is one of the most famous quantum experiments from the old days. This is a milestone in quantum optics from 1977. Of course, this comes from the group of Leonard Mandel, who basically did all the important experiments in quantum optics. And the effect is not as a system, it's basketball. I know your national sport is cricket. I didn't analyze cricket results, but Ron Tenne, a colleague from Weizmann, analyzed actual NBA data from 2017-18 season, and he observed anti-bunching. Basketball cannot simultaneously be in two baskets, which you see at this curve of scores, actual data. Okay, so back to physics and imaging. So this idea of Ossip Schwarz from the group of Dan Oron was realized experimentally in the same group in this quite a difficult experiment, because they used an EMCCD camera, which can only run at a limited speed, up to, let's say, 1,000 frames per second. This is relatively slow to observe anti-bunching, so you need to slow down your emission cycle. You do this by having a pulsed laser at the rate that fits the frame rate of the camera. So you run your experiment at 1 kilohertz. You shoot a laser pulse, and you take one frame for one laser pulse. By this, you make sure, if the pulse is much shorter than the lifetime of quantum dots, that one quantum dot per one frame, which means per one pulse, can only emit one photon. Okay, and according to the theory developed by Oron and Schwarz, you should, by detecting anti-bunching, spatially resolved, you should be able to sharpen the images because the point spread function is squared. You remember this Gaussian for one photon detection gets squared if you talk of two photons. Indeed, this is what they observed in the experiment. Super resolved images for second order correlation and also for third order correlation, which means missing photon triples. Okay, this is very cool. The experiment was very slow, unfortunately, because you had to run it the frame rate of the camera, and also it's wide field, which is not that popular in bioimaging. So actually, bioimaging prefers confocal. Let me remind you what a confocal microscope is. It's simply a 4F imaging system. You have a sample, which again is a single point source in this case. You have the excitation beam. You scan the sample across the excitation beam, and you detect fluorescence intensity with a point detector, or a detector with a small pinhole in front of it. And you see that the detection probability depends on the position of the sample, of course, and it reaches maximum when the sample is in the middle between the excitation beam and the detector position with respect to the axis. Okay, this is an important detail. But an important fact for the confocal microscope, if you want to have good resolution, you put a pinhole in front of your detector or use a very small detector. Okay. Now, depending on the position of the detector with respect to the optical axis, you will record a shifted image of the same source. And this was noticed by Colin Shepard long ago and observed in experiment by Enderlein 10 years ago. So the idea, if you understand the confocal microscope, is relatively simple. So the typical dilemma of a bioimaging person, of a practical microscopist, is that he wants to have good resolution, which you can achieve by closing the pinhole in the confocal microscope. But you also want to have high signal, to have high SNR images. So, and by closing the pinhole and cutting away fluorescence, you lose signal and decrease your SNR. So you open your pinhole to have some intensity. And the idea of Shepard and Enderlein takes away this dilemma. Their idea is to simply have an array of detectors replaying a single detector. And then the array is big. It's like an open pinhole. And each detector can be very small. Each detector registers a high-resolution image with small signal, but the entire array gets all the signal. Okay. Now, if you naively add the pictures acquired by each detector, you would get, not surprisingly, the same image as you would get with an open pinhole. But if you're smart and you notice that the images are shifted, for the reason I demonstrated here, each detector registers a shifted image, you see that you're able to, you first should shift the images and then add them. Okay, then you get super resolved images with high signal. And maybe I will skip this, or I just briefly mention, you can describe the same story that I described with images in the previous slides by saying that the signal in the confocal microscope is a product of excitation PSF and detection PSF, and therefore it's narrower by a factor of square root of 2. I just want to mention that this gives you an improvement of 2 factor for resolution if you apply the convolution, and it's actually a commercial product developed by Zeiss already, and it's gaining ground for broad applications in bioimaging. Excuse me, how am I doing with time? Like, how much time do I have left?
Yeah, half an hour more.
Okay, thank you. So now I will, I explained what a confocal microscope is, what anti-bunching is, and this particular practical version of confocal microscope, which is called image scanning microscopy. Now let's put this stuff together. So we actually have image scanning microscope, where in this experiment, this was the setup built in Zilberberg and Oron groups in the Weizmann Institute in Israel. So this is the setup we have. We have an objective positions next to the sample, and a dichroic mirror, which allows us to excite the sample and transmits fluorescence to an array of detectors, which in this case was a fiber bundle leading to single photon detectors. Okay, and now, okay, just a bit of formulas, but I will be brief here. This is an argument why looking at missing photon pairs will lead to high resolution again. So imagine that you're detecting the number of photon pairs as a function of delay between the two photons. So this is the actual data. You see that the number of photon pairs at the zero delay is slightly lower than at a higher delay. You see these peaks because we excite the sample with pulses again. This is corresponding to the lifetime. But you see that the peak at zero delay is lower than the peak at non-zero delay. This is because here, each emitter is prohibited to emit 2 photons, and here, at a given delay, at a given non-zero delay, emitter can actually emit 2 photons. Okay, so you see by observing that the G2 function, so the probability to detect 2 photons at zero delay is non-zero. You see immediately that this sample contains more emitters, more than one, at this spot. Still you see this anti-bunching signal. Okay, it's just not dropping to 0. And this is the formula: number of photon pairs detected at a high delay. So somewhere here, any of these is good. Actually, we can average over many of them to get a better number. So we have this number of photon pairs at the high delay minus the number of photon pairs at the zero delay. And this difference is actually due to each emitter emitting 2 photons. This is the only prohibited event here. This is why it's described by the PSF of a confocal microscope squared. So I'm drawing this here again. Confocal microscope would be excitation times detection. Excitation red times detection blue in this picture. So this is the green blob line here. For each of the 3 detectors, it's displaced. But now for anti-bunching, we square it again, and we end up with even narrower point split function, which means higher resolution. So this, in theory, should lead to up to a factor of 4 resolution improvement. In practice, we observed a factor of 2.4. This is for a pair of quantum dots. And we also went on to demonstrate it in actual biological sample, microtubules labeled with quantum dots. This is a wide field image and region of interest chosen. This is a standard confocal microscope. This is image scanning microscopy, and this is quantum image scanning microscopy. So you see that there is a big improvement already here due to image scanning microscopy. But there's also an improvement in resolution here. You also notice that the SNR in the case of QISM is lower than in the case of ISM. And this problem was attacked by Dan Oron. So he and his coworkers have shown that you can actually combine the information acquired by QISM and ISM. You have this high SNR low resolution and low SNR high resolution pictures. They are complementary, and you can reconstruct the object better than just with ISM or just with QISM. And I would like to also point out that you acquire this data simultaneously. So you simply detect photon pairs, and then you choose what analysis you do. You either do standard ISM or QISM, or maybe there's actually a classical analog, right? If you work in quantum optics, you probably know that many of things you observe have classical analogs. So we asked this question. Oh, sorry, I went the wrong direction. We asked this question here as well. Is there classical analog of the QISM technique. So actually, the classical analog is older than the quantum effect, and it's called SOFI, Super Resolution Optical Fluctuation Imaging. This technique relies on the classical correlations of fluorescent light, which result from the fact that single photon, or that the fluorescent emitters blink. By saying blink, I mean that their intensity fluctuates. Okay, so if you consider a quantum dot, it's bright, then it's dark. You see that there will be a correlation here. So when you see that it's bright, it will most likely stay bright for some time. If it's dark, it will stay dark for some time. You can use this correlation because one dot is correlated with itself, but not with its neighbors if they are not too close. And these two images are pictures from the first demonstration, again by Enderlein, standard wide field imaging and SOFI imaging. Okay, but as with the quantum correlation technique, we wanted to demonstrate this in the confocal architecture, which is more relevant for practical applications. We are lucky with the acronym, so combining the name of SOFI and ISM results in sophism, which is easy to pronounce. And in the course of this experiment, we also switched from this very nice but very costly detector, which consists of fiber bundle and single photon detectors. We switched to a compact design, which is much cheaper, an array of single photon detectors integrated, developed in Switzerland by the Charbon group. So now it has practical consequences. You simply take a standard confocal microscope, you buy this detector, you put it in the image plane of the confocal microscope, and you're able to not only do image scanning microscopy, but also all the correlation-based techniques, as we show. Okay, so let's move on to the classical correlation microscopy. We have this array of single photon detectors. We pick two of them, A and B. Each of the detector, when you measure for a certain time at a given pixel, records fluctuating intensity. And you could simply average over these fluctuations. And then, for each of the 23 detectors, you will obtain shifted images. So we need to shift them back, which we call pixel reassignment, and sum them. Okay, this is called ISM. But you could also correlate the measured intensities at these two pixels, which I have shown here. And then you obtain 23 squared images. Again, you have to shift them and add them. And now the image is characterized by a higher resolution than the ISM image. Why? This is just a picture. Imagine two emitters. You cannot resolve them in their intensity image. But if you start looking at correlation, each emitter is very well correlated with itself. So here the signal will be higher, but not that much correlated with its neighbor. So in the middle, the signal will be lower. This is the intuition behind why the correlation leads to super resolution. And for the second order correlation or cumulant, this is called variance. Actually, for higher orders, one should look up what cumulant means, and one has to use cumulants and cross out some terms which wouldn't result in super resolution. But second order is the most practical, and then the name is simply variance. You record a movie instead of a single shot picture, and you compute variance in time at each pixel. You obtain super resolved images. Isn't this cool that you simply have to change the data analysis, make the measurements slightly longer, and you get super resolution? This is in contrast to the Nobel-winning super resolution techniques, which are more demanding in terms of data acquisition and experimental setups. Okay, these are our results for like a quantum sample made of quantum dots dispersed on a glass slide. Standard confocal, image scanning microscopy, quantum image scanning microscopy, and the classical version, SOFI ISM. You see that SOFI ISM and QISM look pretty similar in terms of resolution. Here are the cross sections, and they are not the same in terms of brightness. And this is an example of the fact that the classical fluctuations are a bit more complex than the quantum ones, that they really depend on the chemistry of the quantum dots. Anti-bunching doesn't really care about the details of your experiment, and the blinking is sensitive to many factors. So surprisingly, anti-bunching is more robust than the classical correlation in a certain sense. So we did second order SOPHY and obtained 2.5 improvement of resolution, and for the fourth order SOPHY, a factor of 4. You can look up the details in the archive preprint. Okay, and one more practical factor. So if you want to do 3D imaging, and obviously live samples or samples from life sciences are 3D, basically always. And to obtain 3D images, you need to have you need to use an effect that is called optical sectioning. This simply means that your microscope can reject light coming from layers of your sample which are not in focus. So we only want to detect light that comes from a slice of your sample which is in focus. And to see sectioning in theory, you can simply compute a 3-dimensional point spread function. So a 3-dimensional image of a point source. So this is, I plotted in 2 dimensions, the axial dimension, so along the depth of a sample, and one transverse dimension, call it x. So just for comparison, this is a Gaussian beam. And in ISM, you remember that we have to take the product of 2 Gaussian PSFs. We take Gaussian beams for simplicity. This is what you get. And in SOPHY ISM, you have to square this guy. So you square ISM PSF. And you see that this the PSF of the correlation-based technique shrinks in all the 3 dimensions. So, or in 2 dimensions of this picture, which is very, very important. You not only gain resolution in the transverse dimension, also in the axial dimension. And this is experimental data, excuse me, supporting this simulation. This is the data for SOPHY ISM. This is the data for ISM. Indeed, you get a narrower image of a point source. Okay, these are pictures of a biological sample, again, microtubule, labeled with quantum dots, ISM and SOPHY ISM after deconvolution. I would like to point out that one advantage of SOPHY ISM with respect to the quantum technique is that it already gives reasonable quality images at short dwell times, at the order of milliseconds, which is important for practical measurements. If you have a living specimen, you want to be fast in order to see the evolution of the specimen with time. So we analyzed the SNR as a function of dwell time, and we compared it for a couple of techniques: standard confocal, anti-bunching combined with ISM, SOPHY, and SOPHY combined with ISM, and SOPHY ISM wins here. And our intuition behind this effect is that if you measure SOPHY ISM with a detector array, each detector pair probes a given point in space at a different time. And because of this, you measure the correlation multiple times at different times. So you probe, maybe it's simpler to understand it in case of confocal versus ISM, which is plotted here. So you see here you have dark lines in the confocal scan, which mean that a given part of the sample or a given quantum dot turned off for some time, and there is a darker stripe. These artifacts are eliminated in image scanning microscopy because each detector looks at a given spot at a different point in time. So an analogous effect happens for correlation. This is why SOPHY ISM is much better than SOPHY simply applied to confocal with a single detector or with an open pinhole. Okay, now I'd like to, for the last 12 minutes that I believe I have, I would like to switch to the second part, in which I will try to convince you that photon correlations, photon correlation measurements are also useful for phase imaging. I mean interferometric phase imaging. Let me start with a question. So, do you believe, if you have two laser pointers or two laser and shine them in one spot on a screen, would you observe interference fringes? So would two different lasers interfere? And I unfortunately cannot hear your answers. I believe at least some of you would say no. Obviously, two lasers are not coherent, so they will not interfere. And this is not true. And it was demonstrated by Leonard Mandel again. He has demonstrated that two maser light beams, which basically means laser beams, can interfere if you're fast enough. These two lasers that you take in your hands, if they have the same color, the same spectrum, they interfere, but the interference fringes are just quickly changing in time. The phase between the two lasers is jumping from time to time. So with your eyes, probably you're too slow to observe interference, but if you have a fast camera, and Mandel built a fast camera, he could observe interference fringes. I really recommend this paper. You can have a look. Two lasers, fast camera, home built, and these are the results, interference fringes from two lasers. Okay, and he went on asking the question, if you can do this also at the low light level. This will be stable. He turned to a correlation technique with a very smart device. Like, he expected fringes of the size given by each fringe is as big as one of these glass slides. So if the fringes are jumping around because of the phase fluctuation between the two lasers, they can always go mostly to one of the detectors. And if you observe the anti-correlation between the two detectors, you prove the presence of interference. Okay, but back to the... okay, I just want to introduce one more thing. So Mandel had his own big camera. We built ours. We take the commercial CMOS camera, an image intensifier, and an imaging system between. This was first built by Wojtek Wasilewski and then also developed in our lab. Just a quick reminder what an image intensifier is. By the way, it wasn't developed for quantum optics, it was developed for different applications, unfortunately. So an image intensifier takes a single photon, on a photocathode turns it into an electron. Electron is multiplied in microchannel plate, and the cloud of electron hits phosphor screen, like at an oscilloscope in the old days. And this, as a result, a single photon is turned into a bright flash containing up to 1 million of photons. And this bright flash then can simply be imaged by your eye if you're a soldier, or by a CMOS camera in our case. You simply need to put a relay lens which would image the phosphor screen of the image intensifier onto the CMOS camera. Okay, so these are the features of our home-built camera. I will not get into details. I would like to just point out that we are not limited by the resolution of the CMOS camera. We localize each bright flash corresponding to a single photon detection with sub-pixel precision. And we can gate the image intensifier down to a couple of nanoseconds, which allows us to, for instance, detect coincidences from SPDC, or in general, photon pairs with high spatial and temporal resolution. So this is the scenario I would like to consider. You have an interferometer, Mach-Zehnder in this case. You have a spatial phase placed in one of the arms that I denote phi of x, and you would like to reconstruct this phase. Obviously, with an interferometer, this is not that difficult. You see interference fringes at the camera, and then you can apply digital holography algorithms to reconstruct the phase. But what happens if you have a fluctuation in the interferometer? Let's say the mirror is shaking. I denote this as theta of t, the temporal phase that is changing in time. Well, then you see your interference fringes for linear case shifting around. And obviously, if you weight an average over these fluctuations, you will see no interference, just the intensity profile of the original beam illuminating the object. Okay, so this is a problem. If you only have very few photons per the time when the interferometer is stable, you will not be able to see interference. Now, as you know from the title, I want to measure detect photon pairs rather than individual photons, or intensity correlation rather than intensities. So imagine we have two cameras at the two outputs, and we, instead of storing position of just one photon detection and plotting a histogram of it, we plot positions of two photons detected. Okay, one photon is detected at this camera, the other at this camera. We call position of one of them X and of the other X prime. And then after accumulating many such pairs, we can plot a probability distribution, joint probability distribution as a function of X and X prime, position of photon 1, position of photon 2. And this is what this will look like for a stable phase. You simply have to multiply individual intensity distributions, right? And this is how it evolves with the varying phase in the interferometer, just like in the case of standard interference fringes. But now the surprising fact is that if you average over many realizations of this random phase, you still recover interference fringes of a different shape than in the case of stable phase, but still this interference pattern contains the information about the phase introduced. In this case, this was quadratic phase. Here are some examples for linear phase, x to the power of 3 phase, and so on, just for the fun of it. And here is our experiment. So we have, instead of Mach-Zehnder, we have a polarization-based Michelson interferometer. We put a phase object in one of the arms. This was in practice realized by a spatial light modulator. And we put the random phase into the interferometer by moving one of the mirrors with a piezo stage. Okay. We work in the low light regime, such that in the time when this phase is approximately constant, there's just a few photons reaching the image intensifier. In such a case, you couldn't see interference fringes. Few photons is not enough to resolve fringes. But we catch photon pairs at the two outputs, and this is what we get. The joint probability distribution of the two photons. You see that it looks more or less like the theoretical prediction. The grid-like artifact comes from the structure of the microchannel plate of our camera. So the actual positions of photons detected by the CMOS camera after the image intensifier are discretized by the grid structure of the microchannel plate. And we see this here. We went on to demonstrate that we actually can reconstruct various phases introduced in the interferometer. The quadratic phase, with excellent agreement with what we introduce, denoted as sample, and what we reconstruct with the blue line. You might notice that the interferogram, the two-photon interferogram, is different than the one that I demonstrated in the previous slide. This is because we want to apply a digital holography method to our fringes, and we decided to use the method, which requires introduction of an additional linear phase. This is how the interferogram looks if you add the quadratic phase of the sample with the linear phase introduced by tilting one of the mirrors. Okay, this is the sinusoidal phase introduced by the sample. You see that we have some systematic errors. We believe that they come from the imperfections of the spatial light modulator, till the method works, and another example, exponential phase, again, some artifacts. Okay, I would like to thank all the people who contributed to the work I discussed. The first part on the super resolution microscopy was a collaboration with the groups of Professor Jaron Zilberberg and Professor Dan Oron from the Weizmann Institute of Science. The lead author of the quantum ISM experiment was Ron Tenne. And the lead authors of the classical fluctuation or classical correlation super resolution microscopy were Aleksandra Środa, Adrian Makowski, and Ron Tenne. The lead author of the photon pair-based holography or photon pair-based phase imaging was Jerzy Szuniewicz. I would also like to thank the funding agencies. Most of our funding comes from the Foundation for Polish Science. So in summary, I hope I have convinced you that with the advent of relatively cheap and compact single photon detector arrays, it makes sense to place them in your confocal microscope and detect quantum or classical correlation. This allows you to get super resolved images. And if you use photon pair detection in interferometry, you can gain resistance to phase offset fluctuations and perform phase imaging in conditions in which the standard methods based on intensity measurements fail. I would like to thank you for your attention and once again thank the organizers for the opportunity of giving a talk. I will be very happy to answer your questions. Thank you.
Thank you, Dr. Radik, for a very nice and informative talk and very great results. We'll take a few questions now. Subit wants to ask a question, and Subit, you can ask your question.
Okay. Hello, nice talk.
Thank you.
So my question is, so you are taking that correlation recording that interference image. So you are taking the photon from two beams from with two side. I mean, in a same CMOS camera pixel array. You are taking two different part of the sensor, right? CMOS sensor, right?
You're talking about the interferometry technique, right?
Interferometry technique.
Yes, that's correct.
Okay. So while doing the correlation, how you are recognizing how you are deciding that which two pixel need to be correlated? So or which pixel you normally correlate each other for reconstructing that final image, final interference image?
So we have the two outputs actually hitting the two areas on the CMOS sensor, as you said. And then we store positions of both of the photons, and then we can plot all the positions. We take all the combinations of position of photon 1 and position of photon 2, and you see this in the data, right? So we, in this one region on the camera, we collect all the positions, and in the other region as well, and we notice this correlation.
Okay. Thank you.
And if I may share the intuition behind this, why these fringes survive, although you're averaging over fluctuating phase, you imagine that the fringes are shifting around, but if you already catch a photon at a given position, you know that this is for sure not the dark fringe. So this modulates the probability of detecting the second photon. That's why if you cut this plot like this, choosing one position of one photon, you see the modulation.
At a given instance. At a particular time.
Yes.
Okay. We have another question from Professor RPC. Do you see advantage of using quantum illumination in microscopic imaging in near future?
So sorry, could you repeat it? Do I see what?
Yeah, sure. Do you see the advantage of using quantum illumination in microscopic imaging in near future?
Mm-hmm. So. I'm not that familiar with the let's say the standard quantum optical techniques practically. I mean the ones that I introduced first, like that you shine the quantum state of light onto the sample. So it's hard for me to comment, especially about the quantum illumination. But I understand that this is the scenario you're asking about, that you generate a quantum state of light, you shine it onto a sample and detect correlations. But I believe that the fact that the detectors improve so much means that these techniques could become practical relatively soon. I think the biggest concern is that some of them are sensitive to losses, and I think you should expect losses in practical applications. But yes, I think until someone demonstrates this, it's really hard to comment because it's hard to predict which problems might be killing your application.
Okay. I have a question. So when we are doing this ISM, what are actually the factors which are affecting the resolution over there? Is it the coherence or is it the quality of anti-bunching?
Okay, so in our case, if you measure long enough, so if your dwell time is long enough, you can get good SNR, even better than demonstrated at this picture. So if you don't limit your measurement in time, you should get the theoretical improvement of a factor of 4. In practice, we actually don't want to measure very long because the system is not stable. The stage is fluctuating, the laser intensity is fluctuating, so you're limited to like times of even like 100 milliseconds, not much longer than this. And then you see that the SNR is not perfect. I think this is the limiting factor. So actually the number of missing photon pairs that you detected. So the Poissonian noise on the number of photon pairs that you detect, this is the limiting factor, as far as I understand.
Okay. A follow-up question over there. When we are using a source which is carrying missing photons for the imaging technique, you can either have an ideal single photon source like the quantum dots that you're using, or you can use probabilistic sources as well, right? Like heralded single photons. Would there be, are you familiar with that? Would there be any difference using these two different sources?
So for me, it's hard to imagine what you would mean by heralding in this case, like in microscopy, because I imagine it,
or using as a source.
You mean to illuminating sample with single photons, or?
Yes, as the illuminating source that you're using, where the missing photons
are. So I believe, yes, there were pretty important works in this case. If you want to measure transmission of your sample very precisely, it is very advantageous to use a definite photon number, for instance, heralded single photons. Then you can, yes, if you do this with high enough efficiency, as far as I understand, you can beat the shot noise of your measurement. So this would be this line of application where again you prepare the quantum state of light and shine it onto your sample, and then you gain in absorption sensitivity by having a definite photon number. So yes, I think there are also such applications, and in recent years there were a couple of demonstrations.
Okay. So I think we do not have any further questions. So let's thank the speaker, Dr. Rajeev, once again.
Thank you very much.
Thank you. Thank you. So with this talk, we have come to an end for the technical sessions for today. I want to once again thank all of our speakers and the audience for being present and asking wonderful questions. We'll now have a virtual tour of 3 different optics and photonics laboratories in PRL. And following the virtual tour, we'll have the public lecture by Professor Andrew Fox. Now I welcome all of you to the virtual lab visit we have arranged for you now. Over to the host.
I am giving you the overview of research activities of this lab. The area of research of this lab are probing the molecular wave packet and understanding the conical intersection, molecular alignment and photoionization interferometry, laser-induced electron diffraction, higher harmonic generation and Attosecond research. For such kind of research, we have developed various experimental techniques. For example, we have developed the pump probe setup, we have developed the velocity map imaging spectrometer, reaction microscope, and higher harmonic generation setup. We are currently working on developing attosecond beamline for attosecond research, as well as rabbit experiment. Our group member is going to explain you these techniques in more details.
Hello, I'm Vinita. I'm here to talk about the femtosecond laser facility in our lab. To study electronic and nuclear dynamics in atomic and molecular systems, we need ultrafast source. So we have femtosecond laser in our lab, which basically consists of an oscillator and an amplifier. This oscillator is mode locked using a saturable absorber, which uses the passive mode locking technique. The output of this oscillator is 600 milliwatt power and 25 in femtoseconds pulse duration and 80 megahertz frequency with 800 nanometer central wavelength. The power output from the oscillator is not sufficient for carrying out ionization experiments, so we need a high power laser output. So we use a Chaudhary amplifier for that. This basically has 3 stages of amplification. One is stretching, other is amplification, and then compression. So in stretching, this 25 femtosecond laser pulse from the oscillator is used as a seed pulse, and it is being stretched to picoseconds. After that, it will be sent to the regenerative amplifier and then to the single pass amplifier, where the isopile crystals are being pumped by the ND-YLF 527 nanoseconds pump lasers. After the amplification, the stretched pulse should be compressed. So it is done by the optical gratings in both the stages, stretching and compressing, but in the reverse way. After the compressed pulse will be of 25 femtosecond duration, and the power output will be 10 watt. So when these laser pulses, when they travel through any medium, there will be some carrier envelope offset, which is the phase difference between the carrier wave and the phase wave envelope. So to compensate that, we will be using CEP stabilizers, which are like one for the oscillator and other for the amplifier. To study about wavelength dependent properties, we will be using optical parametric amplifier, which is a difference frequency generator, whose signal and idler wavelengths range from 1330 nanometers to 2200 nanometer, which gives us a huge range of wavelength tunability.
Hello everyone, my name is Bhattacharya. I'm a doctoral student at PRL. My research interest is temporal studies of evolution of molecular wave packet and conical intersection. To do these temporal studies, we have a probe setup, which is on a stage of accuracy of 1 micron. So the resolution of 1 micron in the time scale will be 3.3 femtosecond. We can have molecular systems studied in that resolution range. So this probe setup has been coupled with our velocity map imaging spectrometer, which has a gas valve, which has a piezoelectric gas valve operating at 1 kilohertz with an opening time of 20 microns. So this piezoelectric valve generates supersonically cooled gas, and that is being passed on to the 11-plate velocity map imaging spectrometer. So this 11-plate velocity map imaging spectrometer behaves like an Einzel lens for the mass spec for the ions or the electrons that are involved in the ionization region. These ions or electrons, based on their potentials, are driven towards the detector. There is a microchannel plate detector with a phosphor screen. This, according to the potentials, this spectrometer can behave like an ion imaging spectrometer or a time of flight like spectrometer.
Momentum spectrometer setup in our lab. This is a 4-target recall and momentum spectrometer. generated as a result of the interaction and in correlation. This setup has two chambers. This is the supersonic molecular jet chamber, which is connected to a gas cylinder. The gas, which is to be studied in the experiment, enters the supersonic jet chamber and undergoes supersonic expansion due to the low pressure maintained in this chamber, which is of the order of 10 to the power -7 to -8 milligrams. Due to the supersonic expansion, the molecular beam undergoes a cooling to temperatures below 10 Kelvin. At the end of this chamber is situated a skimmer of diameter less than 1 mm, and this skims the molecular beam and selects the central part of the beam which has the lowest velocity distribution, which is the pole target. From here, the pole target then enters the second chamber, which is the Coherence chamber. This is the Coherence chamber, where the molecular beam interacts with the intense and ultra-short laser pulses. As a result of the interaction, positive and negatively charged particles are generated, that is the ions and electrons respectively, and they are then separated by a series of annular rings or electrodes to the two opposite ends of the chamber. At both the ends are situated detectors, which are a combination of MCT and CSDLD, which basically stands for microchannel plate detector and position sensitive delay line detector. These two detectors together give us the time of flight information and the position information of each ion and electron infiltrate on it. From this information, we can reconstruct the complete three-dimensional momentum information of the ions and electrons in correlation. This setup can be used to perform a number of studies like the time resolved ionization and dissociation processes in atoms and molecules, intramolecular migration of moieties, molecular frame photoelectron angular distribution, photoelectron circular dichroism, and many more.
Hi, I'm Pranav. I'm a third-year doctoral student here at PRL, and I'm currently studying higher harmonic generation or HHG in gases. HHG provides us with a tool to convert femtosecond pulses into XUV. Therefore, HHG provides us with a tunable, tabletop, ultra-short XUV laser pulses. XUV generated in this way can either be directly used in atomic and molecular physics experiments, particularly inner shell ionization-based experiments, or it can be used to generate attosecond pulses. Attosecond pulses are currently being routinely utilized by scientists to observe and control chemical reactions on a molecular level. This is quite interesting because then one can observe electrons hop on from one atom over to the other during the course of a chemical reaction, all in real time. Now we will briefly talk about the experimental realization of the HHG cell. The 25 femtosecond 800 nanometer pulses that we have interact with gas in this very unique chamber which houses an optical. Gas can be operated both in continuous or pulse mode, but currently we are planning on using a continuous gas source which will be passed through a needle valve for greater precision and control. Gases used for generation of HHG are typically xenon, argon, or krypton, or neon. When the XUV is generated by the interaction of pulses with gas, it is then passed over to the aluminum filter to block out the incident 800 nanometer radiation to avoid any damage to the optical components. The pure XUV beam is then passed on to a diffraction grating inside, which splits the XUV into its various components that can be directly observed on an XUV camera. To perform the ionization-based experiments, one can then select the harmonic of choice and then send the beam directly either to the Coherence chamber or to the PMI chamber, depending upon the study of interest. Thank you.
Hello everyone, welcome to the Photonics Science Lab. Myself Raghwinder Ghosh. I am currently working as a scientific assistant here. So in this lab, we try to focus in two different fields. Firstly, we try to do nonlinear frequency conversion of various structured beam and try to generate such beams in various time domain ranging from femtosecond to CW, as well as in various spectral domain ranging from ultraviolet to the mid-IR range. Also, we have a quantum section where we try to generate high brightness entangled photon sources, which is various application ranging from quantum communication to quantum metrology and so on.
I'm working as DST Inspire faculty here at Photonics Science Lab. My project mainly focuses on generating structured terahertz beams by using difference frequency generation in nonlinear organic crystals such as DST-MS. This lab mainly focuses on structured beams such as optical vortices, airy beams, hollow for alignment, tunability, and high damage threshold of Attosecond, which allows us to generate optical bottles of high potential barriers, which enhances its overall applicability. And we are also studying the nonlinear wave mixing characteristics of such beams by using this nonlinear birefringent crystal, this triborid. And we are also trying to verify its various properties. For example, the self-healing property. As you can see here, when we block the beam by an obstacle, the beam heat itself over a distance of around 60 millimeters. So such beams can be used for various applications, such as for the optical trapping of atoms, and they can be used for the manipulation, guiding, and binding of microparticles and biological cells, and they can be also used as erase beams in super resolution high fluorescence microscopy.
Hi everyone, my name is Sandeep Singh and I am a chair of in Photonics Science Laboratory. And this is the quantum section of our lab, and here we are exploring the quantum nature of light through various experiments. Currently, we are doing a single photon characterization and coincidence imaging. Since single photon sources are very important for quantum communication, quantum metrology, and to test various fundamental phenomena of physics. So we are generating a single photons and we are characterizing that. So for that purpose, we are using this 4.5 nanometer CW laser, and we are pumping this laser through this type 0 ppKTP crystal, and we are creating a hierarchical single photon source. And to characterize that, I am using Hongo-Meyer interference in my setup. So as an outcome of the setup, I am recording the coincidence count of detected by these two detectors. By calculating the maxima and the minima of the counts, you can actually calculate the visibility of your interference experiment. And if your visibility is very close to 1, then you can say your single photon is the ideal case. And how much it is deviating from 1, you can characterize the single photon in terms of that. And this experiment is also very useful for nanosensing experiments, like in high precision timing measurements, in very highly sensitive gyroscopic experiments. So we have that kind of future plans.
Hello, myself Biswas. Currently, I am working on coincidence imaging using indoor ICCT camera. In classical, if any beam is carrying orbital angular momentum and having donut self-intensity profile, is called vortex 1. For this simplicity, I will be saying orbital angular momentum as a OM. So if any beam is carrying OM, we can characterize it using some simple techniques like tilted lens, self-interference, like that. If we move to the quantum domain, if that photon is carrying orbital angular momentum, then we characterize its charge using tilted lens technique. So we try to devise simple experimental scheme. Let's see what it is. So using 405 nanometer diode laser, we are pumping in type 2 SPTC crystal, through which we are generating photon pair. So using this scheme, we are moving from classical domain to the quantum domain. Using some experimental manipulation, we are transferring the pump vortex charge to the photon, which is carrying the orbital momentum of the pump. So after that photon is carrying the orbital momentum of the pump, they are trying to measure its charge using tilted lens technique. So in the pump, we see, suppose we take vortex of charge 3, using tilted lens, we see that it will have 4 lobe structure, confirming the presence of order 3 vortex. If we move to the photon level, we see the intensity profile in the ICCD camera. Using tilted lens, we are seeing the similar 4 lobe structure. This is confirming that it is carrying the order 3 structure.
Myself, Kumar, I am a senior research fellow here in Photonics Sciences Lab. This is our Ultrafast session.
Currently, we are doing the nonlinear interaction of vector beams. Vector beams are light beams with a specially varying polarization. Due to the polarization dependence on phase matching condition, these beams will lose its specially varying polarization property after nonlinear frequency conversions. At present, we are trying to do the second harmonic generation of a full point carrier beam. Full point carrier beams are a special kind of vector beams that theoretically can carry all possible polarizations. For doing that, we are creating a full point carrier beam at 810 nanometer by using high peak power light pulses from this disphere oscillator. Later, by using a dual behavior crystal system, we are doing the second harmonic of this full point carrier beam. Full point carrier beams have various applications ranging from micro manipulation to optical communication.
Our group leader is Professor Raghwinder Singh and I am Tanya Sharma. I would like to invite you to the virtual tour of our lab. It consists of 4 10,000 class clean labs, and these labs are dedicated to quantum optics and quantum communication. For these we require quantum sources. So this lab mainly works on heraldic single photon sources, and these 2 labs work on big coherent pulses. This lab is dedicated to DBQKD, and here this lab would be dedicated to the future endeavors in continuous variable quantum key distribution. So I'd like to invite you on the first visual tour.
Hello everyone, I am Anu Sharma. This is our quantum optics lab. Currently we are doing 2 main experiments here. One is homomodal interference and another is duality in entanglement. Now to perform such experiment we require single photon source, and heralded single photon source basically. To have such single photon source we use spontaneous parametric down conversion processes, where what happened when pumped photon is incident on a non-linear crystal, it will generate 2 photons of lower frequencies. Now these photons they are generated are basically entangled in different degrees of freedom. That can be polarization state of a photon or orbital angular momentum of the photon. Now Sarika will explain how these photons can be used.
So hi, I am Sarika Mishra. So in this experimental setup, we are demonstrating homomodal experiment, which is basically a 2-photon interference. So in this technique, we are testing the indistinguishability between 2 photons. So generally, when the 2 photons enter onto the beam splitter, they can be anti-bunch or bunch. But when the 2 identical photons are entering onto the beam splitter, they can only show the bunching effect. So this is the idea of homomodal experiment. So in our experiment, we have used a light beam of wavelength 405 nanometer. So then the light beam pumped to the nonlinear crystal. Here we are using type 1 video crystal. So it will create, because of the spontaneous parametric down conversion, it will create 2 photon signal in the island. And then these 2 photons will go through the 2 different optical paths, and at the one of the paths we have introduced the delay stage. So when these 2 photons are entering into the beam splitter, they will couple into the 2 different output ports. these two different output ports are coupled into a single mode fiber, and these two single mode fibers are connected to the SPCM, which is single photon counting module. It will detect the photons. So this is the experiment for fundamental experiment. Along with that, we can also generate entanglement in different degrees of freedom. So here is the next experiment where you can see the entanglement.
Hello everyone, I am Nijil. So you have already seen that quantum entanglement is possible in different degrees of freedom when you pump a nonlinear crystal with blue light over there, blue laser, right? So here what I'm showing is that in the previous experiment you have seen that both of these photons are generated in different directions. They are carrying different linear momentum, different directions. But another class is important where both of these photons are having the same linear momentum and they are indistinguishable in all parameters or all degrees of freedom. So here we have a type 2 periodically polled crystal from which two photons are being generated collinearly and they are coming together along this line and they are entangled in polarization, orbital angular momentum, etc. independently. So such indistinguishable photons are particularly important in different quantum information algorithms. So we are studying a particular quantum property of these photons, which is the duality of entanglement. So what we are showing here is that if these photons are being projected in one of these degrees of freedom, then the entanglement in the other degree of freedom would be visible, which would not be the case since they are indistinguishable. So you need 1 degree of freedom to label. So if they are separated in polarization, then the entanglement in OAM is visible. If they are separated in OAM, their entanglement in polarization is visible, and vice versa. So to detect these very faint photon outputs, which is happening at 810 nanometer, we have a electron multiplying charge coupled device over here, EMCCD. So this is what we generally use to take images of these very faint SPDC output. And we have spatial light modulators, SLMs, as you can see over here. They are basically LCD arrays which can manipulate the transverse phase of the input beam. So these are being used for OAM projections, etc.
Hello, now let's look into some experiments based on weak Coherent pulses.
Hi. In this lab, we work on weak Coherent pulses. As described by my colleague Nijil, the process of single photon generation was through SPDC, heralded single photon source. Here, we use weak Coherent pulses. Weak Coherent pulses can be visualized as attenuating a laser to a single photon level. My colleague Satya will describe it in more detail and the experiment he is working on.
Yeah. Hi, I am Satyajit. As Vardhan said, that weak Coherent pulses can be obtained using pulse laser. We use femtosecond pulse laser of repetition rate 80 MHz and pulse width of 16 femtosecond. By attenuating these pulse laser, we can obtain weak Coherent pulses such that in one pulse there is one photon on an anode. So using these weak Coherent pulses, we generate classical non-separable state as well as using a continuous beam, we can also obtain the classical non-separable state. In classical non-separable states, like quantum entangled states, these states also violates the Bell's inequality. So it mimics, these states mimic the many quantum mechanical protocols. One of them is super dense coding. In super dense coding, 2 bits of classical information is encoded in a single qubit. So this is the setup of super dense coding, in which we are using a laser and we are setting the polarization of the beam to the diagonal polarization, and using this interferometer we are generating 4 Bell states, and these Bell states we are transmitting to the another party which will discriminate between these four states, so that 2 bits of information will be sent by the single figure. Yeah.
Now let's see the applications in quantum key distribution using the protocols.
Hi everyone, I am Pooja Chandransi, and as you have seen that we use coherent weak pulses in our lab. So this is quantum key distribution lab. Here we work on different protocols of QKD like BB84, B92. Now Ayan will tell more about it.
Hi, I'm Ayan. So quantum key distribution is basically it's sharing a secret between two different parties, say namely Alice and Bob. So this sharing of secret key or password is done basically by the method of by implementing the method of quantum mechanics, which is makes this key exchange protocol as inherently secure. So one of those protocol is BB84 protocol. So BB84 protocol basically is that Alice randomly generates 4 quantum states and send it to Bob. Bob, on the other hand, it makes random measurements, and after that they both talk over a public channel and they match their results correspondingly they make what is called as a key. So now we focus into the experimental setup. Here this is a field programmable gate array, which is basically randomly generating the pulse, and this random pulse are fed into 4 laser drivers. So after that, these laser drivers are used basically for preparing in 4 random quantum states, and these are called half-wave plates, which generally sets the polarization into desired quantum states. Then all of these are mixed into this beam splitter, and then they combine here and they are sent via free space channel to Bob. Now, okay. So here in this box, this is a typical Bob's measurement setup. So this is a 50-50 beam splitter, which is acting as a passive random selector. 50% of the time photons will hit in horizontal and vertical basis, and 50% of the time photon will hit in diagonal and anti-diagonal basis. And all these photons are coupled through multimode fiber, and then they are fed into what is called as the avalanche photodiodes. Then they are then their timing is recorded by this timing electronics, and after that we can record the arrival time. Then we can match both the time of Alice and Bob, that what time Bob has received and Alice has sent. From that we can make this secure quantum.
Thank you.
So that was the end of the virtual lab 2. We are running a little behind in time. So next session would be the public lecture. I invite Dr. Gautam Samanta to chair the public lecture session and introduce the speaker.
Okay. Good evening, everyone, and thank you for your presence in today's public lecture through webinar mode. I, Gautam Kumar Samanta, is working in the field of nonlinear optics and quantum optics in the Physical Research Laboratory, Ahmedabad. Have a privileged task to introduce our speaker. Light has been an essential element of existence since the earliest day of human life. Light has dual properties, wave and particle nature, as required to explain different phenomena. As Albert Einstein wrote, quote, "It seems as though we must use sometimes the one theory and sometimes the other, while at the times we may use either. We are faced with a new kind of difficulty. we have two contradictory pictures of reality. Separately, neither of them fully explain the phenomenon of light, but together they do. In present time, we made light as a measuring tool for different scientific and technological applications. Today, we are honored to have a speaker whose experience and background will enlighten us about the shaping of waves. After graduating from the University of Natal, South Africa in 1998, our speaker has spent several years working as an applied laser physicist, first for the South African Atomic Energy Corporation, and then later in private laser company. In 2004, he joined the CSIR, National Laser Center, where he was chief researcher and research group leader of the mathematical optics group. In March 2015, he joined the University of Witwatersrand as a distinguished professor and has established a new laboratory for structured light. Our speaker chairs and serves on committees of several international conferences, OSA and SPI committees, and serves on the editorial boards of Optics Express, AVS Quantum Sciences, and Photonics X, as well as editor-in-chief of UK's Journal of Optics. He is active in promoting photonics and popularizing science, a founder member of the Photonics Initiative of South Africa, a fellow of both SPI and the OSA, and elected member of the Academy of Science of South Africa. In 2015, our speaker won a national award for his contribution to photonics in Africa, and in 2020, the George Foster Alexander von Humboldt Prize. Like other scientists, like we do, our speaker also spends his time having fun with taxpayers' money and exploring structured light in classical and quantum optics. With these words, it's my pleasure to present today's speaker, Professor Andrew Forbes. It's all yours.
Oh, thank you very much for the very kind introduction. Didn't have to say all of that, but thank you for doing so anyway. Let me share my screen and then I can get the talk going. So let me do that for a second. All right. So hopefully you can see my slides. If I don't hear any complaints, I'll assume that it's all okay.
Yes, perfect.
Right, so I asked the students before agreeing to this talk who the audience might be, and they told me, well, it will be mostly students, but could be undergraduate, could be postgraduate, could be members of the public with no scientific background. And so what I've tried to do is to have ingredients in the talk that will allow everybody to take something out, even if not everybody takes everything out. But you are welcome at the end to ask me more detailed questions if you feel I glanced over the physics a little bit too quickly, or if I didn't go into the level of detail that you maybe have wanted me to do. So I thank you once again for inviting me here. I always like to give talks in person at different venues around the world, and it's a little unfortunate that I can't be in India. I actually love going to India. But let me begin, as I always do, by telling the audience where I'm from. So I know that India, most people from India are very familiar with where South Africa is. You know, we're also a cricket playing nation, and so you know us very well. But here we are at the bottom of the African continent. And in fact, I grew up in Durban. Durban is a coastal town. In fact, I would say maybe 60% of the population of Durban is Indian origin. So I studied there. It's a surfing town, lots of beautiful waves, but not the type of waves I will be speaking about today. And then I moved up to Pretoria, and for a long time I worked at a big laboratory there, very similar to your CSIR, something like that. I have an honorary professorship
Sorry, Professor, I'll interrupt you. Can you just push your camera? Yeah, thank you. Thank you. It's fine. Your camera was removed.
Oh, sorry. All right. Yeah, so I also go down to Stellenbosch on a regular basis. That's down near Cape Town. It's a very beautiful part of the country. If you haven't been there before, you really should try to go. And today I work in Johannesburg. So this image that you see here is Johannesburg at night. It's the financial center of South Africa. And in fact, maybe what it's a little bit better known for and a little bit more prettier is that it's the largest man-made forest in the world. So here is an image of Johannesburg when you're looking out from the city and you see the beautiful trees in the suburbs. But my university is inside the city. So you have to come back into the city, and then you find the University of the Witwatersrand, which we call WITS for short. It's a Dutch name. And this is the Great Hall. It's about 100 years old, the university. And if you come a little bit to the left of this Great Hall, you find the School of Physics. That's where I sit. And inside the School of Physics is my lab. And as many of the people in the excellent labs that we've just seen will know, then this is a very typical photonics lab. And I work, of course, in structured light. Now, traditionally, I would do structured light with digital holograms and spatial light modulators, but these days we use a variety of tools. Many of them, actually, we just saw in this beautiful lab tour that we had a few minutes ago. So what do we do with our structured light? In my group, our interests are extremely wide, everything from geodesy to imaging and novel lasers and so on. Lots of exciting things. And in today's talk, what I'm going to speak about is what do we mean by structured lights? And can we generalize the notion of light to waves? And what does that mean for the type of physics that we could really do? So I'm going to start by giving you my cartoon version of what we do in our research area. And it's actually extremely simple. I always feel that everything you do should be simple. You should be able to explain it to the public, because at the end of the day, those are the people who pay us to do what we do. So what is it that we do? So hopefully you can see my little my little pointer moving around, because Macs don't allow you to have a laser pointer for some reason. So imagine I have some laser beam, and imagine it looks like this picture on the left. Now, if you work in photonics, you will know that this is a false color image of a Gaussian beam. So the color represents how much light there is. And so for members of the public, if you're out there, it means that there's a lot of light in the middle and it decreases as you go to the edge. And you see it's basically a round blob of light. Something I'm going to make it a nice smiley face. And I can summarize all the research I do with this little cartoon equation. And what the equation says is, given that I have this field here on the left, and given that I would like to convert it into this field on the right, what optical elements or transformation should I execute in order to do this? You know, what do I need to put here to convert the round blob into the smiley face? And there's two parts to the problem. The one is to calculate what the answer is, and the next one is to work out how to implement that answer. So in the little panels that you see below, I actually show implementation methods. So we could do it by amplitude masks or meta surfaces or diffractive elements or holograms. You don't have to worry about the details. Just know that once you could calculate this element, then how you implement the solution, there's many, many ways you could do it. So for example, you know, the favorite method in our lab is to use liquid crystal displays, very similar to probably your television at home. It would be a liquid crystal television, I'm sure. And we display the answer to this problem on this device. And if we bounce our blob of light off it, you can create any structure you like. So here you see Angela. She's one of my former students. And she has a blob of light coming into the device. And here going out, you see that there's a beam with a hole in the middle. You'll understand a little bit later that that's a vortex beam. It's like the water that whirls down your sink, the plug. Well, the light is whirling around this central hole. And so in general, I can actually create anything I like. So it doesn't have to be a smiley face. It doesn't have to be a beam with a hole in the middle. So long as I know how to do that calculation, I can now calculate any pattern of light that I like. And here you see one of my master students has put together a little movie. Hopefully you can see it. And these are experimental images showing you all sorts of exotic patterns of light. And we call these patterns structured lights. Okay, let's go back to the cartoon again. So how could I do this calculation? How could I work out what the answer has to be? Well, one thing I could do is I could say, well, look, why don't I do the following? Everywhere that I don't want light in the smiley face, let me just block it out. And everywhere I do want light, let me just let it through. You can imagine a little piece of glass where I've used a black Koki and I've done this blocking out of the light. Well, that would work, but I would lose a lot of light. So we don't tend to do that. Another way to do it is to use a property of light called phase. And I'm going to explain what that is in the next slide. But for now, you can imagine it like this. Everywhere I don't want lights, let me try to make it so that when the light arrives there, it cancels out. And everywhere I do want lights, let me try to make it so that when the light arrives at that point, it adds together. So how can I make light sometimes add and sometimes subtract? Well, to know how to do that, you need to know what we mean by the phase of light. So light is a wave, and here you see lots of little squiggly waves that I've drawn on the slide, but you see that they're not exactly aligned. And if I were to join the dots like we get our children to do at primary school, then I would join the dots like this, and you would see that there'd be some funny surface. So these points would represent the same point on each wave, but because the waves are not aligned, there would be some weird curve. This is the wavefront of the lights, and it tells you the phase. But there's a simpler way to understand the phase. So imagine I take two waves, and I look at the peaks. Well, if the peaks are aligned, then the light at those points will add because I have one peak adding to another peak. But let's say I moved one of the waves so that now a peak of the one wave was aligned with the trough of the other. Well, it turns out that the trough of the bottom wave, the field points downwards, and now I have something going upwards and something going downwards, and they cancel. And so you see, by just moving where we are in the wave, I can make the waves add up, or I can make them subtract. And this moving of waves is what we call controlling the phase of the light. So it's the phase that matters. And in fact, this is not a new idea. So Thomas Young, a little bit more than 200 years ago, already started to look at this. And what he did was, and these are actually images from his paper, what he did was he took two simple pinholes, so he let light go through two little holes. And because the path length was different for each of the two holes to a screen, the arrival of the wave, its position would be different, and so the phase would be different. And so he speculated that, well, that means that you would see bright bands in some places and dim bands in other places. So here would be a calculation of what he would have said at the time. So we call these fringes. So fringes means intensity, where the light goes very bright and then the light goes very dark. And the way you get these fringes in intensity, is by simply passing the light through two little holes or two little slits. And then you will see these fringes. And because in this case, we have, I'll come to that in a second. Okay, so Young did it with physical slits. You can imagine taking a piece of cardboard or a piece of metal and cutting two holes inside it. Today, we can do the same thing digitally. So when I told you earlier that I display my answers on a liquid crystal display, much like your television, well, actually, here is an example of such a device from our lab. And you see this little screen here is the liquid crystal screen. It's about the size of my thumb, more or less. And I display my answer on this, and we call it a digital hologram or a computer-generated hologram. Because instead of a conventional hologram where you actually interfere light and make a 3D object, here the entire hologram is calculated on your computer. So let's say that I wanted to have a hologram that would let light through on the white regions over here and not let light through on the black regions. That would represent Young's original experiments of 2 pinholes. So light is going to pass through the 2 holes. Well, for the rest of this talk, you are going to see grayscale images where the color varies from white to black. Now I want you to imagine that a white color and a black color is just how much I'm moving the wave forward or backwards. And so the equivalent of getting this type of function is a hologram that looks like this. So now what it means is that I can do Young's experiment, but I can do it digitally, just with pictures on a little screen, rather than physical slits in a piece of cardboard or a piece of metal. So for example, here are some holograms where I can change, the separation of the 2 slits. And if I look on a camera, and here are some fringes, and hopefully the movie plays as you watch it, then what you see is that, of course, the fringes change their separation. You see they get closer and closer together. And what am I doing? I'm changing the hologram to make the spacing of the slits, wider and closer together. And you see that the slits are in the horizontal plane. And so that gives rise to fringes in the horizontal. And now I can ask you a question. Well, let's say I didn't want fringes in the horizontal, but I wanted them in the vertical. So the fringes going this way. Well, then you can imagine that all I would have to do is take my 2 pinholes and move them into the vertical. And so now for the students in the audience and not the members of the public, what would I have to do to get radial fringes? So a radial fringe means that the fringes are not in the X or in the Y, but in fact they're going out in a radial direction. So I'll give you like 5 seconds to think about that. And while you think about it, I'll play the video. So here is the equivalent of the hologram, but what I actually want. And on the left is the experimental camera that's recording what you get as you change the hologram. Now you see that to get radial fringes, I have to put lots of little slits around the circle. And as I go closer and closer to joining all these slits, I wonder if it will play again. As I go closer and closer to joining the slits, eventually I get an annular ring. And when you get an annular ring, you have a Bessel function. For the members of the public, you see that the symmetry of having lots and lots of little slits around the circle gives me fringes in the radial direction. And so I can control the geometry of the fringes and do things that Young could not have done a long time ago. And here you don't have to worry about the details, but I can get fringes in the azimuth. So going around the circle, I can also see fringes if I pick the holograms correctly to do that. So we can generalize Young's experiment and do lots of cool things. Now, like the last invited speaker, who asked a very good question about what would happen, would you see interference if you had 2 different laser beams from 2 different sources? Now let me ask you a similar question. Why is it that we see fringes in the first place? Well, it's because it was possible that the electric fields canceled because one was pointing upwards and the other was pointing downwards, and so they can cancel each other out. And at the time, this idea of the wave nature of light was highly controversial because of this fact. Because what this says in simple English is that it's possible to take some light and add some more light to it, and the result can be darkness. And that was highly counterintuitive at the time that Young was doing his experiments. Now I ask you, imagine that I have orthogonal lights. Is it possible to see fringes where the electric fields are always going to be at 90 degrees? Now, your first answer might be, well, no, because just from Pythagoras, the only way I could make the hypotenuse 0 is if I had the trivial case that both the electric fields were 0. In other words, I have no light anywhere, and therefore the sum of that is also no light. Well, that's not very interesting. But is it possible to have lights and see fringes? So if your answer was no, you're half correct. And if your answer was yes, you're also half correct. The answer is yes, you can see fringes, but not in the intensity of the lights, not in how much light you've got. So if I repeat Young's experiment with light that's always at 90 degrees to one another, so one slit is always in the vertical and the other slit is always in the horizontal, I see fringes, but now the fringes are in the polarization structure of the light. So it turns out for the members of the public that light can have a direction, and we can follow this direction, and what we see are fringes in the direction of the light, in a colloquial way to think about it. So here we see that we can, in fact, if I zoom into it, we can in fact see fringes, but you need to know where to look for those fringes. You won't find them in how bright the light is. So if I go to the laboratory and I do this experiment with orthogonal lights, sure enough, what I see on the screen is just a blob of light, no fringes. Remember, fringes are bright and dark bands inside the lights. But we maintain that there must be some fringes in the polarization structure. So how could you see it? Well, if you put a polarizer in front of this, the blob of light that you see at the bottom will convert into fringes. And if I change the polarizer to a different direction, the fringes will move. And if you're a member of the public, because this is meant to be a talk both for the students and the public, there's a very nice way to do this experiment, and we do it in our lab for school children. So, you know, if you've ever been to to watch a 3D movie, they give you some fancy glasses. What these glasses do is they change the polarization lights. And so, in fact, if you put on these glasses and you close one eye, you'll see the fringes at the top. And if you close the other eye and open up the one you had closed, the fringes will shift to the one at the bottom. And if you take the glasses off, you just see the blob of lights at the bottom left corner. So we can find fringes in the polarization of the lights. And now I have another question for the students in the audience, the undergraduate students. So there's one way to think about the fringes that we see, and that is that the slits that we have give rise to some uncertainty in linear position. And so the fringes give rise to uncertainty in linear momentum. So if I close off, if I make my position really, really known by narrowing down the slits, then my momentum becomes really unknown and I have a whole variation of them. So what do you think, where would you have to look for fringes if instead of two linear slits, I gave you two pizza slice slits? So imagine I have two pizza pie splice angles in my screen, and I let the light go through, and I can make the pizza slice very big or very thin. Where would I look to find the fringes? So if the normal slit is in linear position, then this is like a slit in angle. So we could call it an angular position. And it turns out that you find it in the angular momentum. And so if I do such an experiment, and the details are not so important, indeed what I see is that I have these, again, you see the telltale signs of fringes. And so I have this oscillation, and not how bright or how dim, but here how much or how little I have in the orbital angular momentum of the light. So fringes can be found in many, many, many places, but you need to know where to look. Okay, so if I come back to my cartoon, I think some of the students will probably at this point be quite happy and they will be understanding what I'm talking about. And some members of the public might be saying, well, I still don't know what the hell this guy's on about. So let me try to go back to the cartoon. And this time I'm going to explain it to you in another way. And I'm going to go back to an example that for sure you know about, and that is a lens. So I'm going to ask the question, how do lenses really work? So the way that you might think, if you have read a little bit about them, is that what lenses do is, of course, they focus light. And so they bend all the rays of light that come into a point, a common point, But they do it in a very special way. They make sure that all the light arrives at this point at the same time. So how do you make it all arrive at the same time? Because you can see that this path length over here is definitely going to be shorter than this one over here. Well, what you do is you add a little bit more glass in the middle than on the edge. And that way, you slow it down over here, and so that it arrives at the same time as the one that had the longer path to take. So that's why your spectacles typically would be maybe a little bit thick in the middle and thinner on the edges. Okay. All right, so I sometimes give a talk to school children about smartphones, and I ask them, what would it take to make a paper-thin smartphone? And it turns out that if you want to make a paper-thin smartphone, what you need to do is you need to make the optics, the lenses inside, paper-thin. Because the thickness of the smartphone is not largely dictated by the battery, because it turns out nobody wants long battery lives these days. It's not dictated by the electronics. Turns out that that can be made really, really small. It's dictated by the quality of the optics. And the reason is that if you ask any teenager what they do with their smartphone, they don't make telephone calls. No, what they do is they take images and they share them. And if you look at the adverts for the latest cell phones and smartphones, it always shows beautiful images of some mountain and says, oh, you can take this beautiful image with this phone. So the optical system is now what is specifying the thickness of a phone. So could we make a paper-thin lens so that we could make a paper-thin smartphone? So to make a paper-thin lens, I'm going to show you how you could do it. And all you need to do it is the following. You need a black Koki, so a black ink pen. You need some transparency sheets. Often when I give the talk to school children here in South Africa, they've got no idea what I'm talking about. When I say transparency sheets, I have to explain to them what those are. And you need a ruler. But if you know Pythagoras, you don't need the ruler. So just those three things. So let's see how we can make the lens paper thin. So here is a cartoon of the blue lines representing some light coming onto my yellow structure, which is going to be my paper thin lens. And I would like the structure to be such that I get a focus over here. And I'm going to do it by the phase of light. So, because remember, it's paper thin, so I can't add like thick glass to some parts of it. So I can't use the path length and the bending of the light. So I'm going to use phase. So in the language of phase, it means I would like constructive interference at this point and destructive interference everywhere else. So remember when I had the smiley face, I said, well, I could make the light add up where I wanted to add up and cancel where I don't. But that's what I'm going to try now. So this is going to be a practical example on how do you actually do that. So light is a wave. That means it has a wavelength. And so imagine I look at the central part, the light coming from the central part to the focus, and I measure the length. And then I go to another point on my optic and I measure its length. So how far does the light travel from this point to here? Well, if you use your ruler, you'll see that this is going to be longer than this. If you knew Pythagoras, you didn't need the ruler. Okay, so already we have a problem because I said that the light must arrive at the same time, but because light is a wave and I only want it to arrive with the same phase, it means that so long as I'm one wavelength too late, that's okay, I'm back on time again. So for example, if this length represented this peak and the longer length represented a different peak, so long it was one wavelength further away, the light would add up in the same way. So this arrow would add nicely with this arrow and enhance the focus. So I say, that point is great. I keep the point at the top because it has the right length. But imagine there will be some point on the optic where the path length to the focus is not exactly a wavelength out. It's maybe half a wavelength out. So what will happen now? Well, now I have light from the peak mixing with light from the trough. The arrows are going in the wrong directions, and so they cancel. But that's no good. I wanted a focus. I wanted the light to get brighter at the focus, not dimmer. So what do? Well, it's simple. I take my black Koki and I simply block out that part. Why? Because I don't want that light to get there. It's going to cancel my light. So I say, I don't want it. I'm going to block it out. And so I keep doing this everywhere on my optic, using my ruler to find out when is it going to be at the right length and when is it not going to be at the right length. And I block out all the places where I don't want the light. And so at the end of that process, my transparency sheet will look something like what you see here on the right-hand side. It will be circles where, yes, it's okay, I let the light through. The black means no, it's not okay, I'm not going to let it through. And this structure will be a lens. And you see that there's no glass here, there's no depth, it's absolutely thin. And I'm using only the phase of light to generate the focusing. And so then the next step is to say, well, let me go back. You say, okay, you know what was the problem with the black parts? The problem was there was half a wavelength out of phase. So then you say, well, why don't I add a little bit of glass, like half a wavelength worth of glass? And if I add half a wavelength worth of glass, I can bring it back in phase. And so here you see actually an image of a diffractive lens, and these little ridges represent those circles that you saw in the previous slide. And now there's like half a wavelength worth of glass added to each part. And this is essentially a paper-thin lens. So we can, by using the wave nature of light, control what it does and how it does it. So in our group, one of the cool patterns that we like to make are patterns that carry orbital angular momentum. And what these patterns are is if I take a textbook laser beam that looks like the one on the left, and I give the phase or the wavefront, remember that the joining the dots with the curved line earlier, well, if I make that like a spiral structure, I can give the light orbital angular momentum. And I can give it many values. I can give it 1 unit or 2 units or 3 units and so on. And each time I give it an extra unit, I have to give that phase an extra twist. But now it makes the light look like a spiral staircase. And you know, spiral staircases have a handedness. So they could go clockwise or they could go anti-clockwise. And so I can also twist the light one direction or I can twist it the other direction. And so these are very exotic patterns. They kind of like my smiley face, but with more physical interpretation and intuition behind it. So now let's use this as an example. I want to create light that spirals. And how could I do it using this idea of controlling phase? And to illustrate that what we do is not directly related to light, I'm going to choose a sound wave. So if I want to generate a spherical, a helical wave, I could just pass it through a piece of glass that looks like a spiral staircase. Okay, now let's try to take the spiral staircase and make it paper thin like the lens. Well, then I would get a spiral phase structure where the phase changes from 0 to some value, in this case 2 pi, around the circle. How could I make sound have this type of structure? Well, what I could do is I could take a whole bunch of little loudspeakers, simple loudspeakers that you could buy at any hardware shop, and I can place them around a circle and then look at the color that they're next to. So for example, this one has got a certain gray color, which means a certain phase. And so I simply, the wave that I send to this loudspeaker should have a certain phase to it. And as I go around the circle, the phase value is different. That means that the cycle of the wave should also be a little bit different. So like I'm moving the waves forward and backwards on each little speaker. And the idea is that if I were to drive each of these speakers with a slightly different phase, then as I funnel the sound down to a focus, the focus should have the spiraling structure. Now, usually I show a little video to convince you that this really works. This is actually what the device looks like. It's an outreach device. We use it to show school children that you can visualize phase. But on this virtual talk, I decided not to put the video in case it crashed the whole system, because it's a little bit big. So if you want to see it, you can maybe chat to me afterwards and I'll show you. But what we can show here is we can rotate macroscopic objects by using sound that carries orbital angular momentum. And you can measure that you really have created sound with orbital angular momentum. And how do you measure a sound wave? Well, just with a little speaker, a little like earphone. So if you just measure around with a little earphone, you can measure the amount of sound. And if you convert that into a wave, you can get the phase of that sound. And you can convince yourself that you've got these donut-like beams where the phase varies around the azimuthal direction. So you can really give sound a twist, just like you could give light a twist. And so what you see with all of this is that, in fact, everything we're doing, although we like to work with light, in fact, we're really just treating the wave properties of light. So when we spoke about having the waves interfere constructively at the focus or destructively, we were talking about waves. It didn't have to be light. And so then you say, well, if we're only using the wave properties, what else is a wave? What other waves could we control in the same way that we can control light? Well, cows are waves. Cows are very sacred in many parts of India. Actually, where I live, it's in a state where there are cows that roam through the pasture fields. So a cow is a wave. It can be a wave. Our quantum theories of 100 years ago tell us that matter can also be a wave. And so the question is, well, can I make a structured cow wave in the same way that I make a structured light wave? And how would I do it, and why would I want to do it? So let me go back to my cartoon. This time I've replaced the question mark with one of the answers. It's actually a lens. And I say, well, look, what is the wavelength of a photon? So the wavelength of a photon, that's a particle of light, is about 1 micrometer. So a human hair is about 100 micrometers in diameter, so it's like 1/100th of a human hair. That's the wavelength of a particle of light in a common laboratory. So what is the wavelength of a cow? Well, it depends on how big it is. It depends on how fast it's moving, but typically it's 10 to the minus 38 meters. So this would be 32 orders of magnitude smaller. That is incredibly small. And so the problem is that we don't know what optics to use for such a short wavelength, and we don't know how to detect such a short wavelength. So it's very, very hard to make a structured light cow. But you can make structured light electrons, because electrons have wavelengths in the order of picometers. Now, picometers are incredibly small, but not so small that you can't manage them. And so if we're going to make a structured wave out of electrons, what should we make it do? So you see these twisting lines as they go in space. Well, we want our electrons to spiral in space. But we don't want the electrons to spiral as particles. We want them to spiral as waves. So these spirals would be like interference fringes, but in matter. And how would we do that? Well, it turns out that we can just add 2 waves together, and that would give us some structure in the azimuth, the fringes that I showed you very earlier on. And then by monitoring one of these little blobs of the fringe, I can see where it stands, and then I can make it spin as it propagates. And I want to do all of this with matter, so with physical electrons. So we know how to get the answer to the question. Remember, I told you that once you have the answer, you must choose how to implement it. And so here we have an example of a hologram on the screen, but this is a hologram for electrons, not for lights. And if you zoom into the structure, you see that the structure is on a nanometer scale. And if you do this experiment in an electron microscope, then you see these really cool spiraling patterns. They look like intensity patterns, like the light that I showed you earlier, but these are not, this is not light. These are electrons that are arriving at the detector. And so I can reconstruct in three-dimensional space what the electron wave is looking like. And it looks like this. So in three-dimensional space, I have interference of the electron wave so that it spirals around itself. And so you can think of these as three-dimensional fringes, but not in polarization, not in how much light you've got, but in the probability of finding matter. So this is a very strange type of fringe. And just out of interest, if you're wondering why would you do that, apart from the fact that it's fun to do, so you can ask some very nice physics questions because we're in the School of Physics. And the question we were asking here was, we know that if we take a particle, a physical electron, and make it spiral, that it will radiate energy. That's how your antennas work. You wiggle electrons and they give off energy. But the question was, well, if I make a wave wiggle, so the particles are not wiggling, but if the wave wiggles, will it also give off energy or not? And it turns out that the theory says no, it won't. And the experiment also confirms that no, it doesn't. So you can make non-radiating, accelerating electron waves. So to come to the last few slides of this talk, and you would have picked up by now that I'm talking about very general waves, and in particular the fringes of those waves. And so I want to talk about another strange type of fringe. And it's related to this one, because I told you that these are fringes in 3D space of where you would find the matter. And we would call this the quantum wave function. Now the students will know what that is. So here we have fringes in the quantum wave function. For members of the public, if I tell you quantum, possibly the first thing that will come to your mind is this very famous cartoon of a cat being in a box. And if you haven't seen it, I can explain it to you very, very quickly. So the old quantum physicists from back in the day had this thought experiment. And the experiment went like this, that you imagine you have put a cat inside a box, and there's some mechanism that with some probability could release some poison. So maybe the cat would die if the poison was released, and the cat wouldn't die if it didn't. But you don't look inside the box, so you don't know what's happened. And the quantum world would say, well, in that case, the cat is in a superposition of being dead and alive. And the key word here is and, because in our normal world, we would say, well, look, the cat is either dead or alive. We just don't know which. But in the quantum world, we'll say, no, it could be both dead and alive at the same time. And now you say, but hang on, that's impossible. Can it really be like that? Can nature really work like that? So we're not allowed to do any experiments on cats. And the lab you've just seen also doesn't do experiments on cats. So they do the same sort of experiments as we do. They use light. And here would be another cartoon of a quantum experiment in my lab and also in the lab you've just seen. So you might have a little crystal, say a nonlinear crystal. You bring in a blue photon or an ultraviolet photon. And then if you get everything right, then out goes two photons, like reddish colors, and they are entangled. So they share this weird, spooky at a distance quantum nature of light. And now we ask the question like we did with the cat, is it really possible that the cat is dead and alive rather than dead or alive? How do we know which it is? So we can ask a question like that of the photons. And it's called a Bell test. And actually the test is very, very easy. So you have two photons that are going off in opposite directions, and you make a measurement on one that doesn't change, and you change the measurement on the other one. So that is depicted here by this rotating arrow, which might be the polarization of the light, but you can think about it as some degree of freedom where elements of that degree of freedom are changing. So I'm changing what I measure on the one photon while keeping the other one constant. And now you get an oscillation in the response. And here's the wonderful thing. If the answer is that the cat is dead or alive, it cannot be both, it's one or the other, you just didn't know, then the oscillation that you see in your measurements, it oscillates around this quarter mark. It never goes to 0 and it never goes to a half. But if the answer is that it can be both dead and alive at the same time, which seems that can't be right, then the answer will oscillate between 0 and a half. You can see that even without knowing the details of the measurements and so on, that just visually you could easily see which is which. And this experiment was done, well, nearly 40 years ago now. And on the right-hand side, I have Elaine Aspect's, an image from his paper. And you can see, well, okay, there's a little bit of experimental uncertainty, but I think we could all agree that the curve that this is most similar to is the one at the bottom. It's going from 0 to a half, you know, it's nearly at 0 and it goes up to nearly a half. It's certainly not this case. And so this experiment showed that in his experiments, these two photons really had the quantum property. That means that the cat really was dead and alive at the same time. And I like to talk about this experiment because it's my favorite experiment in all of physics. And it's my favorite experiment because it's the only one that I know where in one experiment, you can eliminate 25% of all physical theories, just like that. It's what all experimental physicists dream to do one day. So why do I say that? Well, it turns out that we can branch our theories into 4 categories. The one is that everything we do is local, so that things happen where we do them. Or it could be that there's something else, some non-local interaction taking place. And then on the vertical bars, we can talk about a unique reality, which means that, you know, things, you know, the cat is definitely dead or the cat is alive. You just don't know. It has a certain property. Or multiple realities, which means no, it could be dead and alive. And it turns out that with the Elaine Aspect's experiment, you can knock out this block. It can't be possible, otherwise that experiment wouldn't be possible. So it's a beautiful experiment for that reason. So to come to the end of the talk now, because my time is up, I hope I've convinced you that the wave nature of light is fantastic. We can do amazing things with it, but we can also generalize it from light to arbitrary waves. And here I've shown you how to shape quantum wave functions of electrons all the way through to shaping sound. And so to give you an idea of what this means in terms of wavelengths, it means we can shape waves from the picometers all the way to meter wavelengths, because the sound waves in this experiment had a meter type wavelength. And why do we do it? Well, in our lab, we do it because on the one hand, we can do fundamental physics, ask questions about accelerating waves. And on the other hand, we can go to school children and show them that you can really visualize phase, you can visualize orbital angular momentum, and you can have arbitrary control in very simple systems and show very complicated results. So I want to conclude by saying that this was possibly a little bit fast in some points. And so we like to write lots of popular articles and tutorial articles. And I'm quite happy to share these slides with the organizers. And in some of these references that you see here, these are educational and tutorial papers where we show you how to do all the fun experiments and without bypassing all the complicated stuff that really is redundant. And on that note, I think I'm going to conclude. I always like to thank my group because ultimately they do all the experiments. I have to admit these days, I don't get to do them as much as I used to. This picture is a little bit old, so some people have moved on and new people have come, but it's very typical of the size and diversity of my group. And I want to use the opportunity now to tell you that we love to have visitors to our group. So in this particular picture, we had, let's see, let me have a quick glance around. Aha. So we had Maya. Maya was a visitor from the US at that time. At any given time in our group, we always have at least 1 or 2 visitors. We like to send our students out to other labs, and we love to have students from other labs come to our lab. And so if you've always wanted to come to a real cricket playing nation, then come and visit me in South Africa, and we can do some cool physics and go to a good game. And on that note, I think I'd like to thank everybody again for listening, and to the organizers for bringing me here, and thank you for your time.
Okay. Thank you, Professor Andrew Forbes. It was indeed a nice talk. I really enjoyed, and then I learned many things. I mean, brushing up some of my ideas. So there are quite a number of questions. So I'll just read it out so that you can answer. Yeah, first question is from Professor R.P. Singh, who is a faculty here in PRL. He's saying that we are seeing so many applications for OM of light, however, still does not see any application for OM of electrons. Do you have any comment on that?
Right. Okay. No. Good question. So let me see. I don't think I have a slide on that. I want to see if I've saved it or not. No, I don't. Okay. So all right. So I'll answer like that. I have a slide that I sometimes show, but I see I took it out of this in the interest of time. The argument goes like this. It's not so much directly the orbital angular momentum that might be useful. The argument is more the short wavelength and the structure. So we heard in the previous invited talk that if you break some of Arb's assumptions, like the uniform illumination or the linearity or the classical stuff, you can improve resolution. And I would put the story like this. For 400 years, we have been investing in all sorts of clever optical tricks to see smaller. And why do we have to have all these fancy tricks? Well, it's because our wavelength is so long, so big, that to see small things, we have to do really clever stuff. On the other hand, if you go to a standard electron microscope and you ask them what's inside it, it's virtually nothing. They point and look. They have a few magnets to guide the electrons, but they have very, very rudimentary tools, and yet they see amazingly small structures. Why? Because they have such a short wavelength that they don't have to do anything to see small things. And so now the question that we and many, many other groups around the world are asking is, okay, what would happen if you took 400 years of optics and applied it in a short wavelength world? What would you see? What new things could you discover? And that's the motivation, not necessarily orbital angular momentum, but developing all the optical tools at a short wavelength.
Okay, thank you. There is another question from Naval. Okay, so I'll read that one. So there is one word. It's a thank you for so much for your interesting talk. So I should read that out also because that is a comment from that the attendee. His question is, to see matter waves, it is necessary that matter should have to be in motion. Like in case of electron wave. Similar question for case of Gauss wave. So do you need to have that matter in motion to see the matter wave? That is the question.
So no, what you need is you need to be able to treat the matter only as a wave. And then, of course, finally, we can't detect the waves. What we detect are the matter particles. So the detector will just detect electrons at the plane that you're interested in. And then the brightness of the fringe will be related to how many electrons appear there. So, of course, the matter is traveling through space, but it doesn't necessarily have to be. Everything that you do could be at a single plane.
Okay. Okay, thank you. Then again, there is another question from Akanksha Aurora. If I watch electron in Young's double slit experiment, they behave as they are aware of us. Are they really? They totally show different results when they are not being watched. I don't know whether there is a question, comment. So I don't know.
Yes. Yes, that's right. So this is now the dilemma between waves and particles and the role of measurement in the quantum system. And depending on who you ask, it's either a very well settled problem or still a highly controversial one with no satisfactory answer. So there are entire conferences on the foundations of quantum mechanics. Actually, I find it quite interesting myself. I don't understand at all how quantum mechanics works. So I cannot answer the question.
Okay, actually the question was something like that one. They behave, means if you are not seeing it, really, is it really true? Means if you are not seeing them, they behave differently, and if we see them, they behave differently.
Yes, and the thing about it is that it is also meant to be that it's not whether you actually made the measurement, but whether you could have made the measurement. So whether you had information that you, even if you didn't use it, and then they do behave differently. The fringes disappear. You see this, and you can also reverse it, right? So, and we do all these cool experiments. You also do them on quantum erasers, where you can remove all the fringes.
Yes.
But the reason that I always have a debate about this with my colleagues is that in our standard down conversion experiments, we bounce, let's say, the orbital angular momentum beam off a mirror at some point, possibly.
Yeah.
Well, that means that the OEM, let's say it was +1 going into the mirror and it came out as -1. So there's been a change of 2 units, which means the mirror must have had a small torque.
Yes.
I could have measured that. So if I could have measured it, why does the interference in the OEM not disappear? Yeah.
Okay, thank you. So there is another question. I think it's just a more towards comment. If possible, can you demonstrate the spiral nature of sound, what you said, and that can be done in the outreach?
Yeah, sure. So what I can do is I can share the video. I'm quite happy to give the slides to the organizers to share, but I think you did record the talk, so maybe you already have it.
Yes.
What I can do then is email the video to the organizers, and you can share it.
I think it's more required about that. I don't know how you are just making this sound, speakers, how you are aligning. That is more important, just making the phase to get that. So those information is perhaps important to reproduce this kind of, because it's interesting to demonstrate. We do also have some scheme for this outreach activity. So we do.
Okay, let me see. Shall we take a chance? Let me quickly see if I can play this. All right. So I'll share my screen. 1 second. If everything crashes, then I apologize. But maybe I'll and then you'll see how it works. Okay, wait 1 second. Let me share it. It will only take a minute, so it's okay. All right. Do you see this video? Would you see a still image?
Yes.
Can you see that?
Yeah, it's rotating.
So what we're doing here, the sound is quite high. Let me put it down a bit. So as we flip the switch, the OEM is in one direction. So we make the phase go clockwise, and then we change it and go the other direction. And then we have no phase between the speakers. And then it doesn't rotate at all.
Oh, that's fantastic.
Okay. So let me unshare this and I'll explain how to do it. So I should be back, I hope. So all it is, if you imagine little loudspeakers, to make a loudspeaker work, you give it just some signal. Imagine you give it a little sine wave on a signal generator. And then in this case, it was very simple Arduino that was programmed. Yeah. And we just changed where the sine wave for each speaker started. So by just moving each one a little bit back, we can get a phase change around the speakers. And then it's like a phased array, and it adds up to the sound, and then the sound has got the spiral. In the paper, this was a scientific reports paper. We give all the 3D printed drawings to make this. We give all the electronics to make the Arduino circuits. And
so
we
then
explain how you can do it yourself.
So then I think our student chapter kind of perhaps, reproduce that and then demonstrate that OM. I mean, so that will really be a very, very interesting demonstration for the students. Okay, I have, before finishing, because, time is running out also, and there are quite a large number of questions here and there. So in YouTube channel, because your talk is also streamed through YouTube channel, and there are some questions. So one is yes to one. He has one doubt. As a student, can I produce light with OM on my own with own gadgets available in the market? If yes, can you guide how? And I also see a video that speaker mentioned in its possibility, if it's possible. So the question is that OM light for the OM for the light, can it be possible to make using his own gadgets that's available in the market?
Yes. The problem would be to make it in a single state that's pure. But if you just wanted a range of OEM, that's very easy. So what you would do, the simplest way to do it would be to take a piece of glass and your black Koki and leave just a pie shape for the light to go through, like a pie-shaped aperture. And depending on how wide you make that pie, you will get a spectrum of orbital angular momentum.
Yeah.
That would be the simplest. But if you wanted one value of orbital angular momentum, then you would have to make a spiral plates. That would be hard at optical frequencies, but very, very easy at millimeter or radio wave frequencies.
So there is Professor Sivasis Ghosh, who appreciated your talk. It's a wonderful talk. And then he has two questions. One question is, can the matter wave be somehow used for something? For example, matter interferometry, say, for example, to explore quantum property of gravity. And second question is, could you please explain briefly why accelerating electron waves does not show radiation property?
Yeah, it's an interesting question, isn't it? So, right, so matter waves, if you do a quick Google search, you will find that there's several groups who work in this field. We actually did it just once off for fun, so I wouldn't call ourselves the main players by any stretch of the imagination. People like Ibrahim Karimi,
yes,
they do a lot of, and Ben McMorran, they do a lot of matter wave work, and they are definitely all looking for applications. They're trying to induce magnetism into materials, and our aim was to see whether we could generate strong magnetic fields and then use it to switch qubits. Okay, so that was our application, where we're going with it. So there are many, many applications, and I think if you read a little bit, you'll find a lot about them from people who know much more than me. Now, all right, so that was the first question. What was the second part of the question?
So why accelerating electron waves doesn't?
Yeah, okay. So the reason the wave doesn't accelerate is that although, you see, so the acceleration is due to the interference pattern. So it's the interference pattern that's accelerating. But the actual electrons are still going on straight lines. So because the electrons are traveling at a constant velocity in straight lines, there's no radiation. But the interference pattern, that's accelerating. But it turns out that the radiation only depends on what the matter is doing, because the wave itself, and it was an interesting question for us, because I was saying to, when we talk about wave-particle duality, we never speak about the properties of the particles. We always say, oh, you can make a wave out of anything. Okay, let's say I make a wave out of a cow. Will the wave still smell? And it's a similar question with the electron. Now, you might say, oh, the smell one is a bit of a silly thing, but it's a similar sort of thing. In the electron, where is the charge in the wave? Where does the charge sit? And it's when you answer those questions that you realize, oh, it's not going to radiate. And for the students in the audience, which I guess it's mostly students, right? let me, whenever we give talks, we always talk about our wonderful successes. We never mention all the things that go wrong. So let me use this as a good example of something that went wrong, okay? So we submitted this work to Nature Physics, I think, and they actually quite liked it, and they sent it out to review. But the referees were absolutely ruthless, and they said, you said in the abstract that you didn't expect the wave to radiate, and then you found that it didn't. So then you didn't find anything. So why did you write the paper? And then we said, no, but did you not think for a moment that maybe it could have? And it turns out that this sort of story, it works very well in a talk. So I have a nice talk on matter waves, and it's a bit more technical than this, and it works extremely well in the talk. But in a paper, it does not work at all, because your conclusion is that there is nothing unexpected here. so sometimes things go wrong.
Yeah. Okay. So there are quite large number of questions. But I'll just read two questions. One question is from Nizil. Can he use the angular slit on SLM to do orbital angular momentum sorting? And how stable would the output be in terms of visibility?
If you use an angular slit, you will control the spectrum. I can share the screen and just show you the slide. I won't. So depending on, I think you can see my screen, right?
Yes.
So depending on the width of the slit, this is the orbital angular momentum value, and you see you have all these. Oh, by the way, I think the points are the experiments, and this is the theory. But anyway, you see you have a whole spectrum of values, and the spectrum will change as you change the slit. It will be very, very stable. You'll generate a whole spectrum of OEM, but the question is, do you want that? And usually you don't want that, right? So it is a very simple way to create a huge band of OEM, if that's what you wanted.
Okay. And the width of the slit also makes the spectrum sort of smaller or broad spectral width.
Yeah, that's right. So as you change it, so the idea behind it is that if you imagine imagine you had a spiral phase around the circle, okay? And so imagine that the slits, let me go back to myself, that you can see. All right, so imagine that you had a spiral phase around a circle, and imagine I only showed you a small slit of it. If I showed you all of it, and I said, what's the OEM? You'll say, oh, it's easy. I can see it's like, say, one spiral, it's L1. Imagine I showed you just a little bit of it. You say, oh, I'm not too sure what the OEM is. I can't guess so accurately. And that's why you get a spectrum. So the smaller the slits, the wider the spectrum, because you're less sure of what it's going to be.
Yes. I'll just stop with the last question. Even though there are more questions, perhaps they can ask you later, and then tomorrow's session, they can ask you the similar kind of questions. One question is, it's more towards a visionary kind of thing. Means, how do you see the structure beam research, structure light beam research in coming 10 years?
In the coming 10 years, yeah. So I see it as an exploding field. So sometimes we think that there's already been a lot done, but actually very, very little has been done. Most of what's been done is around orbital angular momentum. It's mostly paraxial, and it's only 1 degree of freedom at a time. And I think controlling all degrees of freedom for 4D structured lights, arbitrary control is very much in its infancy. And I think that we have almost all of us, have concentrated entirely on the electric field and not on the magnetic control. We just ignore it, as if like we've forgotten that it's even there. And so optomagnetics and controlling the magnetic structures of materials by magnetically structured light is totally untouched, actually. And then, of course, there's this huge exploding field of chirality, so chiral light and chiral matter. So I think that the avenues of structured light is just going to get even bigger with time.
Yeah. Okay. So I think some more questions perhaps they can ask, because Subid is working on that field. So that's why he's just trying to ensure his career for next 10 years. You know? Okay. So with this, we'll stop here. Thank you very much for your nice talk. It was really a fantastic talk altogether, and we all enjoyed. And then you have just explained things, very difficult concepts in a very lucid and simple way that really help the students. That's why so many questions have also come. And yeah, I mean, it's really, on behalf of the student chapter, I would like to thank you. Even though we wanted you to be here for last couple of years, it's not. And then when you agreed, then the pandemic came. So somehow, you know, somebody is not, not keen of you visiting us in person. But we'll just defeat that. We'll make sure that when you are in coming SCOP conference, you come and meet with our students, volunteers, and then student chapter members, and help them also just to grow in their career.
Wonderful, absolutely.
Thank you very much. And then we'll again see you tomorrow with your technical talk.
Great. Thank you. No, it was a pleasure. Thank you very much. Thank you, everyone.
Thank you. Okay. Bye-bye.
Cheers.